Good morning, everyone. I have to say I'm so excited. This is my first in-person conference in 2 years. I don't know about you, but yay. I know. And we're going to have an awesome time and great snacks and drinks and just getting back to the normal life. So good morning and thank you for joining us today at HAI's annual spring conference. The topic is key advances in artificial intelligence. It's so wonderful to see all of you here live, but it's also wonderful to know we have an online audience joining us worldwide. I really want to just give a special shout out to our online audience. You've been with us through so many events around the world in the past 2 years. We'll continue to include you in today's discussion and going on. So I'm Fei-Fei, co-director of the Stanford Institute for Human-Centered Artificial Intelligence, which we would like to call Stanford High. On behalf of my fellow co-director, Professor John H. Mundy, I'd like to welcome all of you to our conference today. 3 years ago, High was founded on a mission to advance AI research, education, policy, and practice to better human conditions. We believe that Stanford and academia in general plays a critical role in this mission. Since High's founding, we have only seen even more growth in AI technologies, businesses, as well as the debates, discussions, including concerns of AI's social impact growing. One of our most important goals for HAI is to become a platform that brings together technologists, humanists, social scientists, policymakers, business leaders, civil society leaders, and truly all of AI's multi-stakeholders to participate in honest discussions, debates, and intellectual discourse of this technology. This brings me to today, our annual spring conference since the founding of HAI in 2019. At this point, I'm delighted to be moderating this event together with my esteemed colleague, Professor Chris Manning, one of our associate directors here at High, as well as Professor of Computer Science at Stanford University. Chris, come on.
Thank you, Fei-Fei, and welcome everybody. As Fei-Fei said, today we'll be talking about key advances in AI. There are many topics that we might have covered, but we chose to focus on 3 main themes: accountable AI, foundation models, and embodied AI in the real and virtual worlds. Today we have an incredible lineup of speakers representing deep expertise from their respective fields and vantage points. We really appreciate them taking the time to join us today.
Our format today will be brief presentations from each speaker on their respective topics, followed by a panel discussion. We invite you to step to the microphones to ask questions, and you see they're positioned on the middle aisles. We'll also have the pleasure of hearing from Kavita Bala from Cornell, and we'll then wrap up the day with a fireside chat between Professor Kunli Alukutan and Bill Daly from NVIDIA, which will be a real treat.
To kick us off today, I'd like to welcome our first set of speakers to the stage who will be talking about accountable AI. Let's hope they're all ready to go. We wanted to focus on this topic today due to the increasing concerns about understanding AI decisions, maintaining data privacy, and fairness in AI models. These issues in part demand societal and regulatory solutions, and perhaps even new laws. But they are also a rich opportunity for technical AI advances in how you can produce interpretable AI systems, or systems that still work effectively on data that has been obscured to protect people's privacy. I look forward to hearing what our speakers have to say on this topic, as well as the questions from our audience. So please join me in welcoming Hema Lakkaraju, Dawn Song, Thakkar, and Liz O'Sullivan to the stage. You're meant to take any of the middle seats. Okay. We'll wait for you. Okay, great. Let's get started with our session. So for each of the 3 sessions today, we're going to have short talks from each speaker, and then we're going to have an extended time of panel discussion. So please join me in welcoming our first speaker today, Assistant Professor Hema Lakkaraju, a Stanford grad and now a professor at Harvard University. Welcome, Hema.
Thank you. Right. Thanks so much for being here, everyone. Very nice to see you all today. So today I'm going to be talking about a brief history of algorithmic recourse and, of course, some of the work that we are doing in this space. Before I get into the details, I would like to kind of start with a simple example to help us understand what exactly is algorithmic recourse, why should we care about it, and where this all started, right? So let's think of a simple scenario where we have a loan application or an applicant who is applying for a loan to a bank, and the bank is using a predictive model to determine if this person should get a loan or not, right? And in such a case, unfortunately for this particular applicant, the loan has been denied by the bank or the predictive model of the bank. Now, instead of just telling this person that that's the case, your loan denied and you're done, it would actually be helpful if we give more information to this applicant about why their loan was rejected or what can this applicant do in order to sort of improve their profile and then reapply for a loan. Right? So that is exactly what we are referring to as algorithmic recourse, a concept that became quite popular in 2017 thanks to GDPR guidelines, which basically outlined a recommendation of right to explanation for individuals who have been adversely impacted by algorithmic outcomes. Right? And basically, this kind of a recourse helps individuals who, as I just mentioned, are adversely impacted by algorithmic outcomes to find a path forward. Okay? And the moment sort of this problem came out in the open in 2017, there has been a lot of interest, and especially from the ML and computational communities, and people quickly realized that what might be useful as a recourse is a particular class of model explanations called counterfactual explanations, which basically say the following, which is what features of an instance should be changed and by how much in order to change a model prediction. Right? So, and people started using counterfactual explanations as a means for providing algorithmic recourse. In fact, these two became sort of so used together so kind of coherently and consistently that these two terms are now pretty much synonymous. So when people say algorithmic recourse, often they're referring to these kinds of counterfactual explanations. Okay. So now let's talk about the phase of 2017 to 2020, during which a lot of machine learning folks and other researchers in the community started proposing computational techniques for generating algorithmic recourse, right? Intuitively, a lot of these techniques use a very simple tactic, which is you take a point X, which has been negatively classified by a model, for example, like that loan applicant we just talked about, and then essentially add small additive changes to that point until it crosses the decision boundary to the positive side of the classifier. Right? So that's essentially the idea. And then once that happens, you return that counterfactual as a recourse. Okay? And of course, as you can see, the point X has several possible recourses. It can go in a different direction and go to C1 or CF1, or in another direction and go to CF2, right? And that's basically where most of the approaches differ, which is how to choose among several possible recourses, and also what kind of access to the model do the approaches need, whether they need just query access or gradient access or a lot more internal details of the model. right? So that's pretty much what a lot of approaches do. Okay, so now from the year 2021 to 2022, there has been a lot of critical re-examination of state-of-the-art approaches in algorithmic recourse. In fact, recently we ourselves have been conducting a bunch of studies to really understand the utility of algorithmic recourse and using counterfactual explanations for it, right? We carried out a survey with about 182 customers who have applied for bank loans in the past year, and we basically asked these applicants about the utility and helpfulness of counterfactual explanations prescribed as recourses. Okay? And the answers were very interesting. I'll show a couple of insights here which are relevant for our discussion. The first one is an overwhelming majority of the participants essentially said that this kind of a recourse is extremely useful for them. So that's good news. But we also found something which can be a very impactful finding. An overwhelming majority of the participants said that they would be very unhappy with the bank if the bank provides them a recourse, and then if they implement it and go back, they somehow don't get a loan. In fact, the impact of this is so huge that 83% of the participants actually said that they'll never ever do business with the bank again. Right? So clearly, this is a very important piece. So if at all we provide a recourse to somebody, we better make sure that it is really correct and we are going to sort of hold out that promise, right? So this observation in particular triggered a bunch of research in my group, and we started thinking about when can a recourse that we provide not be valid or not be useful anymore or not result in a positive outcome, right? And with no fault of the bank or the individual, there are algorithmic issues that come up which could cause this. For example, recourse generated by existing methods is typically not valid when the underlying model changes. Whereas in real world, models are regularly updated for a variety of reasons, including handling data set shifts and kind of consequent retraining, right? So now what do we do about this? What is our solution? So in order to address this problem, we thought about two key questions that underlie this. One is, how do we even characterize model shifts? And the other is, once we characterize model shifts, how do we generate recourses that are robust to different kinds of model shifts, right? And while there are several ways to answer these questions, the way we thought about model shifts was as if you take a model and its parameters, you can think of additive changes to those parameters as shifts of the model, right? Of course, alternatives can be used with our framework. And once we have this notion of a model shift, how do we generate recourses that are robust to this kind of shifts? That's where we sort of use a typical min-max formulation, like for those who are familiar with adversarial machine learning. The idea is to find a recourse that minimizes the worst case loss across various possible model parameters, right? And that's what we do. Okay, so we leverage these tricks from adversarial machine learning and adversarial training. And results show that this kind of a method improves the robustness to model shifts of recourses by about 74%. Okay? And in recent years, there has been more critical examination of state-of-the-art and algorithmic recourse. For example, thinking more about adversarial manipulation of this. How are adversaries likely to manipulate or game models or recourse algorithms in order to sort of induce undesirable biases or unfairness? And also thinking more about privacy risks of algorithmic recourse. Right? So if I give you a recourse, then I'm exposing some information about the model to you. How can an adversary use it in a bad way? Okay? All right. So with this, I'm going to thank you all for your time and look forward to more discussion about this. Thank you.
Thanks a lot, Hema. And now I'd like to introduce our next speaker, Professor Dawn Song from the University of California at Berkeley.
Great. Thanks, everyone, for being here. My name is Dawn Song, a professor in computer science at UC Berkeley, and also the founder at Oasis Labs. Today, I'll talk about towards building a responsible data economy for responsible AI. As AI and deep learning has been making huge progress, it's important to ensure that we develop responsible AI. And it's great to see that this is the focus of the first session today. There are many different aspects of responsible AI. For example, my group has been doing a lot of work in the area of understanding and improving the security and robustness of AI and deep learning systems. For example, here is example of some of our work on exhibits at the Science Museum in London. Given the interest of time, today I will focus on another really important aspect of responsible AI as well, related to privacy issues and beyond. As we all know, data is a key driver for AI and machine learning. And more data is being collected every day, and the size of the data economy has been growing exponentially. However, a lot of this data is sensitive, and handling the sensitive data has posed unprecedented challenges for both individuals and businesses. Individuals have lost control of how their data is being used. A lot of users' data has been sold without the user's awareness and the consent. And businesses continue to suffer from really large-scale data breaches. In many of these attacks, attackers steal sensitive information of hundreds of millions of users in a single attack. And most importantly, a lot of this valuable data is sitting in data silos and not being utilized due to privacy concerns. And we cannot continue the status quo. As we move forward in the digital age, these issues will only become more and more severe. And to the extent they will hinder societal progress and even undermine human value and fundamental rights. And hence, there's an urgent need for developing a framework for a responsible data economy. What do I mean by a responsible data economy, and what are the goals and principles? So first, we need to establish and enforce data rights. These data rights serve as a foundation of the data economy and prevent misuse or abuse of data. And also, it's important to ensure fair distribution of value created from data, so that users should be able to get sufficient benefits from their data. And most importantly, we need to ensure efficient data use to maximize social welfare and economic efficiency. And there are many challenges for developing a framework for a responsible data economy. There is natural tension between utility and privacy. And data is different from physical objects. Data is non-rival. And hence, we cannot simply copy the concepts and frameworks used in the analog world. And to develop a framework for a responsible data economy, it requires a combination of technical and non-technical solutions. Here, I will briefly talk about the three components, including the technical solutions, incentive models, and legal frameworks. So first, let's look at the technical solutions. It's not advancing. Okay, so first, traditional solutions are insufficient to protect data use. Traditional technical solutions focuses on data encryption that only protects data in transit or at rest. And also, data is either not used, or if it's used, usually they are copied. And once the data is copied, it's very difficult to control the further use of copied data. And also, the traditional method often relies on anonymization, and anonymizing data, as volume of research has shown, that is insufficient to protect users' data privacy. So we need a new technical solution that can provide data protection in use. And in particular, there are two needed aspects for this. One is that we need to be able to ensure controlled use of data without actually copying the raw data. And secondly, we need to be able to protect the computation output from leaking sensitive information about the input. So first, let me just briefly motivate why we need to care about protecting the computation output from leaking sensitive information about the input. Oftentimes, because these outputs are computed from the sensitive information from the input. Here, let's look at a concrete example. So we all know neural networks have very high capacity. So there's a question, whether these neural networks actually remember training data. And if they do, whether attackers can exploit this vulnerability to actually extract the secrets that were in the original training data from just simply querying the learned models without even knowing the details of the models, such as the parameters and architectures of the models. So this is what we set out to do in collaboration with other collaborators, including researchers from Google and so on. So in this case, we looked at the language model. So with the language model, we trained the model from a data corpus. And the goal is that when given a sequence of words or characters, the model will predict the next word or the next character. So in this example case study, we performed the following learning task, where we trained the language model on the email dataset called an unrun email dataset. And this dataset naturally contained users' credit card and social security numbers. Our work showed that by designing new attacks, the attacker can actually, by just querying the learned language model without learning the details of the model parameters and architectures and so on, is able to automatically extract the original social security numbers and credit card numbers embedded in the original training data. As an example illustrating that even as we train machine learning models, it's important to ensure with the protection of users' data privacy. And so this is an example of, on the particular learning task of a relatively smaller model. We also extended our work to show that even on really large state-of-the-art large language models, such phenomena also exist. For example, by studying GPT-2. And our work showed that by designing new attacks, a similar phenomena also occurs. Attackers can also automatically extract sensitive information, in this case, for example, personally identifiable information from the original training data. And so all this illustrates that even as we train machine learning models, it's really important to take the measures and precaution to protect users' privacy. So what can we do in this case? So in this particular case, we show that there are some mechanism that we can use. In particular, instead of training a vanilla language model, instead, if we train a differentially private language model, then this can significantly enhance the privacy protection for users' data, and also at the same time still be able to maintain similar utility for the model. And the next speaker actually will talk in more detail about what differential privacy is and how to develop some of these differentially private machine learning algorithms. So differential privacy is essentially a foundational privacy notion with formal guarantees. And volume of research has been done in differential privacy. But however, it's actually been very challenging deploying differential privacy in the real world for a number of reasons. A lot of data analysts and machine learning practitioners are not experts in differential privacy. And there are actually many different types of differential privacy mechanisms that one need to use depending on the particular analytics or learning tasks. So in our recent work, we developed automatic methods to make differential privacy much easier to deploy and be used in practice. For example, in our work in Chorus, we automatically develop program rewriting techniques and tools to automatically rewrite data analytics queries to embed differential privacy mechanisms into the queries itself, such that even though the analyst doesn't know anything about differential privacy, we can automatically convert a data analytics query into a differentially private query. And when the query is run on the database, it will also automatically return a differentially private query results. We also extended the work to develop new, essentially high-order type systems to be able to automatically analyze machine learning algorithms to automatically prove that it is differentially private. And our automatically derived bounds, in certain cases, have exceeded manually derived privacy bounds. and the work has won the Distinguished Paper Award. And also in our most recent work, we developed the system called PrivGuard, which is the first work that automates the tasks for ensuring that a data analytics or machine learning algorithm program satisfies the privacy regulation as compliant to privacy regulation, including, for example, GDPR and CCPA and so on. With this work, we enable users and data owners to specify their desired privacy policy, and by using static analysis of Python programs for these data analytics and machine learning algorithms, the static analyzer is able to automatically check whether the program is compliant with the desired privacy policy. And some of our work has been piloted in various industries, including Uber, BMW, and other sectors. So far, I've only talked about one of the component technology on differential privacy to enable responsible data use. So in fact, there are a number of different components that are needed to ensure responsible data use, and I call them responsible data technologies. So differential privacy helps protect the computation output from leaking sensitive information about the input. We also need to ensure that the computation process itself doesn't leak sensitive information, in particular, enabling us to do computation over encrypted data. And this is what secure computing technologies enables. And there are different types of secure computing technologies, including cryptographic-based methods, such as fully homomorphic encryption, secure multi-party computation, and so on, as well as using secure hardware, such as Intel SGX and secure enclaves and so on. And also, federated learning is another type of approach where allowing the data to stay on user's device and perform distributed machine learning across different devices to train the model. And again, the next speaker will will share more details in this area as well. And finally, distributed ledger provides a solution to ensure that users' data rights are kept in this immutable ledger and help enforce users' data rights. Okay. Oh, so to put this all together, by combining secure computing and blockchain immutable ledger solutions, we can enable a new type of data asset, a new type of assets that we call data assets to ensure that the user's data rights are maintained, and at the same time, data can be utilized in a privacy-preserving way. So I won't have time to finish the other components of this framework for building a responsible data economy. So overall, by utilizing these responsible data technologies, and also we developed new methods on data valuation using Shapley value and so on. So this can enable a new framework of a responsible data economy. Thank you.
Great. Thank you, Dawn. Next up, we have Thakkar, a senior research scientist at Google. Welcome.
Good morning, everyone. So today I will focus on how to train production machine learning models in the framework of federated learning with formal differential privacy guarantees. So the previous speaker focused on a few keywords here, and I'll go into more details. So let's start by briefly understanding what do we mean by the notion of differential privacy. So imagine we have a data set D that contains data from several users, and we use this data as an input to an algorithm, here denoted by A, to get out a model theta. So this algorithm is randomized, and as a result, there is a distribution that the algorithm can have over this data input. So what I'm showing is a distribution over some set of outcomes. Now imagine another data set D prime where I remove the user of, the data of one user. So in yellow, this is the new data set. And if I input this instead to the technique, I could obtain a different distribution over the outcome space. What differential privacy guarantees is that the change in between these two distributions, where the input was D versus D prime, would not change by much. In particular, it provides a mathematical guarantee for how much these two distributions can vary for any particular set of outcomes. So no matter what the input data set was among these two neighboring data sets, it will be difficult for an adversary to distinguish looking at the outcomes. So with this notion, in 2018, researchers from Google came out with a technique called differentially private federated averaging. This is a technique to collaboratively train a machine learning model using distributed mobile devices in the setup of federated learning. So here's the setup. We have a population of mobile devices. They want to train a model. The technique proceeds as follows. First, we uniformly sample a subset of devices. Each of them gets the current model, and then they do some tasks at their end. They use their local data to compute what is called a model update. There is an operation called clipping. So they clip their update and then send them to an orchestrating server. So this average update now needs to be privatized. So some calibrated noise is added to this update, and this is how we obtain a differentially private update. The noise can be added by the devices or the server, but basically it needs to be calibrated such that it hides the influence of individual devices. Now, once we have this differentially private update, it's fed into the model, and this training proceeds. So this is how iteratively you can train a model in federated learning such that it can have guarantees of differential privacy. In 2020, what we did was we trained a 1.3 million parameter language model using this technique. This was used for next word prediction for Spanish language users in the Gboard app. To give you an idea of how intensive it was, we trained for 2,000 rounds. It took around 3 weeks to complete, and 20,000 devices participated per round. In terms of utility, we saw model quality as well as utility improved over the baseline that we had. So for example, these metrics, we saw positive improvements over the baseline. We also provided some empirically tested privacy advantages over non-DP models for this release. So for example, something Don talked about earlier, we evaluated for unintended memorization of data on this model. However, for a differential privacy guarantee, what we could say was if we can ensure uniform sampling from a known population size, then we can guarantee then we can provide a differential privacy guarantee as follows. So the important point here is that uniform sampling is required for what is called privacy amplification by sampling to provide a strong privacy guarantee for this technique. And we actually show that this is infeasible to provide in practical training. To go into a bit more detail, why is it so? There are various challenges that we encounter in actual real-world training. For example, a device can have a limited availability. It may not be available for the full 3 weeks that we train over. It could be, for example, not charging, not connected to the internet, not idle. So there are various reasons where it could disconnect and reconnect in training. For efficiency reasons, communications are started by devices. So the server doesn't ping all of the devices that, hey, are you available? It's the other way around. So they are client initiated. In particular, at any point, it's difficult for even the server to know what is the size of an active population. This is also incompatible with load balancing techniques. So to summarize, we had a protocol later that was feasible, but it required some complex changes, and it still relied on amplification with a large number of devices being available. So in 2021, we came up with this new technique called differentially private follow the regularized leader. I'll briefly go over how it operates. So we have the same setup. The model is now sent to a batch of devices. Each device does the same that they did before. They compute clipped updates. To the averaged update, the server does something different. It uses a tree aggregation method. I'll not go into details in the interest of time, but this aggregated update is used to have a model for the next round. What's important is there is no sampling requirement for this technique. So the server can just operate on the next batch of devices that is available. And in the paper, we also show that it performs, this technique outperforms federated averaging without any amplification, and it is competitive with DP federated averaging with amplification at various settings. So with DP-FTRL, what we did was we trained the same 1.3 million parameter Spanish Gboard model. This training ran over 6 days, and 6,500 devices participated in each round. So it's a 3x gain in both training time and devices. We had to make several other improvements. For example, each device could participate at most once daily. We tightened the privacy accounting. But with this, what we were able to do is to train the first production neural network that trained on user data and was announced with a formal differential privacy guarantee. So what was the, and this was announced in February this year. What was the guarantee? So we were able to satisfy a user level ZCDP guarantee. It's an analog to differential privacy. You can also get differential privacy guarantees for this from this guarantee. And we also observed model quality improvements over the previous DP federated averaging model. In terms of future directions, we are currently conducting research for better aggregation mechanisms for prefix sums, which is used in this FTRL technique. And another direction is to train more production models that have formal differential privacy guarantees for them. So this work was the result of the efforts of people from multiple teams over multiple years. So I'd like to thank every one of them, without whom this work wouldn't have been possible. With that, I'd like to conclude. Thank you.
Thank you, Om. Now I'd like to welcome the last speaker for this session, Liz O'Sullivan, CEO of Parity.
Hi, everyone. My name is Liz O'Sullivan, and unlike these amazing colleagues here on the stage today, I am not a lawyer or a data scientist or an academic of any kind, but instead I'm a serial startup masochist, as I like to say, and an activist, which means I'm really good at making pitch decks and yelling at politicians in the hope of enacting meaningful change. Oh, thank you. Wasn't expecting that. But what I am is somebody who has seen the way that things work practically in industry, where a lot of these concepts and these technologies are made and put to use. And for the last 3 years, my focus has been on the responsible AI marketplace, which means that I've generated quite a lot of knowledge about the way that large enterprises and corporations are tackling these questions of how to make their AI responsible and fair without discriminating against or harming certain minority populations. And so if I talk about the responsible AI marketplace a little bit, 3 years ago when I started on this journey, we began with doing a lot of education. And so people really came to us, and every client had their own line, and this client line was usually something like, oh, our models aren't biased, we don't use age or race or gender as inputs to our model. And then they learned a little bit more, and so a couple years later it became, oh, our models aren't biased, we don't use zip code because we don't use proxy features, and so on and so forth. And so today, the rest of this talk is going to be a couple of the more common misconceptions that I think we keep hearing more regularly today, and some unanswered questions that I think it's really exciting to see progress, especially even just in the talks that we've reviewed this morning, but questions that we'll be working on together as the combined research and industry communities. And so the first misconception that we hear quite a lot is that, believe it or not, a lot of large enterprise believe that they have reached consensus on how to debias very particular forms of existing enterprise AI. And this is particularly heightened when we look at tabular data and different kinds of models with regard to trying to comply with existing laws, in particular anti-discrimination laws. And so, of course, I'm talking about this notion of disparate impact, which is the unintentional discrimination against protected classes. It's a concept that's created by people, that's used mostly in the legal system, but it is also the name of several metrics that purport to measure this kind of an unintentional discrimination. And people tend to think that once you have measured this, then your work is done. As long as you don't cross a certain threshold of performance between protected classes and the majority group, then your AI is compliant, it's not discriminatory. And so in order to get to this threshold, which I think is very much under debate, people use a combination of pre or post-processing techniques, but what they neglect to understand is that sometimes these techniques in particular industries can actually themselves be illegal in the application of it. And industries disagree with one another, and they actually can introduce new risks or political risks with the treatment of different protected groups as differing from one another. And then if we think about language models, there's so much to talk about here. I'll actually come back around to this a little bit later on today. And so for the last few years, we in the activist community have been yelling very loudly about the need for regulation. And I think a lot of people think that once we do get these new laws, many of which are actually proposed already, that everything will be okay. And that no one will get harmed by either intentionally or unintentionally by these algorithms. And I can tell you that that's just simply not true. In fact, we saw the country's first AI-specific regulation in New York City earlier this year, the Automated Employment Decision Tools Regulation, which reaffirms candidates' rights not to be unintentionally discriminated against by virtue of the, again, notion of disparate impact. But the law only calls out 3 categories that people have a right to not be discriminated against based on their age, their race, or their gender. And as we all know, there are many other minority categories that would otherwise be implied in the existing laws. And so in some ways, by calling out these 3 protected categories exclusively with regard to AI, the lawmakers in New York City, the City Council, actually made a huge oversight in omitting people, for instance, who have disabilities. Now, that would potentially give cover to large enterprises who may otherwise try to measure the effect of these kinds of algorithms on disability communities, even though it's very difficult to get access to that demographic data. And so in some ways, this law may have actually made things worse. And of course, we're all looking forward to the EU regulation, which is probably going to be agreed upon this year, the AI Act. And the AI Act, in a lot of ways, is very similar to the General Data Protection Regulation, or the GDPR. And I think that it's really important to note that billions of dollars in industry have been spent trying to comply with the GDPR because of this really significant fear that there would be massive penalties, on the order of millions of dollars, or a large percentage of the revenue of the company. And so this has been many years now that these companies have spent all this money and time and effort to comply with the law, and the enforcement simply has not shown up. And so there's really a big concern that this will continue and will have actually discouraged people from trying to comply with the AI law from the EU when it actually does arrive. And so I think it's important for us to try to examine whether the correct incentive structures actually do exist in industry as opposed to potentially in academia. Don't get me wrong, I'm a startup CEO. I believe in industry, and I do know that we have been doing quite a lot of really good work in this space. But I think it's important also to recognize that the startup incentives are sometimes out of line with what we want to create with regard to responsibility in the world, or accountability for our algorithmic systems. The venture capital market creates really interesting incentives for hypergrowth. And I'm not thinking, of course, of my colleagues at Parity here, but I am thinking about the very clear pipeline for especially heightened awareness of computer vision companies that have transitioned from really good social goods type work into the military industrial complex, the prison industrial complex. And so I think one thing that we do hear a lot at Parity is that there are companies who really just want a simple solution. They want to sort of hide behind our brand, our logo, and try to ethics wash, as we refer to it, with a simple solution that may not actually go all that far. And it's very easy for us to say no to these engagements, but when we do, there are competitors in this marketplace that are very happy to take on these ethical quandaries and dilemmas. And so I do want to say there are plenty of wholesome actors in this space, and so really rooting for them and cheering them on. And so it'll be very interesting for us to all check back and see how we did in 10 years. And I think the most important question, which I'll spend probably maybe a little bit too much time on here, but just another minute or two, is this question of how can we sufficiently manage risks on models that have impossibly large complexity? And in particular here, I'm referring to computer vision models or large language models, where the notion of debiasing something is really an infinite task. And so how do we even define bias in language? I don't think that we have consensus on this at all, because isn't all language biased? And when it comes to large language models, there's a really important debate raging that I don't think is getting nearly enough attention at all. And this is this notion of curating data sets and training data, which is sometimes referred to as censorship, which I find very odd. Because the notion of redacting training data for toxicity is referred to negatively as potentially violating some form of freedom of speech, And because it's very often that the organizations who make these arguments are those that are also saying things like that partially conscious AI may already exist to some degree. And I'm not here to comment on that, or whether it's possible now or whether it ever will be possible. But if you will forgive me the really bad joke, I will say that on this question, I do find myself to be very personally biased in favor of curation because of my experience using no-code tools to train computer vision algorithms. And when we did this, math alone was never sufficient to, for instance, teach the algorithm that not all wedding dresses are white, and some cultures use red to express that, to celebrate that occasion. It actually required human experience and a diverse team who was actively testing for this because they knew already that it existed. And curating data was the only way to sort of train and teach these algorithms that other cultures exist. And the sensitivity is most heightened, I believe, around the debate of how to debias large language models. And again, I'd like to say to the organizations who are claiming that perhaps these models are somewhat conscious, or that training data redaction may actually, in virtue of protecting certain people, violate some notion of free speech, that this is potentially, interpreted as, we can call it being a bad parent, right? Because what parent would, for the sake of some free speech ideals, sit their child in front of Reddit and ask them to consume quite a lot of toxic content that they would then learn about the world from that information, or potentially even memorize it? Because if we are going to create a consciousness, and again, not commenting on that today, then we are going to be the ones who teach it our concepts of morality and ethics, and we can't just rely on this emerging from nowhere, because it simply won't. But there is good news, and I do think that it's really, really heartening to see. It's heartening to see that this field that we are working in is extremely popular, and it's growing in popularity every day. Actually, at Parity, our very first intern was a high school senior who's now at Berkeley, and she told me that she knew that responsible AI and algorithmic fairness was something that she really wanted to pursue with her career already. And in many cases, the right people are at the helm. I can think of dozens of examples of incredible people who are running organizational groups at universities, independent research organizations, and even in large tech companies against impossible odds. And again, as an activist, I can say that it's been really amazing to see how quickly regulation has progressed in this space. So help is on the way, and it does seem that it's been really a fight that has garnered a lot of attention and a lot of progress. So it'll be very exciting to see how things progress over the next couple of years. Thank you.
Thank you, Liz, and thank you to everyone on our amazing panel. A lot of interesting topics there, ranging from algorithmic recourse to how we can do learning with privacy, and then talking about how some of these issues of regulation and addressing bias do or don't work out in the real world. We're hoping now to have half an hour of discussion, and we welcome the audience to come and take part in the discussion. So if you have a question that you'd like to ask, please come to one of the two microphones. There's one there and there's one there. And if you could just very briefly introduce yourself before asking the question, that'd be really helpful as well. But let me start off with asking one question, and I guess I'm going to key off Hima's first talk, but other people could have opinions. So, I mean, overall in this session, we heard, some good news, that there are new ideas of giving explanations for algorithmic recourse, new ways of learning with differential privacy. And I think that is actually good to say, because there is real good news, right? That really for almost the entire history of machine learning, people ignored all these issues, and now that there's a lot of focus on them, it is actually leading to, robust new areas of study and genuine algorithmic advances and letting us do things. But I was still left a bit questioning as to this algorithmic recourse. So the idea is you're going to tell people what would take them over the line to make them eligible for something. And I was sort of sitting there thinking about something like an insurance scenario, and I was wondering, how do they, so there are different ways you could move in different directions, and Hima mentioned that problem, but no matter which direction you move, isn't the answer for how you'd be able to get insurance with us is, if you lived over in the next suburb, then we'd give you insurance, or if you owned a more expensive car, then we'd give you insurance. I was, in the abstract that you had 93% of users said they'd be happy to get recourse and be useful, but would they really be happy when they were told the answer? I was really left wondering about that question.
Right. No, I think that's a great question. And while we didn't have time today to go into all the mechanics of how to think about recourse so that we don't run into these kinds of problems, right? Like I think sort of one of the things is over 3-4 years, different methods have been proposed. And some of the methods, especially the newer ones, especially try to avoid scenarios like what Chris mentioned, which is we might not want to tell people to act upon certain features that are not actionable, right? And domain experts can provide us with inputs on those features, whether it is telling somebody that, go live in another suburb, or whether it is telling somebody that, get a master's degree, but also without increasing your age, right? So people have sort of thought about these kinds of things, and this is where thinking about like causal graphs or structural causal models when recommending recourses can be like a very useful sort of an approach to address some of these challenges, and that's something that has been proposed by prior literature. Of course, it brings up new challenges like, do we really have causal graphs of real world data sets? Maybe not, but then again, we have some answers in the sense that, we can use some of these variational autoencoders and so on to kind of create latent spaces, capture some of these relationships, learn them from the data, and then sort of use it so that we recommend recourses that don't sound outlandish, right? So that is one of the ways in which we can address this problem. Of course, that said, the thing that while I'm cautiously optimistic about like where we are going, I broadly agree with your point that, there could be several unknown unknowns there. And we are sort of, I think machine learning as a field, there is a tradition to progress, we find an area, we sort of propose a bunch of algorithms, then realize the pitfalls of those, then take corrective measures and rethink, right? That's why I was saying, like, we critically re-examine and then redo things. So yeah, that's what I would say to that.
Does anyone else want to make a comment on that, or should I grab the next question? Oh, okay, well, I'll take the first audience question.
I think a gentleman was
Oh,
first.
okay, sure.
I'm Ted Selker, and I've thought about AI and user interface most of my career. I'm thinking about this box. We got this box where we got the computer and the AI doing stuff, and then we have the person. We have a system with people. And there's a couple of ways that I kind of want you to maybe answer about that. One is that I've worked in voting technology where a lot of the beliefs of people about how secure things are trumps what actually is. And it's very hard to see what algorithms have done, whether they're really doing what they say they're doing, relative to securing things. So that's one place. The other place, very quickly, is just you take a look at this Romanian that hacked all sorts of famous people by just kind of guessing passwords and their, whatever. So and the question is, a lot of my more recent papers are about how to make people recognize how to make themselves be more secure, how to make privacy happen at the interface between the person and the system. And I just wonder if either of you guys have any comments on those things.
Someone game to address that?
Maybe could you clarify the question a little bit more? Like, right, so you're asking about security and privacy. So maybe you can clarify the question a little bit
Well,
more?
basically, people are often losing all of their privacy and anonymity and all of the things that we're trying to support right at the moment when they are interacting with the system. And we don't necessarily help them know when they're doing that, but also we don't give them good tools for seeing whether they're doing that. And then also within the system, people have no idea whether they're doing all these fancy things that we've written all these papers about how we're anonymizing and protecting people's privacy. And so what are we doing, what are you guys thinking about relative to how we make people understand what they're doing that makes this accountability happen?
Okay. Yeah, sure. Yeah. Happy to help. Yes, I think this is a really great question. Also, it's actually a huge challenge that the whole security and privacy field is facing. In the sense that, yes, like you said, we are developing all these technologies and also helping the actual engineers to, when they build a system, to make it easier for them to build more secure and privacy-preserving systems by developing all these tools. And also on the user side, however, users are not as sophisticated. So there are a couple of issues. One is, right, unlike a system, you can see how fast it is. So it's very easy for users to tell whether the system is efficient, is well-performing. But in terms of security and privacy, it's very hard for a user to tell apart. And even it's very hard for actual experts from just looking at the black box to tell whether the
Maybe
system
impossible.
is secure. Right, exactly. So, and hence, this actually has been an issue for example, for companies. One company spends a lot of effort improving the security and privacy of the system, and the other one only just claims that it has good security and privacy measures and not actually spending the resources. So you can see one actually use a lot of resources, but for the other one, they can use the resource to do other things to improve the business and so on. So from the user side, because the user cannot tell, and often the companies who actually don't spend the resources, actually they are not necessarily at a disadvantage on the market. So this actually has been essentially a discouragement for a lot of companies to put in more resources in the space. But however, of course, with regulations like GDPR and CCPA and so on, so this has put more requirements on the company side to put more resources to address these issues. We also recently have actually done a meta study in the effectiveness of, for example, data rights in GDPR. And what we have seen is that one, yes, it's actually very hard for users to even know all these different data rights, and it's very difficult for users to, in practice, to actually try to enforce these data rights as well. So overall, I would say it is a big challenge, and that's why for the whole field, I think we need to essentially combine the different aspects, including, as I mentioned, technology the legal aspects, and also some the proper incentive models to
Are there any other thoughts?
Right, exactly.
Yeah, I just wanted to quickly chime in, and I think I agree with a lot of the points that Professor Don made. And I think it's kind of like there are multiple parts to this problem that you discussed, and it's obviously a very deep problem. So one is, I think Don mentioned a little bit about the regulation. While we may not entirely know the full sort of the pipeline of, okay, my data has been taken, it's going into this recommender algorithm, that algorithm, something else, and so on. Ideally, if we had that level of understanding and transparency, that would be great. But given that, that is almost like a sort of an impossible pipe dream, maybe even like thinking about regulations in the form of, while each individual may not be able to see this entire chain, kind of giving some high-level guarantees in terms of, yeah, this company is adhering to these standards, could be like one first step to that problem that you're worried about, which is what is happening to my data, how do I sort of think about it, and hopefully my data is still private and so on. So I also echo that sentiment that maybe regulation can help a bit, but I think going forward it might be interesting to also explore when used to see how to train people to be more aware of these kinds of things as end consumers, right? So that is, yeah.
Okay, maybe we should go to a next question.
Well, good morning. My name is Misha Dollar. I was academic professor at King's College London for many years. I'm now chief architect here in Ericsson Inc. In my community, the wireless community, we really tick around standards. They have been very powerful in bringing together a very heterogeneous ecosystem, everybody with their own commercial interests. And as part of the standardization processes, we also dealt with a lot of security issues, with a lot of privacy issues. So my question to you is very simple. Do you think it's time now to start talking about global standards, maybe one standard of AI, which would help with security, privacy, and also maybe also with the federated AI learning issues, interoperability between models. So I'd like to get your view on that. Thank you.
Yeah, I can talk about that a little bit. So, we pay pretty close attention to this because I think that one of the counter arguments against regulation has been historically from large industries who really don't want it to come, and their proposition is usually something along the lines of, oh, we'll just follow certain standards. And usually this is the first step towards getting a regulation anyway, and so it's been really heartening to see, here in the United States, we have NIST is just in the process of putting out their anti-bias framework, their risk management framework, and the White House is working on a digital Bill of Rights, which is, a form of self-regulation as well. But other countries are way farther along in this process, so including China, Singapore, Japan, lots of companies have, not companies, this is where my life is, but countries have been working really hard to create their own standards. And a lot of them, there is a lot of overlap, right? Like data protection, privacy, there's, right to explanation has made a resurgence in some of these standards and things. But I think you would have a really big challenge in trying to get all of these different value systems to agree in certain areas, like these corner cases. So I do think that there's value in trying to create a global standard. I think that if there were a place that it might happen, in the United Nations. But I think it would be pretty difficult to get people to agree uniformly across different populations, just because of the differences.
It's a good point. I'm sorry to interrupt. What I meant is not a legislative kind of standard. I mean actually really engineering standards, right? So we have succeeded really, apart from the regulatory frameworks, which give the envelope, to actually give technical standards, which would help then, I think, also with a lot of the privacy issues. That's what I meant. Sorry,
Yeah.
Just wanted to clarify that.
Do you have any thoughts on whether there could be shared federated learning? That's a corporate challenge as well as technical challenge.
Right, so what I'd like to say is having a uniform standard for all kinds of applications might be difficult to have a benchmark that this is what needs to be achieved. Like from situation to situation, it can be different, and what privacy means. what leakage implies. And so, for example, for our cases, even if you show that models don't memorize data, that can be a huge step forward in showcasing how the protection might work. Of course, providing strong guarantees against leakages are even further steps, but then what guarantees do you get can differ from one scenario to the other. How strong the guarantees are, what data is being protected. So yeah, it kind of depends on what application you operate in. Yeah, research is taking steps towards showcasing different kinds of protection via various methods.
Any other thoughts? Go on.
Yes, I think in these different sub-technical areas, there are standards consortium where different companies and academics are coming together to make progress in the space. So for example, in secure computing, there's a confidential computing consortium where Google, Microsoft, Intel, a lot of the top tech companies are part of this global consortium that's actually setting up standards and unified APIs and so on to enable secure computing.
Okay. Thank you.
Yeah. Okay, so moving on, I didn't actually realize there was a third mic up back there, but we've got a person at it, so I could take that question.
Thank you so much. Great talk. Awesome talk. My question is for Liz. I think that a big problem in today's big tech is political censorship. Google, co-founder of this conference, has been clearly accused of political censorship on both sides, left and right. Either it's the search engine, either it's YouTube. I wonder whether what Elon Musk tried to do last week is the solution, is essentially having people with a different political point of view in the board of directors of these companies, because I don't believe in regulation. So if you give politicians the power to regulate these companies, you're going to get the bias of this or the bureaucrats of whoever embedded in those regulations. So I still believe that the free market is the way to go, but I don't know what the solution is. Thank you.
Yeah, so I do think that when we talk about political risk, there are a number of ways to interpret that, and certainly what you're talking about does exist, and it does happen. Like, there's no question that email providers, the research that just came out the other day, that they filter, and it all comes down to user data, right? Like who's marking what as spam and who hangs out in that email server. But when I was talking about political risk, I was actually mentioning something more along the lines of treating protected groups in a different way in order to try to balance outcomes across those protected groups, which may be fine under certain administration, and it may be actually pursued actively under a different administration. So I think political risks are a very unique kind of risk for organizations to try to defend against, because it does shift, right? The administrations change, right. And so that shifts pretty regularly. So whatever regulations do exist, I think we need to be very careful that they're adaptable and that they're flexible enough to incorporate new research as it becomes available.
Thank you.
I feel forced after that to ask the opposite question. So how many people saw John Oliver last night? Anybody see it? Not very many. So John Oliver last night was on data brokers. And basically what it was about was this enormous unregulated market of trading of all of our data. So that all sorts of apps you use regularly collect data, and the various companies can make money by selling it to other people, and then they sell it to other people, and they sell it to other people, and the people who it ends up with, actually it's sometimes the government, but it's often different companies, and sometimes it's political parties, so they can send you targeted ads. This is the free market at work, right? They don't pay too much attention. They don't encourage people paying too much attention to it. There's a lot of money by trading around everybody's data. Now, in all honesty, that's not an AI issue. This has nothing to do with AI. This is just raw data being shared around the system. But it doesn't really seem like the free market by itself solves that problem. In fact, it's the free market that is building this problem. So I wonder if any of you have any thoughts about that.
So that's exactly the data economy, responsible data economy problem that I was talking about. Exactly this market of selling data and without users' awareness and so on. And sometimes the data is sold under the premise of anonymization, but actually we all know that it actually doesn't really protect user privacy and so on. So, and that market overall even and the market about how to use the data, like you said, and sell to others and so on. This data economy is just growing like really fast and so on. So that's why you mentioned that the data economy is not an AI problem, but actually that's why in my talk, actually at the end, I wanted to make the point that building a responsible data economy is an important part of responsible AI. Because at the end of the day, when you are serving ads, when you are trying to train machine models to figure out who to serve the ads to, it is essentially you are training models using this data, which is violating users' privacy and so on. So it is a really important problem. Yeah. And so that's why we need all these different combination of solutions, in particular helping users to maintain better control of their data and their rights to data, and being able to get better benefit from the data.
I agree that AI is part of a customer of the data economy. Are there any other thoughts?
Yeah, I mean, I echo some of these sentiments, and I agree that I think free economy of the data is probably not going to solve this problem. I think it's potentially going to address some of the issues around incentives of obtaining data, but I think maybe this issue of like privacy or like data leakage, or like as you said, like people having their hands, different political parties maybe having their hands on the data of different people, which has been obtained through the free market, and using it for targeted ads, those problems remain, right? So even if you create a free economy, so that problem is not solved. It might be solving some of the other problems related to incentives.
Yeah. Okay. So we go on to the next question.
Hi, good morning. Carlos Oriol. I'm a student of Professor Song at UC Berkeley. I know we were listening in some of the questions about the regulation and the standardization of the algorithms themselves, but I'm looking more at the data itself under the assumption that if we have some ethical data in usage leading to the training of the model, then the AI itself will be ethical. And so is there currently a empirical measurement of how ethical a data set might be, how unbiased, and if so, how is that enforced and how is that regulated? Who is enforcing it? I'm thinking like a LEED certificate for buildings, but for data.
I know of a number of organizations that are providing consulting services on that regard to say, that I don't know that there's like an empirical metric of, how ethical a data set is, but it's one of those things where you kind of know it's not ethical when you see it, right? And there are so many examples of that in all these open source data sets that are, very clearly imbalanced, with regard to gender representation, or various kinds of marginalized communities not being present in the data sets. So I think it's a lot easier to see the effect rather than the data sets themselves, especially when you think about, this is the secret sauce. So big companies aren't going to publish necessarily metrics about their data set. But I do know that there are, small organizations and even the big 5 consultancies who are working really hard to qualitatively assess, some of the data sets to find out if there's anything obvious that jumps out. But it would be really interesting to try to standardize various measurements. It's not something I've seen yet.
And just a quick follow-up, when you look at the effects, it's obvious that there is some bias in place. Do you think at that point it's a little bit too late to then come back and try to fix the model itself? Should there be something in place beforehand?
Never too late, right? There's always the future. These algorithms are still in production making decisions. Even if they've made bad decisions in the past, they can make better ones in the future.
Thank you.
Okay, should we go to the question up the back?
Thank you. My name is Lu Yan Fang. I work as a Seattle startup healthcare called Prescriptive Health as a AI and the Data Chief AI and the Data Officer. Also, I want to mention the point, it's really Michel Dollar. He brought up the standardization. I started the effort called AI-HCCI. The intent is really how do we get to a place so we can test the methodology, we can measure the result, we can have a place to educate. Also, we can document how to use each AI solutions developed. So where I come from is I worked at IETF, the Internet Task Force, for about 18 years. That's how we get the internet running. There is a standard organization, not government run, it's engineering run. But you need to have a common agreement, every protocol, how to get interoperability, how to get consensus, and stamp into RFC. That's where I think at the point now, I can see a lot of companies come to say, we're number one, because this consulting company said we're number one, and we're number one, which is actually working, which is actually not working. If we have a place, can test them through and publicly publish the result without disclosing everybody's secret sauce, but the common data source used, how you manipulate can be your technology, but have the result and the document down how to use that, how the doctor can use that. If you use it wrong, then it just not serve the purpose. So that's something, I think it's time for the community to get together to have such an effort. It's not about government, it's not about total democracy, it's to have a common place to set the standard interoperability.
So the question is, can we achieve that? Is that roughly it?
I think it's an
Can we
advice.
achieve that if we make effort? It's going to be very hard because same as the internet, multiple parties, all different opinion, different agenda, but it's definitely achievable. I see some other countries already started such an effort. So if we can start within US and globally, eventually,
Does
start
anyone
from
have
small.
any thoughts on whether that's achievable or how?
Yeah, I just wanted to comment on that a little bit. I think, thank you for this comment. I think that's actually valuable advice. I think it's less of a question and, it's more of like guidance, which is really needed at this point, right? And I think, what she seems to be suggesting is also that let's not wait for the government to do something, all the big companies to come together and do something. Why not think of an academic consortium? And I think Professor Don has already given some examples of such for privacy. We can do that more broadly for other areas as well, so that we can lay out guidelines of, this is maybe how you want to use, like a doctor might want to use AI, and like here are the known issues, here is how we want to see the workflow going and so on. So I think, yeah, at least starting in the academic community might be a good first step. So thank you for that thought.
Thank you. And with the practitioner, like hospital doctors,
for sure.
right?
Yeah, thank you.
Does anyone else have a comment, or do I move on? Okay, wait, I think it's the person on this side next, thanks.
Hi, my name is Eddie Karot. I'm a retina surgeon here. So this might be a question for Himabindu with your work with high-risk data and applications. So doctors are pretty good at knowing when they don't know and asking for help, but models not necessarily. And it kind of actually baffles me how the FDA doesn't have a prerequisite for approval for like out-of-distribution detection, for example. How important do you think out-of-distribution detection is for high-risk models?
That's a great question. So yeah, I think it is definitely, if we are talking about out-of-distribution detection just generally as a problem when learning, let's say, medical models or like even detecting shifts that the data is undergoing as you run models on it. I think broadly the problems of data set shifts and thinking about how to detect them, monitor them, and also if needed sort of replace your models, I think those are very critical pieces. that are absolutely essential for healthcare. Like we collaborate with some of the hospitals in the Boston area, and that's one of the key things that they want to first focus on, right? So we can use all these models to help, let's say, a radiologist, to sort of like see or even do early detection of, for example, tumors. But we want to be able to see this when somehow there is a shift in the data, like whether it's caused by an external event, whether it's caused by some, diseases developing, like we saw in the past 2 years. That shift, detection of that shift, sort of like correcting it, and even like replacing models. I think that entire area is definitely very critical for high stakes things like in healthcare. Yeah.
And it's kind of crazy that the FDA doesn't require that. I mean, you have models that are diabetic retinopathy or not.
Yeah.
And if something else comes in or if there's a shift, they won't tell you.
Right. Yes, I think this kind of sort of monitoring, I guess that's the broader term that's sort of being used to refer to a lot of these detecting shifts, correcting for them, even checking if different groups are being treated well in terms of the model predictions and so on. I think more than like sort of even not just like sort of having some of these, as you said, the guidelines at the beginning stage, like, oh, when you deploy the model, this is what you should check for. We definitely need to have guidelines for monitoring stages through the life cycle of the models. 100% agree with you on that.
Maybe go to the person at the back. Hi.
Yeah. Hi. So this may be more of a philosophical question, but I'm not sure. Most likely this is for Liz, but others feel free to chime in. So I heard many of you talk about unintentional bias, and even though there's a sort of lack of clarity on that, my question today is more about intentional bias. What I do mean by that is the data in some cases that we get and as modelers choose to model is inherently biased because the data sources are biased. For example, in banks, when there are loan applications and some systems are deployed to automate that using ML. There is also a component of human-centered AI which seems to be missing in many of these applications that are intentionally biased. For example, before, if people's loan applications got rejected, they could still walk into the bank and have a chat with somebody and see what went wrong. How do you folks see addressing this problem when we move to fully automated pipelines, where people don't necessarily know the reasons why their loan got rejected, for example? And just to elucidate more, there are some marginalized groups by default whose loan applications are rejected. This is a known problem. And the explanation, the intuitive explanation for this is that, well, the stats do represent that the repayment in such marginalized groups is low. But moving from a sort of human interaction to ML-based interaction, as an end user, if I'm from a marginalized group, what do I expect to see differently? Does that mean just utilizing a sort of explainability laden AI approach, or does that mean human-centered AI approach, or something else?
Okay.
So just to add a thought.
Shall we get some answers now?
Yeah.
Liz, do you want to go first?
Sure, I'll be brief just to say that I think there's a lot in that question, and I do think that it is a very philosophical question in nature, and in some ways I can imagine an argument being crafted that says that failure to correct for historical bias is actually intentional discrimination, and I really like it. That's not something I've heard before. But just to say, maybe let's tackle the most important, or what I would maybe have pulled out as the most important thing is, like, are we ever going to get to a point where banked loans are completely automated decisions. I'm not sure, and I think that because there are laws that exist that require adverse action notices to be created for every application that comes in, that's a relatively recent law, and there are a bunch of different interpretations of it, but it does exist, and companies spend a lot of money trying to make sure that they can explain, at least in a bare minimum kind of way. So it's been really heartening to see some of the proposals for algorithmic laws have that same provision, and it's something I feel really strongly about too.
Got it. A short addendum to that would be, should we put some effort to model what we think is an ideal world, or is there some sort of framework, a guidance framework to even consider what would be the most ideal? In other words, should we model what exists, or should we model where we want to go to? That's the question.
I have a very strong preference there, but I bet we would all disagree, right? I think that it'd be pretty difficult from a corporate perspective to try to comply with the law to create a data set that's largely synthetic, representing something that is the world that we want to see. So I'm not sure. I don't know the answer.
Yeah, you probably should go on.
Hey, my name is Sid, and the question I have is related to algorithmic recourse in the landscapes of marketplaces that move very, very quickly. Think like advertising, where if you change the creative, that's information you're telling them and it gets better. Or if you're an Uber driver, telling to drive here, and that you'll make sure you get paid more. How do we think of the recourse information affecting the market dynamics, especially places where it's really quick? And how do you approach those landscapes? Because more and more things are becoming like marketplaces.
Yeah, no, that's a very, very great question. So I think currently I feel like if you're asking about are we ready to do that, right? So with existing approaches and so on, I would be a little bit cautious because I think this is a fairly, as I was discussing, it's a fairly new field, and I think there are still people are kind of figuring out that here are the pitfalls, here are the pitfalls, and here is how we should sort of think about fixing them and so on. But I think as we sort of go forward, I definitely was also recently talking to one of my colleagues about this exact situation where, so far we are thinking of recourse in terms of there is a big entity, they're sort of giving like a point-to-point recourse, right? So the bank says something or the insurance company says something. That's the kind of settings we are trying to design algorithms for, which makes sense, that's like the first step. But I think going forward, as you said, if we were to kind of scale this to marketplaces where there are multiple actors, a user may want to know why their Uber ride was not approved or turned down, right? Or same thing, as you said, the driver may want to know why he's not getting paid more for this trip and what he can do in order to change that. And if recourse is even a good thing in those settings, I think a question that we should also ask before we get there. I think there is a lot of potential and opportunities there. But I think the way the existing literature is, I would say maybe we need to be a little bit more cautious for a few more years before we sort of try to scale this up to marketplaces. But great idea. Thank you.
Okay, let's get a question in from Fei-Fei.
I've been just so intrigued by all the audience questions. Excellent questions. I want to get to differential privacy a little bit. Start with the more technical question, but really thinking about the future and the application, especially queuing the next panel after our keynote is on foundation model and large models. That there's a tension now, right? We've been excited by differential privacy computing for a while, but that complexity and computational cost is really high. In the meantime, modern AI is moving to these huge models driven by huge amount of data. We'll hear more of the foundation models. So on the technical side, Don and Om, how do you see this progress of privacy computing catching up with these large models and segue into the more path to application? Are we going to see practical applications of privacy computing on large models soon, or this is still, more or less only showing up in URIPs and ICML papers?
Sure. So that's a great question that researchers have been constantly working towards improvements. So I personally think of privacy as an enabler. So for example, today I talked about 2 results which by incorporating privacy, we were able to improve what was existing beforehand. So there was a model that was trained on server logs, but when we trained with a private technique, we could train on device. And that actually helped improve utility of the resulting model. With advancements of new techniques, we can even make further improvements on top of that. So there are various areas where privacy can actually help improve the state of the art instead of thinking of it as a trade-off. Like you can get more insights, you can guarantee less memorization, and like overall the utility can be better off with privacy than without.
But there's a cost, right?
There is, like, there are trade-offs in, for example, compute. So if you can design your systems according to those trade-offs, there can be like net gains in other domains.
But the companies are racing off to large models, where they're racing to increase computational resource for these large models, and how does privacy computing come in?
And also, right, and also privacy actually is a really multifaceted concept. And even on the differential privacy side, actually, even if the model is differentially private, it has been shown that it can suffer from other types of privacy attacks and so on. So on one hand, I think, right, it's helpful also for the audience to understand the privacy. Right now, we don't have a silver bullet. Even putting the computation resource aside, actually, privacy is so complex that we don't have a good solution. And then on the other hand, I think certainly, depending on the different types of privacy technologies, yes, the computation resource is always going to be an issue, but then more technologies can help there as well. As Om mentioned, in certain cases, it helps improve the utility, and also there actually has been a growing industry in developing various hardware accelerations for different types of privacy technologies and so on. So for example, I would love to see in the future, like GPUs and TPUs, they have secure enclaves in there, so you can really do secure computing. As you train these large models, essentially you get a certain type of security privacy for free. And then also on the differential privacy side, there's work, including our own exploration also, in terms of how you can get, in certain cases, you can get differential privacy or this kind of privacy guarantees for free. So when you do the training, when you do the training data set in a certain way, that you can get some of these privacy guarantees for
That's
free.
an excellent question for this afternoon's keynote speaker from NVIDIA, privacy hardware. So we'll take a note of that.
And I'm afraid I think we have to wrap up this session now, so sorry for the people whose questions didn't get asked. But if you'd like to follow up with them, if you wanted to email HAI, we can make sure the questions get to the speakers.
I'd like now to welcome Kavita Bala onto stage. Kavita is the Dean of Cornell's M. Bowers College of Computing and Information Science, which houses the departments of computer science, information science, and statistics and data science. Kavita received her master and PhD degree from MIT and her bachelor degree from IIT Bombay. She was a postdoc researcher at the Program of Computer Graphics. Kavita co-founded GrokStyle, a visual recognition AI company, which drew IKEA as a client and was acquired by Facebook in 2019. Before becoming dean, Kavita served as the chair of the computer science department at Cornell. Welcome, Kavita.
Thank you. Thank you, Fei-Fei, and thank you for being here. It's a pleasure to have this opportunity to talk to you. Today I'm going to talk about work in my group that I've been working on for a couple of decades now, but primarily this last few years is what I'm going to focus on visual appearance and understanding, starting all the way at micron resolution to planet scale and world scale. So before I start, I'm just going to give you sort of an inspirational example. I don't endorse this particular movie but necessarily, but this movie, Anon, had a very interesting visual interface of how a protagonist was interacting with the world. So as this person walked around, the real world had overlays of visual information that was interesting to him. He happened to be a car aficionado, so it showed him information about this particular car he's seeing, so that as he walks around, he gets enriched from the experience of seeing things in the real world. And to be able to tell you what a car is just by a photograph of it, you need the field of computer vision's visual understanding research to drive that kind of technology. He walks further towards the back, and actually, as you get closer to these models, you realize they're not real models, even though they look very realistic. So their appearance is such that he's been showing different things that he might want to purchase. And to do that in a good way, you'd need research on realistic appearance. And then in a completely new, reimagined universe of window shopping, as he walks up to a window down the street, he sees all of these items. His technology, his interface gives him all the information of what he's seeing, and he can just hold it right up and decide right then and there, without touching anything in the real world, whether he wants to buy it. So I show this, and to achieve this, you need a real-world photograph. You need to be able to do what is called inverse graphics, is figure out all the material shape properties of this object, so that then you can imagine it virtually, and he can interact with it. So I show these examples to give you an illustration of the kinds of technologies we are now building. You're hearing a lot about augmented reality, mixed reality worlds. These are the kinds of technologies that drive it. Now, there are many questions that come up if we were to live in this world. That movie particularly looks at, for example, the security aspects of it, which was discussed at length this morning. I'm going to focus on the visual technologies that drive it, which has been the body of research that I have worked on. So in the area of research where you start off with a virtual model and make it look so real that you can't tell the difference between real and virtual, that's the field of computer graphics, rendering in computer graphics, actually, in the area of realistic appearance. And conversely, there's the other direction. You take a photograph of something and you understand what it is. So you understand all of its properties, but then you can build on that understanding to understand maybe bigger properties of the scene and the world around you. So in today's talk, I'm going to talk about 3 areas of research that are just depicted here. Physics-based visual appearance models, so models that really capture and accurately the physics of the world of objects interacting with light. Inverse graphics, as I said, building models of the world. And then at a very large scale, taking all of these technologies that we have and trying to do visual discovery, so using visual recognition, but at world scale to understand our world around us. And the first 2 are pretty different from the second, so there'll be a pretty big logical break in the thinking in the talk, but I hope you'll bear with me. All right, so let's start off with physics-based graphics. In 1988, this is the famous Cornell box that introduced what was basically a visual Turing test. One of these is a photograph of a real box, and one of this was a rendering at that time of a virtual rendering of a virtual scene. And the concept that was introduced is we shouldn't be able to distinguish between these 2. And just for your edification, real on the left, virtual on the right. This has spurred decades of research as people have tried to meet this goal of the virtual Turing test of not being able to distinguish virtual from real. Of course, the world is not made of materials as simple as this. In the real world, there's a lot more complexity. So we have fabrics shown here, as you saw in that model there, skin, rocks, and other trees, leaves, all of this stuff, food, and all kinds of biological matter in the real world. And you're continuously interacting with this world, and you're making judgments about what you're seeing and whether they look realistic. So dealing with this complex materials has been a big challenge in the field. And as I said, this is one of the big areas of research I've focused on for several years. So I'm going to talk about one set of projects around properly capturing the appearance of fabrics and cloth. And the question that we asked ourselves is, actually, look at these 2 pictures. On the left, you see velvet. You as a human being can immediately recognize that. On the right is some sort of a shiny silk-like material. So why can you recognize that instantly? What makes velvet look like velvet, and what makes silk look different from velvet and look like silk? Well, it turns out the answer lies in the structure of these materials. The cloth and fabric are not just surfaces. They actually have structure to them. And if you capture that structure, you capture their essence of their visual appearance. So what we did in this original set of projects is we looked at micro CT scans of these materials. So here's a swatch of velvet and a penny associated with it, just to give you a sense of the scale. And in the middle are the CT scans that we will show slices of. On the right, you'll see the structure of the velvet, which will have this characteristic appearance. Velvet is a very fuzzy material, so there's a substrate and there are yarns that come out of it. And you can see that on the right there in the 3D visualization of the data for velvet. So that's velvet. Conversely, silk is very different. It's very tightly interwoven warp and weft yarns put into a particular pattern. And in fact, because it's so tightly woven, that gives it the classic shiny appearance that silk is very famous for. So what we found, to our surprise, is once you capture the structure with these volumetric models that you get from CT scans, you're actually almost there in getting a complete appearance model for these very complex materials. And just to give you an idea, CT scans nowadays, they're kind of like Kinko's. You can send a sample and $200, and half a day later, you can get all of your data that represents them. So it's a really new modality that's very exciting. Once you have the structure, it turns out a small amount of extra information that shows the optical properties, for example, the color, et cetera, is enough to give you a complete model, so that we were then able to produce the most realistic models to date of these kinds of fabrics. So I'll give you a little flavor of how we use this information, these volume information and the photographs that go with it. So when you have these volumes that come from the CT scan, there's some density to them, and there's sort of an orientation to all of the way the fibers are in those volumes. And if you capture that, essentially you're capturing this arrangement, the structure, so to speak, of these materials. And meanwhile, from the photographs, you're getting the base color, so to speak, the albedo of the material, and some idea of its shininess, the spread of light when it goes through that volume. And together, that gives you that model. I'll show you now examples of this. You can see the volumes on the left and the appearance that you can get. These are the highest accuracy that you can get of these kinds of models to date. Partly, and they capture exactly a very characteristic appearance. The silk looks shiny as it's expected, and the asperity, the velvet has what is called asperity scattering, the very characteristic highlights that you get on the rim of the model. And at that point, this moved us forward quite a bit. Since then, we've done a whole bunch of research on actually generalizing these models, et cetera, so that we can then use them. And what's the ultimate goal? What to use them for what? Might be a good question to ask. And the answer is really that we want to make these kinds of tools available so that designers, industrial designers, textile designers can do digital prototyping such that they can predict the appearance of a real woven fabric. So in an industrial loom, you have actual yarns on spools, and they're fed a weave pattern, and then an industrial loom will produce a fabric like a picture there shown on the right. And sort of in our modern day visual Turing test, we want to create essentially an entirely digital pipeline that achieves the same effect. Using this combination of CT scans and photographs, et cetera, we should be able to produce a virtual rendering that matches reality so that a designer can make important decisions without having to actually build a fabric ever or fabricate the fabric ever, and can make important decisions with fast turnarounds, low trial and error to get to the outcomes they need. So that was sort of one body of work. In fact, we built further on that, and these volume models are pretty heavy and hard to work with. So we actually created lower dimensional models with 22 parameters that are more intuitive, that represent the structure of these materials. And once you have them, you have a lot of power as a designer. Now, I'll just say quickly, there is a challenge here. How you find these parameters is a difficult problem, and that leads to the inverse graphics that I'll talk about shortly. But given these models then, and here you can see two pictures of yarns. On the left of each picture is a photograph of the yarn, and on the right is our virtual fit. It's a complete virtual rendering of that yarn that we have fit to it. And now you have textile designers have a lot of power. They can take these yarns, and without actually manufacturing a completely different kind of a yarn, they can go and they can look at what would happen if I produced a new kind of a physical yarn that had a different twist parameter. How would that look? And if I like how that looks, maybe that's the direction I should go. And you can do this all without any physical trial and error if you have good predictive models to produce appearance. So I wanted to just motivate this area of research on physics-based visual appearance models, because we'll come to how does that fit with learning very shortly. But digital prototyping and industrial design, all of the techniques, all of the areas that really rely on this kind of virtual techniques has a big financial impact on them. They need these kinds of predictive models so that they know what they're getting and they can rely on it to make important decisions that change the outcome of how their design process operates. So the next area I'm going to talk about is the area of inverse graphics. So let's say we have all of these models. The question is, how do you actually fit to those models, so to speak? And that's been a big area of research in computer graphics for a long time. It's recently received a lot of interest because of the possibility of adding learning to it, which has enabled new kinds of capabilities in this space. So here's what you're trying to do. If I go to that watch example, you're taking a photograph of something in the real world and trying to create a fully virtual representation of a shape, its material, and maybe even the lighting that contributed to its appearance so that you understand what you're seeing. Before I get into sort of how we actually would go that, I just want to go into that area. I just want to give you a sense of why it's difficult. So materials like metals, for example, when light hits them, light bounces off them, and they're still difficult to simulate because you have to capture light bouncing around a room like this, hitting all the surfaces in the scene. That's a big problem of global illumination. But there are other materials, skin, food, and all of the things that actually a big part of the world that we're living in right now, have this extra complexity that light doesn't just bounce off the surface, it goes in and interacts with the surface. It's called subsurface scattering. It scatters within the material, and that fundamentally changes the appearance of these materials. And you really want to capture that correctly, but it's quite complex to simulate and represent. And just so you know, you use judgments on subsurface scattering all the time. If you look at a piece of sushi and you're deciding, do I really want to eat this? You're making a judgment on its freshness entirely based on how that appearance is coming and presenting itself to you. So I'll give a hint, just a flavor of different techniques that we're trying. This is a very exciting area right now with a lot of interest in it, partly because of the development of a new area of research with great researchers across the community working on differentiable graphics. And I'll talk briefly about that. But let's say we want to solve the problem of inverse graphics. The problem we're trying to solve is really take a picture of something. Can I figure out what the material properties are of this object I'm seeing? Right? In an ideal universe, you'll have some sort of a learned representation there. So you take the picture and you can spit out the material parameters. In this case, those three correspond to various scattering parameters. How far does light travel in a medium? How much does it spread out when it scatters? What's the albedo of the material, et cetera. So I want to create this kind of a pipeline, and the reason there's promise to do that now is we have physically based renderers that are simulating the entire physics of light that work pretty well. So you can imagine combining them with a learned representation, and if you have this end-to-end pipeline, then if you match that output image and that input image, and you get them to match, your loss is minimized, then you're able to hopefully recover the material properties that are sitting there in that middle of the slide. And to do that effectively, you're effectively combining learning and physics, and you're inverting sort of the physical rendering process in the world and trying to come up with the inverse parameters. This is a very exciting space. As I said, recovering shapes and materials is hard. I will say to make it work, you need that rendering engine R to be differentiable, and a lot of recent research has focused on that. So I'll now give you just a flavor of some of the techniques that are out there that use this. If you have a differentiable renderer, then, for example, you can take lots of photographs of the object, this particular fish, for example, and you can have different representations for the shape, material, and lighting and recover them using this combination of learning and physics in this pipeline. So you can represent shape with sign distance functions in this case, the materials with diffuse and specular representations that are learned, and the lighting with spherical harmonics, spherical Gaussian, and you put that together and you have an end-to-end representation for simple objects. Once you have this, you can then relight the object. So just like the guy was holding up his watch and was able to see it, you can potentially try out different settings, try out different metals that you want to make of that material or different materials of this fish and see how it would look. So you get that power of design, intuitive design, through these kinds of mechanisms. To make this work, and I'll just give a brief hint of the kinds of problems you deal with. As I said, we're one of many researchers who are really pushing the state of the art in this space right now. You need to have a differentiable rendering pipeline, and what I mean by that is you need to be able to differentiate your loss with respect to the whatever properties you're recovering. So for example, in the case of material properties, you need to differentiate with respect to that. And I won't get into the details here, but here's an example where we're recovering material and geometry, and the details are in the paper, but we're able to actually characterize this differentiable, the differentiable rendering aspect using the chain rule, and are able to compute it just using some simple sampling on the boundary of the surface. And that gives us the information we need. Now we can build a pipeline like this one, let me see here, where you have a cell phone camera, you can take a few images of an object and just walk around it very easily and create, starting with the coarse initialization, this extremely fine detail model just with a cell phone and at-home equipment, essentially. And here are examples of now taking those kinds of models and then applying it in completely different settings, augmented reality, virtual reality apps, et cetera. So that's all been looking at the problem of surface-based models. We were very inspired by looking, I told you subsurface scattering is a very important phenomenon in in the world because of the skin and the food and all of the things that we have. How could we capture that? So before I get you too excited, this is actually a photograph of real food created by an artist, and I give them a lot of credit, and served as an inspiration for us for this project. So these are it's called cubes, and they carefully, meticulously created 2.5 centimeter cubed cubes of 98 different food items. And just to give you a sense of the complexity of the world we live in, these are each of the beautiful cubes. They aligned it together, put it in a line, and took a photograph of it. So this is not rendered, but we were inspired by this to try to create models of this kind of complexity of food. And as I said, the thing to remember is because they have very complex subsurface structure, you have to capture the appearance of that. So to appear, it's going to appear at SIGGRAPH this year. We looked at, again, the differentiable rendering, and this one is quite involved, so I'll wait for you can read it in the paper when we release it shortly. But we actually developed a whole differentiable rendering pipeline with subsurface scattering as the core material property that we are recovering. And once you do that, again, you have a pipeline where you can take some photographs of this object, and we've created these renderings of kiwi and dragon fruit for the first time. There's still a long way to go. The quality isn't quite there. You can tell that this is a virtual model, but it starts to get the essence of what these materials are. So all of this begs the question, why are we doing all of this detailed modeling when you can just use large data and learn this, right? That's a question, and we're seeing amazing work coming out. For example, DALL-E 2 the paper was just recently released, and it's amazing the kinds of things that they can do with a language-based model to edit the world and to change it so that you can visualize the kinds of appearance you can get, both in a stylistic manner, as you see on the top, but in a realistic manner if you see down, right? How do you get that? So what is the relation between these two? So I'll tell you, this is sort of based on just a couple of decades in this business. I think combining learning and physics is really exciting, and we are at that time when we think we can do that. And the reason you do want the physics, though, is because of this need to do predictive rendering. So here's an architectural visualization of a scene that you would like to visualize before you actually build the scene so that you understand how it looks. And I'll give you sort of the motivations to summarize all the arguments I've made up till now is, when we were looking at the fabrics, we didn't even understand why they looked the way they did. So understanding the visual phenomena through the physics is actually an important part of how we can explain why velvet looks like velvet and it's different from silk. But then additionally, the key goal here is not only to produce something plausible, though that's an important goal in its own right. There are many creative tools that can produce plausible output, like you can see with DALL-E. And that is a very exciting domain for lots of people to explore and for citizen artists to design. But a lot of our work that we do sits actually on the predictive side, where we want to correctly predict how appearance will look before we build an item or build a building that's hundreds of millions of dollars. We really do want to make sure we've simulated it properly to understand how it might play out. And that brings to an interesting problem that actually we identified in our field. It used to be the case that we were told artists really just want artistic control and they don't care about the physics. That was the belief till the 90s, when we finally figured out how to get the physics to work properly so that you can use it in tools. And then it turns out artists actually love having the physics. And the reason is because artists want control on the artistic process. They don't actually want to waste their time simulating physics, which they hope nature gives for free for them. So once you realize that, what you really arrive at this place is you want to have this combination of control along with physics and designing tools that have that, not just a black box that's learned, but one that has the physics in it and can combine the two of them. That's, I think, where there's a lot of interesting work to do. So we don't know yet how to do it in our community, and there's a lot of it's just being developed as we go, but I'm excited to see what the next 2 years bring along that space. All right. So I've talked about the first two parts of the talk. I'm now going to spend, as I said, switch gears pretty substantially and go in a different direction, which is looking at this question of if you have all of these images and you can understand what's in them, what can I do with that knowledge? And I'll talk briefly about a world-scale visual discovery, which is an area of research we're working on in this space. So remember the time when that guy walked down the street and he looked at these watches and his interface told him exactly what he's seeing. That problem is called fine-grained object recognition. It's a big area of research in computer vision, and it shows up in many places, not only in product recognition, but also, for example, chandeliers in real estate, for example, in this indoor house scene, or understanding whether an influencer is carrying a particular item of fashion. All of these require you to look at it and say, this person is carrying X. And it's not X like X is a handbag. That all of us can do. It's X as in here's a particular brand of handbag, which most of us can't do. At least I can't. I don't have that level of knowledge at all. So essentially, we have the promise of providing expert level, and maybe even more than just any one expert level of knowledge through visual recognition. And that's a very exciting space to be in. So we worked on some of the space with my student, Sean Bell. We actually worked on fine-grained object recognition, where we would recognize an item like this and say this is not only a fire pit, which I don't know if you would have recognized just by looking at it, but it is this particular kind of fire pit and where you could get it and who the artist is who's created it. And as Fei-Fei mentioned, we rolled this out with IKEA in their augmented reality app. So this is where all of those earlier visions of that interface are starting to become true, where we'll have visual recognition and we'll have virtual renderings all intermixed together in augmented reality apps. That's our hope. The work that we did here is actually now part of Meta's shopping AI, GrokNet, and their tagline is to make every image shoppable. So the work is having an impact now, but separately in my group, we've been looking at a variation on that problem, not to make every image shoppable per se, but to make every image understandable. So what do I mean by that? So first, before I do that, let me just, of course, you all know this, that's why you're here at this conference. But we are, of course, collecting information at an unprecedented scale at this time, visual information, whether it's photographs or videos, and now satellite images. So it used to be that we had about 50-odd satellite images a couple of decades ago. There are 1,500 now, and they're uploading 100 terabytes of data per day. And in fact, that's a direction I'm very excited about, understanding images at satellite scale so that we can understand how our world is changing and see what's going on across the world. So we want to gain, and if all of these images, it sure seems like we should be able to understand more than what any one human being can understand with their ideas or their worldview. And so the hope is, can we gain insight at planet scale by looking at all of these images? So we started working on this field, and the field is very broad. I'll talk about one slice of work that we've been working in this space, but the idea of doing world-scale visual discovery and understanding. So we can ask questions like, how do we live? What do we wear? What do we eat? And how do things change over time? How is the planet changing over time? I will say that in this work, and done with Utkarsh, Kevin, Noah, Bharat, we started to work actually particularly with cultural anthropologists and with sociologists, because they are fascinated by these kinds of questions, except they don't have the tools to really explore them. So when you think about what a cultural anthropologist or a sociologist does in their field studies, they'll go to some locale of the world where they have a hypothesis of what's going on in that place. They do a bunch of interviews, and then they try to then understand, build up a theory or build up a cultural understanding of that space. And so when we reached out to them, they were incredibly excited to have a tool that they can use to maybe expose the kinds of questions that they could ask, that they would then follow up with very rigorous field work. They weren't planning to ever give that up. That's an important part of informing these outcomes. But it'll help them actually reach, seed hypotheses as they go along. So the particular one we worked with, a cultural anthropologist who was very interested in understanding how clothing changes across the world. And actually, this relates to something I was very intrigued, something Liz said in the earlier panel today. So why do people dress differently in different parts of the world? Well, it turns out weather plays a big role. Most of you are wearing clothes that you don't normally wear in summer here because it's a little chillier here than it is normally in California. The activity or the occasion demands a certain kind of clothing, whether it's you're going to a party or you're going to a sporting event. Culture changes certainly what you wear. Different parts of the world dress very differently. And of course, there's fashion trends. There's actually fashion influencers, et cetera, who change what you decide to wear, and that plays a role. So we decided to study all of this within the context of these projects, where we got a set of images for about 8 million images of people from different parts of the world. And we developed a simple recognition algorithm to recognize what clothing they wear. So it's just simple 12 attributes. But we wanted to understand what can we glean from this very simple analysis. And the main point is, let's assume recognition works. What further insight can I get about the world that I live in? So we looked at, if you look at the classifier and then you just look at the embedding of the images that you get using that simple mechanism, you can start seeing some structure in the clothing that we've analyzed through this process. And I'm assuming the projector is not washed out, but you can see on the top right, there's sort of greenish kind of clothing, and the bottom left, there's a reddish kind of clothing. So there seems to be some structure to what we've learned of the clothing that goes across the world. And in fact, we characterize these using a mechanism just to seed some number of style clusters and try to understand what these style clusters are. So we show here sort of these top 4 style clusters that we get out of this simple analysis. And they show interesting things. So for starters, you can see each cluster actually shows a very distinctive type of clothing. But more importantly, we can actually start to understand where the data comes from. And you can look at the cities on the x-axis and the time of the year that you're collecting on the y-axis. And now you start actually seeing a lot of structure. For example, this very distinctive top row is called all the women there are wearing, most of the women there, there's some noise in the data, are wearing this distinctive headgear called the gele, and that comes from Lagos. Here in the middle 2 rows, you see the hijab, which is worn extensively in Cairo and Jakarta. Other places of the world too, but those particularly plays a heavy presence. And down here is something that's kind of ubiquitous across the world. It's sort of cold weather. You're seeing essentially winter in the northern hemisphere and also the southern hemisphere at the other months. And you're seeing people dressing up for cold weather across the world. So just by analyzing the data, we started to understand a little bit about different unique aspects of culture in different parts of the world. And so that led us to the next set of next project that we did in the space, is trying to understand how things change over time. Can we detect temporal trends and events by analyzing this data? Again, we take these recognition, and then we actually fit simple curves to understand whether there are weather-related behaviors shown here in the red, or there's something more exciting going on beyond just weather. So here's an analysis of some of the data we get, and if I look, I think at the middle one, you see, I think that's Delhi, and you see, sure enough, in winter, people wear more layers, and in summer, they tend to be more lightly dressed. That makes sense, so that forms our baseline. But then what's interesting is out pops from this very rich data automatically events that don't match what you'd expect to happen in a particular place just based on predictions of weather. So now we start to find outlier events like this one. So this is Chicago and people wearing green, and there are spikes at one specific time of the year every year in March. And what is it? It turns out, for those of you who know, people are nodding, it's St. Patrick's Day over in Chicago. Everybody wears green. It's a very important cultural event. So we have fully automatically found something that is very important to people in Chicago that you might not know if you're not a native of Chicago. We found another very interesting example. We actually didn't know about this at all, but out of the data popped this political rally that was called Catalan Way, where everybody wore yellow shirts and formed actually a human chain. This was to protest. This was over in Spain. And again, the data just informed us about a cultural and political event that we were completely unaware of, and that we learned about the importance of an event to the local population. In fact, going further, we did all kinds of analysis about worldwide cultural events. So we can see the Stanley Cup, we can see various sporting events that pop up, for example, the Melbourne Cup over here in Australia. We identify something that most of you probably know is important, but the data just pops it right out. Fashion Week in Paris pops out here. New Year's is important in certain parts of the world. Father's Day is important in certain parts of the world. All of this just gets exposed, and we as we were computer scientists, but working with the cultural anthropologists, felt we were learning about the world through understanding these cultural variety that exists in the world around us. For those of you who know, in Calcutta, Durga Puja pops out, which makes total sense for those who are local and is probably completely alien to people who don't know what it is. So it's a wonderful way to learn about the world around us. So with that, I know we have to get to the end. So I just want to wrap up and just talk about these very two different worlds, but we live in an exciting time where we can bring learning, large data, and physics together to create sort of these new kinds of interfaces with the visual world that didn't exist before. So I've talked about these 3 projects that we worked on in my group, but I'm really excited, as I said, going forward, looking at very large-scale visual discovery, learning visual understanding, and going all the way from micron resolution understanding or what makes things look the way they do, to planet scale, satellite scale. How is the world changing, and well, what are we doing to help it? So we live at I tell my students, this is the best time to be doing research in this space. We're making science fiction a reality. But of course, with great power comes great responsibility. And that's one of the goals of this forum, is to work with a very broad range of disciplinary experts to understand how AI can be used to improve our understanding of the planet, culture, and more. All right, thank you. And thank you. And
you can have a seat.
Thanks.
In the middle.
And I should say, I do want to thank all my wonderful collaborators. The green are the students who did all the work. They're not students anymore, but they were. And the blue are my long-term collaborators. And with that, I think we can go.
Thank you, Kavita. We have a few minutes for questions. Audience, as usual, there are microphones on the aisles, and I'll be moderating these questions. All right. Well, I'm just going to start by thank you. That was such a fascinating talk. I work in computer vision, and Kavita, you're one of the few people whose research has really traversed both computer vision and computer graphics. That was just fascinating. If we're not having audience questions yet, I want to start with a couple of questions to. There's a lot of technical questions I want to ask, but let's just broaden up, because for someone like you who's being a leader, technologist leader in the field of computer vision, computer graphics, and now a leader in higher education, I think there's a lot of things I want to explore in this very short amount of time, and waiting for audience to chime in. Let me start with something that was already mentioned in the previous panel. It's the issue of bias. You work a lot with physical world, materials, objects. Is there a sense that as long as we're dealing with physical world, we're not worried about bias? Because what kind of bias is there in materials?
Oh, that's a good question. I must admit that bias is not so explicit in that context, but there is an implicit one. So and I didn't talk about that work today, but we had this project on materials in the wild, and we were trying to understand materials in different parts of the world. And of course, it turns out that in richer countries, there are richer materials. And so, in fact, if you only restrict yourself to the kinds of pictures that you get, and initially we were looking at real estate pictures within the US, you form a very different model of the world and the materials that people use. There are mud huts with mud stoves that are, and once you expand to actually include images that include India, Africa, all of those countries that have a very different profile in how they approach, in fact, the material world, you actually expand the kinds of materials you recognize and the kinds that you should develop representations for. So we were actually, we had done this work 6-7 years ago when the idea of bias was just starting to ramp up and the recognition of that. And we also felt that, yes, we were seeing this very clearly. Real world life is very different in different parts of the world. The clothes they wear, the kinds of materials you use, and depicting them correctly and accurately requires that understanding of the bias and how to undo that and really have a broader understanding.
And how do you convince your students that they should care?
I was fortunate to have students who did care, perhaps. So but there's a bigger question, actually. That's a great point about just generally in education, in the domain that we are in universities. You do need to make students care. And I will say, so I'm at Cornell, and we have this computing and information science. As Fei-Fei mentioned, we have 3 different departments. And early on, this is 20 years ago, we actually created a very interdisciplinary department that had people with computer science, many of them degrees, but worked with sociologists, science and technology studies, the law school, et cetera, and very interdisciplinary department. And if you don't do that, and at that time, people just thought technology is technology. We'll toss it over the transom and somebody else will deal with the societal implications. This decade has proven that is completely wrong, and venues like this are starting to take it head on. How do we address this? Companies are also, to a certain extent, they have different motivations, are also tackling it. But we need to bring it to the education, into all the courses we teach. So we teach now an ethics course at Cornell. I know Stanford has an exciting one. What we found is our students did not have the language to even understand how to grapple with the ethical questions that they were going to have to do as they're writing their software in whatever job they were doing. So we feel it's important not to give them answers because we don't know the answers, but to give them the language to ask the right questions so that when they're grappling with them, they're at least able to know how to look at the question and maybe where they should go to get help. So that's one piece. I think we have to change fundamentally education in the computing and information technology world to hand in hand understand societal implications in all the technology that we're doing.
Thank you. That's music to my ears, and thank you for leading that at Cornell. It's so important. We do have an audience question. Let's introduce yourself and be brief with the question.
Yes, my name's Neelam Ram. I'm in the Communication and Psychology Department here at Stanford. Thank you very much for the very inspiring and fast-moving talk. I'm curious about how is it that you disaggregate the context of the specific object which you are looking at. So you had some variables that you brought in, such as geographic location or the temporal trends. Is there a way that we can identify the scale at which we should be looking for these context variables, the background lighting, the room, et cetera? And what happens if we get it wrong?
Well, I think we have to be very cognizant, and this is actually how do you avoid getting it wrong. I'll say we always work with domain experts to help us to stay honest. I think so I'll answer that second question first. But it is valuable to think about the context, but you have to balance that also with the privacy of the amount of information you're extracting from a photograph somebody chose to share. So I'll say in the work that we do, we don't use the person's information at all, right? We only look at, for example, in that particular project, the clothing that they have. And all of us know, at least all of us have Zoom backgrounds where we actively, the reason we include a Zoom background is because we don't want to reveal anything about our context to the rest of the people who are there. So there is a rich source of information there. We have to be careful about how we include that. I'll say in all of these deductions you make, when in this case we are trying to understand cultural differences across the world and how people dress, if you have a person from that who's an expert, they inform you about, well, this thing that you think is an effect is not an effect. It's actually bias in the data because that country, and a perfect example is young people post pictures of themselves and old people don't post as many pictures of themselves, right? The whole selfie thing is more a generational thing of a particular kind of generation. So you miss an entire quantity of data for a particular slice of the population. If you have an expert in the field, they help you with that and they help you find the right resources to augment for that.
That's a great question.
Just one another quick follow-up is, when you embed the physics model inside of the learning process, the pipeline,
yeah.
How important is it that that becomes interpretable? Or is it okay if we put the wrong physics model inside, and what are the consequences?
I'm a physics diehard, so you should never put the wrong physics model in. Physics is what nature gave us, and you should put the right model. But the whole point of that is that we want interpretable knobs, right? And in that case, those interpretable knobs are the material properties of the object that you're recovering. There are other kinds of knobs. So in the graphics community, there's a lot of interest over time has been around perceptual knobs. So you don't necessarily change the actual material properties. You change something that affects your percept of the material. Is it shiny or is it not? So would we get those knobs? That would be fine too. But the interpretability of it is all pretty critical for that. Otherwise, you're just monkeying around with random knobs and don't know where you land. Now that I have a very specific worldview on that, as you probably realized, and I know it'll be good to talk to more people who have a different worldview.
Physics is what nature gives us. We shouldn't waste this. Okay, so you mentioned something really fascinating, visual Turing test. And you showed this very cute example of Cornell box. That was what, 80s, 90s?
88. 80s, yeah, and it's still there in a...
Fast forward almost 4 decades, 3.5 decades, we've gone from Cornell box to a deep fake video of Zelensky surrendering in the war. Comment on that. And especially as an educator.
Yeah, again, this is, with great power comes great responsibility. This is a power we have now unleashed, and we have to think about how to use it responsibly. So when I think about the kinds of we will need to develop technologies to be able to tell when images are doctored. And this has been a problem that has existed for a long time. In fact, Stalin famously, since we're talking about Russia and Ukraine, Stalin famously would do a lot with image doctoring in those days. We weren't just that easily fooled. So there are multiple pieces to it. We need to educate our audience, for starters. We need to educate, of course, our students, but we need to educate the world, actually, to recognize I don't just believe everything I see. In the old days, would you believe, would you trust your lying eyes, right? That was the axiom. That's not what we can use right now. We have to say, you can't trust your lying eyes. It's possible that somebody doctored this image. So we need to develop technologies to really be able to detect that. And there is a lot of work. I know that this has been ramping up in different companies. So once we have those technologies, once we have a more educated populace about the dangers of that, you will still have a whole bunch of people who want to believe what they want to believe. That is actually a reality of our time too. There's a longer education process related to making people understand that it is important that there is this idea of trying to get to a common, sharing across differences, rather than just sitting in your corner believing what you want to believe.
Thank you. That's so important. I mentioned earlier, Kavita, that you are one of our nation's higher education leaders in computing as a dean of Cornell's, a very important school. I want to talk about this because you also have a unique view, having collaborated with the industry. In the world of computing, and of course driven by AI to a large extent, there's a huge just gravitational pull to industry, our talents, the computational resource, the data that's available. What is the role of higher education in this moment where there's tension?
So again, I have a strong view. We are here to keep...
We want your strong view.
We are here to keep everybody honest. That's what you can do in a university, that at the end of the day, as long as you are reporting to somebody with a financial obligation to that person, as a lot of companies with the best of good intentions, they have a very different objective function they're optimizing for. Universities aim to, pursue the truth and do it, without bias. And we are here to help, and we have to work with these. I will say, though, I do worry, right? We get starved out of resources, whether it's compute resources. We don't have access to the large scale of data that's available. We have to think about ways in which that kind of, or approximations of that, are available across the board to the universities and to the academic communities so that we can help with the research. Now, it's a very difficult time we're in, and I hope that we can maintain that strong voice while we work with, and I know there are many industrial partners here who will reach out to the academic partners so that we can actually partner together to keep the world honest.
Keep us honest. That's a great message. We've got one chance for audience question, and then we have to wrap up.
Thank you so much for the talk. I was on the edge of my seat wishing I was in grad school again. That was really a lot of fun. As you've been incorporating models of reality into a variety of machine learning contexts, I think there's a lot of lessons that you could potentially learn. So large language models, for example, just run happily over large amounts of data, but are often unconstrained by reality. As you've been putting these models, embedding them in, there's lessons you might be learning like computational costs. Because if you really want a perfectly high fidelity physics model, I mean, you need to go quantum, I mean, you need to go crazy, and that's just way too computationally expensive. So when you're making those decisions about what models of reality include, there's constraints that you have to deal with, as well as understanding how to make these two worlds work together. I was just wondering if you could just like comment on like lessons learned that would be relevant to this audience.
That's a great point and a great question. And I'll say in the computer graphics world, you know, we started off with these simple boxes of painted materials, and we have got into an incredibly complex, the kinds of materials I was talking about. But that's not actually the end. You're exactly right. There are people who are modeling diffraction and wave phenomena, and that's actually a big part. If you actually pull out, any one of you pull out your phone and you look at the phone at the right angle, you'll actually see the kind of diffraction phenomena that have to be modeled if you want to get the appearance correct. So what we have found is there's actually an endless, at every stage in computer graphics, people have said, we don't need that complex physics stuff. We can just, we'll be fine. And then somebody goes and figures out how to do it well, and everybody goes, well, obviously, we always needed that stuff, right? That's happened so many times in my career. It's almost, so when somebody tells me, we don't really need that level of correctness, I go, you know, once we figure out how to do it efficiently, I bet you'll show back and tell me, come back and tell me you did need it. So we keep learning, we keep pushing, and, you know, this, in our case, we have physics that, you know, gives us there's a ground truth there that you can aspire to. There is you have to look at it for the tasks. For example, these large language-based models, I think, could be incredibly valuable for creating, you know, creative output from random citizen artists, as I said. But they're not the people who are going to be doing the kind of predictive stuff that you need when you're actually building things with financial impact on them. So you pick the right model based on the task, and ideally what you have, and that's the whole question, can you get one general model like our brain is-ish, and can you then optimize it? But I would actually argue there are different experts here, and we also don't have like the one model. I'm not an expert on a whole bunch of topics. So you will have to have that specialization based on the needs of the task and go as far as you need to go for the task that you need.
Kavita, thank you so much.
Thank you.
It's such a pleasure.
AI at Stanford was pioneered by John McCarthy. This conference comes roughly 50 years after his Turing Award lecture on the present state of research in artificial intelligence. In it, McCarthy focused on the issue of generality in artificial intelligence systems. Last fall, HAI launched the Center for Research on Foundation Models, led by Stanford professor Percy Liang, who you'll be hearing in our next group of speakers. CRFM is an interdisciplinary team of more than 100 researchers that aims to make fundamental advances in the development, deployment, analysis, and safeguarding of large pre-trained models for language and their generalization to other data modalities, such as in the just released DALL-E 2 model from OpenAI, which you're also likely to hear about later in this session. We think that this is a very exciting time in the development of AI with these new foundation models, which are the first big breakthrough in addressing the lack of generality of earlier AI models. Indeed, these models have generated an enormous amount of excitement in the past year, so we hope that this will be a very lively discussion. Please join me in welcoming Percy Liang, Sarah Barnard, Cordelia Schmidt, Ilya Sutskever, and Rob Reich. Our first speaker today is Associate Professor Percy Liang of Stanford, Director of our Center for Research on Foundation Models.
All right, thank you, Chris, for that wonderful introduction and setting the stage here. So I'm really excited to be here in person, and hello to everyone online as well. Last week was quite a week. Many of you probably have heard the news of Google releasing their large language model, PaLM, which outclasses GPT-3 and can do all sorts of different capabilities, such as explain jokes, among other things. And not to be outdone, OpenAI released DALL-E 2 2 days later, which I'm sure Ilya will talk about, which can take captions and generate photorealistic images such as that teddy bear, which you've seen on a previous talk already. These two models are examples of a larger class of what we call foundation models. Foundation models are models which are trained on broad data, usually at immense scale in a self-supervised way, and that can be quickly adapted to a wide range of downstream tasks. And there are many examples of foundation models, some of which are listed here, some of which you've heard about. And one thing that I think is really significant about foundation models is that it changes the paradigm in which AI systems are built. So rather than having bespoke models for each individual task, now you train a general purpose foundation model that can be adapted across a wide variety of different scenarios. So I should underscore, though, that foundation models are raw and unfinished. And they're, by their very nature, they're a foundation, not the complete house. And there's work that needs to be done to turn them into actual applications. So there are things that you might not necessarily want to release to 1 billion users. And how to do this adaptation responsibly is an active area of discussion, which we'll hopefully discuss more about. So we recognize the importance of foundation models. And last year, we started a Center for Research on Foundation Models, as Chris talked about. Now it's over 200 students, postdocs, and faculty. And one thing that's really remarkable is how interdisciplinary the team is. So last year, we put out a massive report explaining the opportunities and risks of foundation models. We released some open source software to help people train foundation models, and we also held a workshop on inviting the entire community to engage on this topic. This year, and in the remaining of the talk, I want to highlight a few examples of the work that's happening at the center right now, which are roughly grouped into 3 categories. So the first is social responsibility, in which we are trying to benchmark and document the existing models out there, develop community standards, and also think about how these models are actually impacting people's lives. We are also making progress on technical advances, developing new model architectures, principled ways of defining new objective functions, and so on. And finally, we're looking at different applications, both general purpose capabilities such as privacy and robustness to distribution shift, but also ways in which the writers and designers can use these models in different ways, as well as whole areas such as law and medicine, which are kind of explored. So in the remainder of the talk, I want to highlight spotlight 7 of these projects in maybe 3 minutes or so. So we'll see how far we can get. So the first I wanted to talk about, this is a collaboration with Erik Brynjolfsson, where we're trying to understand we know foundation models are capable, but what is their impact on the economy? We look at kind of the total wage bill of writing occupations, as well as kind of individual impact on writers who are trying to use tools such as GPT-3 to do tasks such as copywriting. On the improvement of model side, transformers are the workhorse of modern foundation models. But they have one big deficiency, is that they're not very good at modeling very extremely long-range dependencies, which, you think about audio or video, presents problems. So this is work by Chris Ray's group, where they went back to the 1970s control theory literature, and where they had explored models of thinking about long sequences, and designed something called structured state space sequence models, S4. And they show that these models are much more accurate and efficient than transformers on a task such as speech classification. And furthermore, they actually are more robust to differences in sampling rates. So this is very exciting. We also looked at the question of what are the right training objectives, because there are so many ways you can train a foundation model. How do you navigate the space? And we asked a very naive question: what is an optimal foundation model or representation? Now, with some assumptions, we came up with the idea that the representations are always ones that can predict the equivalence class. Now, this is impossible to actually implement, but if you approximate it, this leads to a number of insights that allow us to improve over the state of art on some image benchmarks. Now, looking at ways that we can use foundation models. So domain adaptation is a critical problem because ML systems are known to be unreliable when you train them on a source domain and you try to adapt them to a target domain. But we show that if you train a foundation model on the union of the unlabeled data from source and target, and you simply fine-tune on the source, that actually beats classic unsupervised domain adaptation methods, suggesting kind of the generality of foundation models, which wasn't specifically designed for this purpose. Privacy came up in the previous session, where we want to try private models. But the problem is that when you ensure differential privacy, you had to add noise, and that hurts your accuracy. So one promising way to get around that is to train a foundation model on public data, such as Wikipedia, and then you can fine-tune on your private data. And we show that if you have the right setup, you can actually train these large differentially private language models based on public foundation models that are both accurate and private. So another collaboration is with Michael Bernstein from HCI. And here, the context is you want to design a social computing platform. You want to create a subreddit, but you're curious, how will people interact with it? Is it going to be dominated by internet trolls and so on? And we found that GPT-3 was actually a really good tool for enabling designers to generate human personas, goals, and interactions, which are all simulated, but give the designer an idea of what's plausible. And this is interesting because foundation models are trained on internet data, and usually this is a bad thing because it inherits all the kind of ugliness of the internet. But in this case, it's actually right because you want to simulate what would happen on the actual internet. A final example comes from a colleague, Akshay Chaudhary from radiology. And here, there's a massive opportunity here where even at Stanford, we're sitting on petabytes of medical imaging data. And the goal here is to train a foundation model that can power a wide variety of downstream medical imaging tasks. And here, the medical images are interesting because they're very different from internet images. So you see that green rectangle, there's a white blip. Is that noise, or is it actual indication of a serious kind of medical illness? And so some of the classical techniques don't really work in this setting. So there are many other projects I could mention, but hopefully this gives you a taste of what's been happening at CRFM. Maybe I could distill it down into kind of 3 themes. One is that foundation models are super impressive. They've been used in a lot of different settings, but they're far from optimal in terms of efficiency, robustness, bias, and all these things. And I think one of the things we're doing at CRFM is to go back to first principles and think, how do we design these models so that they can be much better than they are right now? The second point is that foundation models, you think most people probably have in their mind this teddy bear in Times Square, right? But I want to emphasize that foundation models are really useful for these kind of general capabilities, such as robustness and privacy, which are part of kind of the responsible AI session that we heard about. And foundation models in these cases actually gives you a substantial lift. And finally, while a lot of foundation models you hear about are focused on kind of internet applications, I want to emphasize that there is actually many more opportunities across a vast variety of disciplines, represented at Stanford across law and medicine and other sciences, and where there's a lot of data that you can harness the power that we've learned about through foundation models and make other discoveries in these fields. So with that, I'll end there, and thanks for your attention.
Thank you very much, Percy. Our next speaker is Sarah Bana, a postdoctoral fellow at the Stanford Digital Economy Lab.
Thanks so much, Chris, for the introduction, and thanks so much, Percy, for leading or ending with the applications. I think that what this project is it's really an application of foundation models to social science research, and I'll talk a little bit about my work as well as other opportunities for social science research. So where I'm coming from is thinking about a foundation model to provide new insights into the age-old question of what determines wages. Economists have spent decades trying to decompose wages into a variety of different elements. But one major problem is data constraints. So survey data, for example, one place where you can ask people their wages and what they do, is constrained because the more questions you ask, the more costly it becomes. The more people you ask, the more costly it becomes. Administrative data might be one potential solution to this problem, but in the United States, at least, occupation or what people do is not collected in administrative data. However, online job search provides a tremendous opportunity. Us being searching for jobs online and employers posting for jobs online gives us a digital trace in terms of what employers want as rich text in the form of online job postings. So what I do is I start to use a foundation model to answer the question of salary determination. Fundamentally, I'm interested in whether or not words matter for salary determination and whether or not we can predict salaries from the text of job postings. How well can we predict these, and if so, how do they compare to other benchmarks? If they are indeed valuable, what can the text of job posting tell us about what employers value in terms of attributes like different skills, titles, locations, and other attributes of jobs? To answer this question, we assemble a large data set with over 1 million job postings from 2019 by combining multiple different vendors' data. The critical attribute in this data is recruiter inputted salary bands. The job postings data has postings from a variety of different domains, like this clinical research coordinator 2 at Stanford University's Department of Pediatrics. So that's a pretty near job posting, but plenty of far ones as well, like this aircraft maintenance technician for UPS in Anchorage, Alaska, and also spans a variety of different domains, including this entry-level server at my sister's favorite hot pot restaurant near my hometown. Because these postings have such a wide variety of domains, a variety of different words are also used in those postings, and that's where large language models come in. So what I do is I fine-tune a BERT model for the task of salary prediction, estimate on out-of-sample postings, and then compare to a variety of different baselines. In this talk, I'll focus on the measure of how much variation the model is able to explain. That's sometimes called coefficient of variation, or R squared. I can show you a measure like root mean squared error, but I find coefficient of variation to be helpful because it's very interpretable, goes between 0 and 100. So it turns out that the BERT-based model does really well. It can explain 83% of the variation in salaries, and that's along the lines of a lot of other applications of BERT to economics. I'm now going to show you a variety of different relevant benchmarks, and I want you to think about these as, I'll talk about how these relate to varieties of different data we currently have. So first, occupation fixed effects. Occupation fixed effects means that we allow for a different occupation intercept for around the 800 occupations that exist in the data, and that explains just under 60% of the variation. We also know that location matters, and so we can add different intercepts for different occupations by locations, and we find that that explains just under 70% of the variation in the data. I want you to think about that benchmark, occupation by location, as the level of data that government surveys like the Current Population Survey currently collect. Now I'll do two sort of thought experiments, one with very broad skill groups like IT skills or legal skills or design skills, and then the other one with more specific skills like cybersecurity or artificial intelligence. And what you can see is that these two models still underperform compared to the BERT-based model. But you can imagine being asked, let's say, 28 or 648 different questions on a survey, or alternatively, your employer being asked whether or not your job requires all these different skills on a survey. And that's a huge burden. And even then, it still underperforms the BERT-based model, which has activities, skills, locations, but also things like experience levels, technologies used, and a variety of other information. So now, hopefully, I've convinced you at least a little bit that job postings have a tremendous amount of information, and we can leverage that information. A natural next question is, which tokens or words play an outsized role? To get at this, I'm going to use an attribution method called integrated gradients. I just want you to think about perturbing a given word or a given token and how that's going to affect the salary attribution process. And so these are just a couple select examples. So I've listed a bunch of activity-related words, and you can see the word manage is associated with a positive effect, or educate also being associated with a positive effect, but the word clean or assemble potentially being associated with a negative effect. These words also have mathematical interpretations. That is, for example, the inclusion of the word evaluate is associated with a 0.0002% increase in salary. Now, that might be small, but it's actually statistically significant. And I want you also to think about this as the effect of a single word in a job posting on salary. We can also look at technologies and see mostly positive attributions for technology skills. The Microsoft Office suite, not so much, but skills like SQL, Java, Python, a lot of the skills that we use in our work are associated with positive effects. So I see a tremendous number of applications of foundation models to social science research. I'll just briefly talk about one. I'm sure you've heard a lot of discussion about inflation nowadays. Inflation is actually really challenging to calculate because of the fact that products come and go. But Pat Bahari and co-authors have used product descriptions on Amazon combined with BERT to develop a hedonic pricing model and values of given features of goods. And what they can do is develop even better algorithmically defined price indices. So the big finding from their paper is that consumer welfare actually went up between 2013 and 2017 as a result of quality increases. So there's plenty more papers. I just wanted to point out that most of these are all came out or have been revised in the past couple years. And so there are plenty of opportunities in social science, and hopefully we'll be able to talk about a few more of them. So thanks so much, everyone, for your time.
Thank you very much, Sarah. Next, I would like to welcome Cordelia Schmidt, a research director at INRIA and a research scientist at Google, who's joining us virtually. I hope you can hear us okay, Cordelia?
Yeah, hello?
Hello? Yes, we can hear you. Okay, if you could please go ahead with your talk.
All right, let me share my screen. Right. Okay, can you see my screen? Hello?
Yes, we can see your screen and slides.
Can you hear me?
Yes.
Okay, perfect. So yeah, thank you for the introduction. And so I'll give two examples for large-scale multimodal learning. And so basically, what are the open questions? One of the open questions is actually when training these large-scale models, which training data to use. So this has been a recurring issue in computer vision for a long time. But if we have these large models and large-scale data, which is available, it's even more important to actually know which data we use to train these models. Only if we know which data we use can we really understand what is contained in them. And another thing which is important, that we have this multimodal information which is available. For example, video data, which comes with speech, audio. Speech can be transcribed by ASR into text, and have textual metadata. So we have this concurrent information which is available and which can be very well captured by these foundation models. One thing is, you have also heard before, is that many downstream tasks are possible, and they're completely new tasks which are now possible, such as vision, language, and navigation, robotics, multimodal translation, multimodal ASR, and many more. And then one thing which was also mentioned, which is becoming increasingly more important, is to develop alternative models which have possibly less parameters and can span larger time ranges. So for now, the time spans are still limited. I'll now show two of our recent examples. The first one for data curation, which uses cross-modal supervision, and the second one for a new task, which is a transformer-based model for vision, language, navigation. So what's the idea of our cross-modal supervision? Just ask. So the task we want to solve is given a short video clip and a question. So here, for example, what type of animal do we see? We want the system to give the answer. Here, the correct answer, which is produced by our system, is our fish. And so here the idea is that we want to go away from any type of annotated training data, but we want to perform zero-shot vision question answering, and to obtain the examples, use the cross-modal supervision. I'll explain in a while how this works. And this allows question answering dataset automatically. 96 million question answer pairs plus corresponding video clips. The idea is the following. We take a large scale dataset, here how to 1M, which comes with video clips and the speech transcribed with ASR. So for each clip, we have the corresponding speech transcribed. And given that those are instructional videos, we have, in many cases, a description of what's happening in the video. So for example, here, cut the white felt in circles. Then we have to our disposition a manually annotated text question answering training corpus. So there are text paragraphs, corresponding questions and answers. And we can then train a transformer on this data set. And we can then apply this text data transformer to our description of the videos and obtain for a given clip the corresponding question answer. And so we can see here, we have this an example for a generated question answer. We have the video clip, the ASR, the sound is amazing on this piano, and we can then automatically generate the question, what kind of instrument is this sound of? And the generated answer is piano. We then train a transformer on the data. Here we have a transformer which takes as input the video and the question, and another one which takes as input the answer. We can use contrastive loss with positive and negative answers to train our model on this large-scale data set. Here, 16 million different answers. And then we can evaluate this for zero-shot vision question answering. So we don't use any annotated training examples, but we evaluate the results on standard test data of standard benchmarks. And you can see the first row shows performance if we give random responses. And the second row shows our results with our zero-shot pre-trained model. And we can see that the performance at top 10, for example, 43% is very good already. Here an example of one of the zero-shot results. The question is, what is the largest object at the right of the man? And the answer is wheelbarrow. And if you would use a text-only model, the response would be statue. So you can really see that there's some gain from using the video. And we have seen here that we can use this cross-modal learning to exploit the large amount of data online available. So you have automatic data, a small annotated data set, and we can leverage the two together. We can use the correlation between these multiple modalities, here video and language. And open issues are how to further improve the zero-shot performance. We have seen that it's not yet at the same level as supervised performance. And one example would be to use fine-grained matching and object detection to remove incorrect examples. That's future work. And in the second part, I'll present a new task, which is a transformer-based model for vision language navigation. So what is the goal here? We have an indoor and synthetic indoor environment taken from real pictures and then assembled. So these are existing environments. We have an instruction here, go to the bathroom in the bedroom with orange stripes, make sure that the faucet is not leaking. And then we have an autonomous agent that wants to accomplish this task. And here what's new is we have designed a fully transformer-based model. This model takes as input the text, which is the instruction, then encodes the history, so what the agent has seen previously with the hierarchical vision transformer to memorize the locations and the actions the agent has seen before, and then takes as another input the current observation and feeds all this information in a cross-model transformer encoder and can then use this encoder to predict the action. And here again, what is important is the losses. So we resort to a number of standard losses for vision language training. So mask language modeling, last region loading, and instruction trajectory modeling. And then we can add new proxy tasks for vision language navigation, such as single step action recognition and spatial relationship prediction. And show that all of these losses improve the performance. The ones on the top are standard ones, and the other ones allow to refine our downstream model. And then we can show that our approach outperforms the state of the art on several data sets by a margin, and it was the winner of the Very and Soon Challenge in conjunction with ICCV 2021. So here we can see that transformers can also be used to predict actions. We have seen that standard vision language losses improve the performance and can be used as for other models. Again, additional pre-training data is useful. And open issues are how to generalize better to unseen environments, for example, by using more training data, and how to collect this additional training data. And then obviously it would be nice to apply these models also to real robots. Thank you.
Thank you so much, Cordelia, for that talk. Next, I'm delighted to introduce Ilya Sutskever, co-founder and chief scientist at OpenAI, and one of the people who's done more than anybody, perhaps, to lead to the development of foundation models.
Thank you for the introduction, Chris. I hope I can be heard. Sounds like I can. All right. Well, thank you for inviting me. And I'd like to tell you a few things. I'd like to tell you a story. It'll be a quick story, not longer than 8 minutes, actually shorter than that. One thing that I really enjoy about all of AI is how simple it is relative to how impactful it is. Unlike something like quantum mechanics or some other complicated physics or complicated chemistry or math, AI is really simple. You just have those artificial neurons which are inspired by biological neurons. And there is a math formula consisting of 3 equations that tells you how these neural networks should learn. It's called backpropagation. And it's the kind of thing which you can explain to a high schooler that knows math in about half an hour. But the magic is that the result has been so impactful. And so what ended up happening is that there is one recipe, essentially one recipe, that's been powering every single thing that's ever been done that's also cool in AI. The recipe is you take a big neural network a big digital brain running on a big computer cluster that's running this learning formula, which I described to you, that I told you about but did not describe, and you just feed it a lot of data. And then what you'll see next is how we vary this formula, how we change the neural network, how we change the data, and the downright magic that ensures. You know, when I started OpenAI with our co-founders more than 6 years ago, I was motivated by a belief that neural networks will continue to surprise us and to make the kind of incredible progress that they've made. And it's quite likely that the progress that neural networks are making, the progress that they have been making, will keep going on for quite a while. I don't think anyone here believes that neural networks will slow down. And so their impact will be very vast. They will touch every aspect of society, every part of human activity. And so with this belief, we thought to create OpenAI to not only fulfill the original sci-fi promise of AI, to realize it, but to also make it benefit humanity with all it entails. But now I want to go and dive into some of the technical details and tell you about some of the neural networks that we've built. Because time is so short, I will go quite quickly through them. So GPT-3 is just a really big neural network whose training objective is to guess the next word. Well, you could say, what's so special about guessing the next word? The thing about guessing the next word is that it's something you can do in math. You can just measure how good your neural network is at guessing the next word. But if you do a good enough job at that, if you guess the next word well enough, you must understand something. And the better you guess the next word, the better you understand. Imagine a mystery novel where the detective is about to unravel the identity of the criminal at the end of the book. If you paid attention, you might narrow down the appropriate next word down to 2 guesses, maybe even to 1 guess if you paid really close attention. So now you have a link between guessing the next word and understanding. So GPT-3, I think many people are familiar with it. At the time, it was quite surprising and unprecedented that you could just communicate with a neural network in this way, ask it questions, ask it to do stuff, do few-shot learning. It was a big surprise. Now it's been almost a year and a half ago, more. Old news. We're not surprised anymore. Tough crowd to please. One cool thing I want to mention are the use cases of GPT-3. One of the cool things about these models is that they're no longer science projects. They're useful. So GPT-3 has been exposed through the OpenAI API, and it's been used in production by hundreds of companies. I'll mention my single favorite use case called the Trevor Project, where they use GPT-3 to pretend to be disturbed teenagers to train therapists to talk with real disturbed teenagers. So I think that's my single favorite application of GPT-3. I think it's legitimately quite cool, if I may say so myself. I'll briefly mention GitHub Copilot. It is a collaboration we've done with Microsoft where we trained a really good neural network to guess the next word in code. Unsurprisingly, a neural network can do that task quite well also. GitHub Copilot is really popular. Programmers love it. And the users of GitHub Copilot commit 30% of the code that they commit is written by Copilot. So that's a pretty good statistic. And of course, as with all these neural networks, this is not the end point. This is more of an appetizer. Things will get a lot better. You may also have heard that we have made some progress on image generation with DALL-E. You know what it can do. You give it text, it produces an image. Why do it? We've made a lot of progress in text-only models, but the world is not just text. And I don't think anyone here believes that the powerful AIs of the future will be text-only. I'll just show you some cool images that I like. There's many more on the internet, but on the text, you have the caption that produced the particular image. I like this one. I mean, really, those are pretty good images. This one is, I think, caught the attention of many. I think Percy had this one in his slide as well. I like this corgi in the shape of a fish. It's pretty good compositionality, I have to say. You have to understand fish and corgi and the way it would look like if they were to be combined. fur monster in a purple room. I think it's a very appropriate fur monster. That's quite a beautiful photo of this family of mice with like the zoom in, like the blurry background, very artistic. Just a beautiful painting. I think that's quite meta. So I only have 1 minute, but I want to tell you about safety and deployment. You know, as I mentioned, our goal at OpenAI to not only build general AI, not only realize the promise of sci-fi, of the AI sci-fi of old, but also make it beneficial. And what that means is that we will be what it means is that we are building increasingly more powerful AI systems. We make them safe and we figure out how to deploy them. And I'll describe to you the high-level process that we use for deploying these systems in the remaining 30 seconds. And we've done quite a bit of work on this process with DALL-E. And in short, it consists of 3 steps, the high level. We do a lot of planning ahead of time, where we try to think about the many ways in which it could go wrong, the kind of biases that it may have, the kind of misuse potential that we really don't like. We make decisions. How do you trade off the exciting, cool applications with the negative applications? What kind of restrictions do you want to put on it? We do training, where we modify the training data and do additional training after the fact to modify the capability of the system. So for example, with DALL-E, we modified it so that it is unable to generate recognizable faces. It took us additional work to remove this capability. And then, of course, when we deploy our model, we put it on our servers behind an API. And we gradually increase the surface area of its application. And we carefully fine-tune the usage restrictions as we learn the ways in which people use those models and misuse them. This is all I have to say. Thank you so much for your attention.
Thank you, Ilya. Our last speaker in this session before the discussion is Professor Rob Reich from Stanford University.
All right, I stand between you and lunch, and you just heard from a whole series of people with technical expertise. I'm a philosopher by training. I direct the Center for Ethics and Society here, and I'm helping to bridge ethics on campus across to the engineering school as one of the associate directors of HAI. We live, to say something very simple, in an age of AI, agreeing entirely here with Ilya that AI is transforming every aspect of life, personal life, professional life, political life. And these enormous foundation models are the latest and potentially most powerful of the transformations that AI will bring about. And so I want to frame my remarks today, not technical remarks, but philosophical remarks, by sharing a passage that speaks to me and I think is relevant to our conversation today. The passage is the following. What the inventive genius of mankind has bestowed upon us in the last 100 years could have made human life carefree and happy if the development of the organizing power of man had been able to keep step with his technical advances. As it is, the hardly bought achievements of the machine age in the hands of our generation are as dangerous as a razor in the hands of a 3-year-old child. Anybody know who wrote that? It was Albert Einstein in 1932, 90 years ago. What can we do? What must we do to advance the organizing power of mankind alongside our extraordinary technical advances? That's the question I have for us today. That's where I think philosophers, social scientists, humanists have something to contribute to the technical and scientific advances of our extraordinary age. Now, one kind of response you might hear from a philosopher is to insert into the conversation ideals like the following. Let's think about justice. Let's think about fair AI and machine learning models. Let's think about equity, about transparency, accountability, and power. Familiar terms, familiar concepts, familiar ideals from our ethical and political lives. And those are important contributions. I have to say, I don't think, in my experience working with alongside technologists, that they hardly find them interesting or original, as if technologists were uninterested in justice or fairness or equity or transparency or accountability. They are. And there's enormous and productive amount of work taking place at the intersection of social science, the humanities, and technologists in order to make advances in those particular areas. You heard some of it just earlier in some of the presentations. So I want to take a different tack. I don't want to talk about fair machine learning at the moment. I want to frame for you a different way of thinking about these questions. And that's to identify what I'll describe as 3 different levels, 3 different kinds of points of intervention to think about the ethical and political dimensions of our machine age, of this AI age, of the foundation model age that's just dawning. The first level is what you could describe as personal ethics. Do you have a relevant moral compass that guides what you do as a human being? That's a familiar thing for people on college campuses. It's a familiar thing to talk about in the wider world. We should all have some moral compass that orients how it is we act. And I want to share with you what I find this the least interesting way to think about ethics. Because number one, human beings are not perfect. They routinely fail their own moral compass. Does anyone think that if Elizabeth Holmes had only gotten the ethical reasoning course at Stanford before she dropped out, that it wouldn't have gone the direction it did? Or that other people across any domain of life, Lance Armstrong, Richard Nixon, had only taken enough ethics courses to have gotten their moral compass in order, that all would have been well? No. Moral compass is fine, personal ethics is fine, but we need to organize our lives to assume human frailty and human moral failure, because that's the human condition. So the second level of ethics, the second point of intervention, is what I'll call professional ethics. How is it that people in a profession organize themselves around a common set of norms or an ethic of responsibility to steward their own work, to regulate, as it were, in a soft way, not through law and policy, how it is that the professional domain advances? I want to focus my remarks largely on that area with the last minute or two I have left. But I'll just identify the third area of intervention for ethics, which is social or political ethics. How do we think about formal policy, law, and regulation? Now, the premise of the work that I've done here on campus with HAI and with colleagues in the computer science department and in public policy is that on the advance of science and technology, there will always be an outpacing of the capacity of formal law and policy to be on the frontier in a wise way. So in this race between what you could call disruption and democracy, the technologists and the scientists are always pushing ahead more quickly than how regulators can knowledgeably act. So I draw from that general observation, a reflection that many people in the room might share, that there's a kind of suspicion of DC policymakers getting in the game now to think about what OpenAI is doing and putting in place a set of regulatory guardrails. Instead, we need to think about professional ethics, professional norms that organize the work that we do as AI scientists, because we shouldn't count on the ability of regulators to keep up with the frontier. And so, thinking then about professional ethics and professional norms, I'll just offer up an invitation for you to imagine a comparison between the professional norms that guide the field of biomedical research as compared to AI science. In biomedical research, we have things as old as the Hippocratic Oath. We have professional licensure requirements. We have the institutional review board that guides any type of work with human subjects that happens in universities or in pharmaceutical companies. We have a federal administration, the Food and Drug Administration, that's required to give permission to anything that's released on the market. We have an entire scholarly field called biomedical ethics that has grown up over the past 60 to 70 years. We have hospitals and companies that have ethics committees as a routine part of their organizational practice. Now, AI is, by contrast, a developmentally immature domain of scientific inquiry. AI has only been around, computer science has only been around as a field, formally speaking, since the 1950s and 60s. And given recent developments in AI that have taken place just in the past 15 years, this neural net age, it's much younger still. So to put it in a provocative way, what I would invite you to think about is the idea that AI scientists lack a dense institutional footprint of professional norms and ethics. They are, to put it even more provocatively, like late-stage teenagers who have just come into a recognition of their powers in the world, but whose frontal lobes are not yet sufficiently developed to give them social responsibility. They need a rapid acceleration. We need a rapid acceleration of the professional norms and ethics to steward our collective work as AI scientists. Think, for example, of Jennifer Doudna, the other twin revolution that's shaping the 21st century in gene editing and CRISPR. She wakes up, Walter Isaacson tells us, from a dream, a nightmare. What if Hitler had access to this technology? And she organizes her professional peers within the professional bodies of biomedical research to impose a voluntary moratorium on the use of CRISPR on humans or human embryos. No one will be allowed to publish if they cross that moratorium. They won't be invited to professional conferences. There's a strong professional norm in that domain. AI scientists, to the best of my knowledge, have very few institutional touch points that parallel biomedical research, and I pin that on the idea that it's a younger field. So as we hear from Ilya and others who are at the forefront of pushing the technical frontier forward, my question for us, who is organizing the organizational and institutional and professional ethics to accelerate at a pace that matches our technical advances? I'll conclude with just 4 simple questions specifically about foundation models. Number 1, we know that there are huge risks. We've heard about misinformation, disinformation on steroids, about job displacement. Sam Altman tweeted out last week after some of these announcements that we thought for a long time that AI was coming for the jobs of low-skilled workers, but it looks like actually it might come for high-skilled workers first. Coders, illustrators, writers are the ones that will be displaced, not truck drivers, or at least in that order. And then there's a huge concentration of power. This is the paper that Percy referred to, the opportunities and risks of foundation models. So, question 1, what are leading AI scientists doing to accelerate the development of professional norms? What counts as responsible development? To put a question on the table for OpenAI, I hope Ilya can speak to, I know that he can, he has in the past, about the shift from GPT-2, in which there was a restricted release, a kind of policy override of what otherwise might have happened within AI science, to a different orientation now with GPT-3 and beyond. Number 2, as someone who writes about democratic theory, you might be surprised to think that I am suspicious of the idea of democratizing AI. We don't want to democratize access to some of the most powerful technologies to put them in the hands of anyone who might use them for an adversarial purpose. It's a lucky thing that access to plutonium and uranium is not democratized, and it's easy to organize limiting access to it. But with AI models that are in the world open for anyone, we're inviting adversarial use. How can we move away from democratizing AI in that respect, but opening up access to independent researchers? Third and last question, we need to think about the political economy that exists. No university is capable of putting together the compute and the data sets to make these models on the frontier. It's for-profit or capped for-profit companies that can. We need to think about issues of brain drain, about commercial incentives that drive the scientific frontier rather than scientific inquiry and non-commercial incentives. All right, questions, provocations, not answers. Thanks for listening.
Thank you, Rob, and thank you to everyone who spoke on this panel, including Cordelia Schmidt, who's being represented by that large video monitor down the left-hand end, to be as part of our panel. Okay, so for the next half hour, we're going to have discussion and questions. So it looks like I don't really need to say this next bit of coming to the microphone. There are 3 microphones if you'd like to ask a question. It seems like there are lots of questions, including the very big picture questions that Rob asked at the end of his talk. I'll just ask one while we're getting started that is much smaller than some of the questions he asked. But I mean, so for foundation models, there are clearly safe uses. So Ilya gave one nice example of a safe use with the Trevor project of training suicide hotline people, and that's very safe because it's just used for training. I mean, using codecs for coding sounds fairly safe too, though you could imagine that there are things that go wrong there. But it seems like there are also a lot of uses that aren't safe. Do any of you have any thoughts as to how one can define the boundary between safe and unsafe uses of foundation models?
Maybe we can start. I would actually say, I mean, codecs has potential problems. I mean, imagine a code that you're generating that, I mean, people already don't necessarily understand the code that they're generating, and if AI is generating the code and it seems to work, you could have kind of insidious security vulnerabilities that potentially slip in. I mean, I think this is generally a good question about dual-use technology. There are some places where if you're trying to do drug discovery using a large foundation model, that's perfectly fine. But if obviously on the other end, if you're spamming or engaging in fraud or disinformation, that should be outlawed. I mean, this is where I think it's less at the technical level, because the technology is by design just capable of things, but at the kind of process of terms of use, or kind of having a more of a system in place for tracking kind of what these models are released for and what can people use them for, and having mechanisms for if something is misused, having ways of reporting. And I think we lack that infrastructure right now because the emphasis is more on kind of training these models, but the models need to kind of exist in a larger ecosystem.
Yeah. Anyone else have a thought? Yes, Sarah.
Well, I think earlier in the panel, somebody talked about PII as a result of just querying the systems, right? Presumably, do we consider that unsafe use? And if we do, then the boundary for safety is very different.
I'll just add that there's call it a small scholarly field of research done under the heading of AI safety that applies in particular to questions about the aspiration to reach AGI. So that's one place to look for an answer to these questions. But from my point of view, thinking about this as a political philosopher, not just strictly as a moral matter, any large picture questions about what we define as safe or unsafe uses seems to me necessarily to extend beyond the purview of any technical expert or even company. Having an AI safety team at a company is all well and good, but ultimately questions about safety are social questions that deserve input from multiple stakeholders.
Okay. Well, maybe I'd better start turning to questions from the audience. Maybe I'll start with the very back mic person. And it'd be great if you could just sort of introduce yourself very quickly before your question.
Yes, I am Ethan Hamilton. I got a PhD in electrical engineering from Stanford, and I work as a software engineer in a local startup. So I have 2 questions, one very short for anyone, probably Ilya. How much does it cost? Everything, training, salaries of the researchers, you name it, to produce one of these foundational models, to know how high the barrier is. So that would be the first question. The second is for Rob. I want to challenge, so I agree with that there is a problem, no question, but I want to challenge the FDA as the perfect model. ProPublica has made a great reporting about each of the large big pharma companies has been fined for malicious marketing of drugs. It's a legalized drug cartel. do we want to create another one of those?
Okay. So Ilya and then Mark.
Thank you.
Yeah. So I can't comment on the precise cost of these models, but it is indeed the case that they're not cheap to make. And it's not just the compute. You also need to have a really strong team working together for quite a while. So yeah, I mean, my expectation is that for if, let's say, universities want to participate in the creation of these models, they need to do what Stanford has done, which is to basically band together and organize a lot of resources. And in particular, I think that one place where universities need to build some muscle is on the engineering side. Because you can get money, you can get compute. Mm-hmm. But then the natural way in which universities do research is different from the kind of organized effort that's needed to really push such a system. So I think that this would be another organizational hurdle that universities would need to overcome to participate.
But it's in the range of, say, tens of millions of dollars, hundreds of millions of dollars. It makes a difference.
I understand, but unfortunately I can't comment right now.
Yeah, I think there are some papers you can read on that, but let's turn to Rob.
I don't mean to point to the FDA or the idea that we should create an independent federal agency, the Digital Technology Agency or something. I meant that as an analog. Here's what biomedical research has built out over the course of decades, and here's what is absent from AI science. I don't think we port the professional norms and institutional design from one domain over to another domain. So I mean it as a way to think about the density of the institutional design. And of course, we need to come up with purpose-built answers for the age of AI.
Okay.
I have a question for Ilya, but for anyone in the panel. Given all the advancements in multimodal, multitask foundation models, how do you define AGI? What are the milestones to get there? And is embodiment key for it? Or what are the other requirements people aren't talking about?
How to define AGI? So it is indeed the case that AGI is a little bit of an ambiguous term. It's not used very precisely by people who use it. It should be understood as more of an aspirational goal, kind of like a North Star. And the way you can tell that we have reached the age of AGI is when you have lots of computer systems. Like one way to tell, here's one way to tell, is when most of the economic activity is done by some kind of an AI. This is an objective criterion. Because if someone comes to you in the lab and says, oh, check out what I got, how can you really know whether you're being shown something real or not? But if you are living in a world where the economy is growing really fast because AI is doing the great majority of all economically valuable work, that's how you know that AGI has been reached. I mean, I think that the current models are really exciting. They're making a lot of progress. And like the way to really measure their impact is like how much are they being used in the real world to actually solve problems. Like I would say that right now, these models are just breaking out from the lab. Until very recently, AI would make a lot of exciting progress on benchmarks in the labs. It would be really cool science projects, just starting to get out, starting to impact the real world. So there's still lots of work that needs to be done. The models need to get so much better, so much more reliable, need to explain ourselves, really collaborate with us in order to solve problems. All these things need to happen. We are seeing very small steps in that direction. Things will be a lot more exciting in terms of how much these systems can do.
Okay, let's take a question from Fei-Fei, and then you'll be after that, Pat.
Yeah, okay, I'll start with the intriguing technical question, possibly mostly for Ilya, but interested from the technologists too, is that when we look at that corgi fish picture from DALL-E, frankly, for average human, it's very hard for an average human to draw a corgi fish. In the meantime, for average human, it's very easy if I ask you to draw a toy cube tower that would fall under gravity. Like that concept of a simple tower, toy tower fall. So there's a discrepancy. I think that's going to be hard for DALL-E. So there's a discrepancy between what's easy for human to generate and what's hard for machines. Do you want to comment on what in the making of these transformer models that create this discrepancy between DALL-E and humans?
Yeah, I can comment on that. So I'd say, that question, there are actually two different sub-questions. In the case of DALL-E in particular, it was designed, there were certain engineering and design choices that were made, which are not inherent. They were made for convenience in order to make the system have certain better properties. So because of that, it is not as good at some of these tasks which you mentioned, but those limitations can be lifted. I do want to point to a deeper, more fundamental difference between these neural networks and human beings. These neural networks, they have more breadth and less depth. Like if you consider a language model may have read far more books than a human being ever would. But a human being understands the information that they've consumed more deeply. So I think that this is the more fundamental discrepancy between human beings and AI. So it is indeed the case that there are many more scientific breakthroughs that can be made to improve those systems. Despite this discrepancy, there are still clear avenues for improving those systems, and so they will still get a lot better. And perhaps over time, those discrepancies will diminish as well.
Maybe I can make a quick comment in response to Fei-Fei on the last question, which is how one should kind of think about progress. Because I think AI traditionally has been viewed as kind of autonomous systems where you measure them in isolation. But we know for a fact, especially when they're deployed in the real world, we hope that they would be under some control or aligned with values of humans. So I think human beings have to be part of the picture. And then you go back to kind of thinking about economic impact. It's not clear how that aligns exactly with this kind of age-old dream of building human-level intelligence. In some ways, that may be not even relevant, because what we really want is tools that help us build a better society. And if they can't do certain things that humans can, that's perfectly fine, as long as they can do a certain well-defined set of things well, robustly, in an unbiased way. I think that could have a tremendous amount of impact. And I think that maybe framing is maybe a way we should be thinking about assessing the value of these technologies rather than measuring it against a kind of a human yardstick.
Okay, let me get a question from Pat.
Sure, thanks.
Cordelia.
And this is mostly for Chris and Percy, who can probably guess what I'm going to say, because I say this after every talk I hear at Stanford. So the best science and the best engineering builds on previous work, and the failures and the successes of that previous work. Now, AI has a long history of successes and failures, but we've had deployed AI systems in industry since the 1970s. We had deployed systems that were built using machine learning by the late 1980s, long before deep neural networks became a thing. And in natural language processing, there were a bunch of systems that were used for various applications using classic natural language technology, and you guys were trained with some of this. I know you still cover it in some of your courses, but when I hear you talking about foundation models, I grant that there's been plenty of progress and the results are impressive, but it would seem to me there must be some way to bring together that progress and some of the classic ideas to get the best of both worlds. In particular, in a meeting on human-centered AI, some of those older approaches are far more connected to what we know about how humans process language. So can you say something about how we might do that, or if you think is that a bad idea?
Okay, I think Percy, you better take that.
Yeah, I can definitely take it. I think there are certain things that are age-old and will never disappear that we should think about, kind of knowledge, representation, and kind of reasoning. But there are also a lot of things which in the 70s are probably not relevant today, given kind of what we know about how capabilities. I think that one way I think of these technologies is they're very good system one. They can instinctively kind of generate things on demand, and but for very long-range sophisticated reasoning, they're getting better, especially with some of the latest kind of multi-step reasoning things, but they're not quite there, and they certainly don't have the crispness that we have. So that part is still missing. I mean, one outstanding question is whether we can get there. I think that is open with the kind of existing methods. That I think is an open question, and I like to be kind of open-minded about it because in the last few years, I've been surprised. I think everyone has been surprised how these technologies work, and I think but I think holding on to some of the kind of the principles of how you can generalize, I think is very worthwhile.
For example, you could imagine using.
Pat, I think there are a lot of questions, so maybe I think we'll have to move on. You can pick on. You can talk to Percy later.
And my name's Pat Langley. Thanks.
Let me try and bring Cordelia into the conversation. So picking up on that theme of being more human-centered, so there's been productive work on multimodal models, but most of the visual work has used just images, and that certainly stands in distinction to human learning, where not only do we have the equivalent of video, we're seeing this moving world around us, but human developmental studies have shown the absolute importance of interaction for little kids to learn, right? So just watching videos even isn't very effective. So does that mean for multimodal foundation models we should be doing something quite differently? I mean, to put it most provocatively, one could argue that something like DALL-E is really a sort of a dead end because it's not really heading us in the right direction for human-level artificial intelligence.
Yeah, I think we should.
Can we see if Cordelia, do you have some remarks?
Yes, I think I would agree that basically the next step is really using video because you have all the motion information. I mean, basically Fei-Fei's example for tubes falling, you need motion information to learn from them. You have all the corresponding information with audio and speech, so you have a much richer corpus of information, right? And I think you can also see obviously the video as an extension from the images, right? It's not because you can generate an image from text. The next step would be you could generate a video from a sentence, right? So I think it's not either or, but I would say video allows you to do much more. And then I guess video has the multimodal information. And one thing of these foundation models or these transformer models that they can really capture this multimodal information very well, right? It's much easier to design multimodal representations with these models because they can learn automatically what corresponds between the different modalities. And then obviously, if you want to go towards more general intelligence, you need to also interact with the world. But that's something I think we don't, I mean, we just start to see how these models can actually integrate interaction with the environment. And so I think that would be the next step.
Okay. Do you have a comment, Ilya?
Yeah, just a brief comment is that one way we can think about the progression of these models is that of gradual progress. We've made a lot of progress in text-only models, and we were surprised by what they can learn. We have added another modality, perhaps not perfectly. Perhaps this is not the final way in which we will add the modality. Some exploration will need to be done. But eventually, I think it is a reasonably safe bet that we will figure it out as well to find a very useful packaging of the modalities so that the system will know more, understand the human world better, and be able to interact with us better because of them. So it's a technical problem that will likely be solved.
Okay, great. Right up the back, yes.
My name is Evelyn. I was a Stanford student, and I took my first AI class with Professor Liang. So I really appreciate it, Professor Liang. And you mentioned the process of adapting a general model to a specific domain. So I guess my question is actually to Ilya. I have built an application using GPT-3. And by the way, OpenAI has a very good safety review process. I went through the process, got the approval, and rolled out a global launch. What I observe is that the option to customize the general model to a specific domain is very limited. Although there are options, but it's very limited. So my question is, what is OpenAI's plan to allow more customization and configurability of the GPT-3 or DALL-Es?
Yeah. I mean, you should expect that that the ability to customize these models will increase in the future, customize them through fine-tuning. I do want to make, however, so I should say, it will become easier and the tools to do so will become more powerful. But I also want to make one other comment, and that's about the shape, the likely shape of customizability of these models in the future. One point of view, which I happen to believe in right now, is that if you take a model, any neural network, and you have some kind of benchmark, and you fine-tune the neural network on this benchmark, you'll get really good performance on the test set. But that doesn't actually mean that your system is that good. And that's something we've seen a lot also. I think it was most apparent in the kind of intermediate years, maybe like the mid-2010s on ImageNet, on the ImageNet dataset, where people started to report human-level performance on ImageNet. Yet the systems were obviously not human-level not at the human level. So what does that mean? Like, I think what that means is that there is hidden overfitting going on when you fine-tune. And so I think that several things will need to happen. Like, the fine-tuning technology itself will need to improve so that you'll be able to preserve a lot of the generalization of these powerful base models. And we'll actually find that zero-shot evals give you the best and most reliable, like, representative performance. What you can get zero-shot or few-shot, you know that's on your test set, you know that's the performance you're going to get in the wild. So it's a much more honest measure of performance measure for yourself as you evaluate your system.
Okay, sorry.
Yeah, perhaps this question is best suited for you, Professor Liang. I was just curious, what is the academically precise definition of this so-called foundation models term? Like, you know, models are getting bigger, they use billions of parameters, they're able to generalize beyond expected tasks. Like, all of these are nice properties of some of the things we're observing. But I'm wondering if there's a precise way to say, okay, this is a foundation model and this isn't. I mean, is it a vague sort of comment on an industrial inflection point, or is it actually something that we can say that this is a foundation model?
Yeah, that's a good question, and we spent a lot of time thinking about this. We actually have a blog post on our website that explains the details, but just in brief, it's a spectrum. Is BERT, let's say, is Elmo a foundation model? Maybe. BERT is probably a foundation model. GPT-3 is definitely a foundation model. The definition I gave in the talk is a model that is trained on broad data and can be applied to a wide range of downstream tasks. Now, those are, fuzzy terms, but I think the breadth of the data is important because that's, and also when you talk about broad data, that implies certain other features such as, self-supervision and training at scale, because without those, you can't really train on broad data. And so I think many, you could think about breadth and the kind of as the kind of key defining factor, and many of these incident, whether you use a transformer or use backprop, those things kind of follow out given where we are in terms of the technology. In 10 years, maybe we'll have, we won't be using transformers, we'll be using something else, and we'll be training in a slightly different way, maybe with reinforcement learning, but that doesn't change the kind of the essence of a foundation model.
So any large model trained on a wide breadth of data is a foundation model?
So a model that's trained on a broad set of data and can also be applied generally. Yeah.
Okay, Fei-Fei, let's take one more question from you.
Okay, this question is absolutely inspired by Rob, so by Rob's talk, as well as for the past 3 years, he's worked with me on this and inspired me, but I'm asking this to technologists. Rob talked about the need for professional norms and ethics, and Rob has also inspired all of us at Stanford to think about baking ethics into the design of algorithm. So I want to ask Cordelia, Ilya, and Percy, when you are building your foundation model, big or small, what exactly are you doing, or your organization, are they doing baking ethics into the foundation models?
Yeah, I could comment on OpenAI's process around the way we go about releasing these models in a way that allows us to capture as much of their beneficial uses as possible, while contain their harmful uses and contain their harmful biases that we don't want exposed as much as possible. I mentioned it in my last slide of my presentation, and I want to elaborate on that. So, we think about it a lot, and we see us finding good practical answers to these questions as a core part of our mission at OpenAI to build general AI and make it benefit humanity. We want to figure out how to actually deploy these systems with each new level of capability. I'll mention an anecdote. When we trained GPT-3, we kind of already foresaw many of those issues. And so we had we also had the luxury that no one else had such a model. So we took a very long time. It was almost a whole year where we manually reviewed every single application request to use GPT-3 somewhere. And we built a very large amount of institutional expertise around the kind of use cases that are okay, the kind of use cases that are more objectionable. There have been some ambiguous calls as well. And the process that we've converged on today, that we will continue to refine, is one of, we look at the capability that's about to emerge, and we try to anticipate and categorize the different uses that we can predict just by thinking. We make a list, and we say, okay, this looks exciting and we want to support it. This looks like we really don't want to support it. We then make a decision on the basis of those predictions around what will be the next step. So for example, we might modify the training set using filtering, or we might do additional training on top of a finished model. So for example, we've had work recently that we've announced where we used reinforcement learning from human feedback to teach a GPT model to follow the intentions and the instructions of its users much more closely, to be more aligned. We've done this work. And then on the third step, the models are on our servers, and we have very precise controls on the kind of queries we want to serve and the kind of specific applications and uses that we want to support or not. So there is a usage policy as well. So that
maybe we should get thoughts from others at this point.
Can I
I'll let Cordelia give her thoughts on professional norms first, and then Percy.
Yeah, I would say it actually joins the question about what data we use to train these models, right? Because if we don't know what data goes in, we have no guarantee what comes out, right? And this, I think, is a central point that we have to understand much better which data goes in. And for language, I think we know which corpuses the data comes from. This gives us some guarantee that for example, we train it on books, that there's not misinformation per se in there. But if you have any random content, you really need to curate the data. And I think this is like one of the things which are really key, to know which data goes in. So this is the first thing. And the second thing is to make these models more interpretable. To have an idea why this answer was given, where it comes from to backtrack and then maybe remove the data.
Maybe just one follow-up to Ilya's one. I think it's great that OpenAI is taking these measures to ensure the safety. I think it's not enough in the sense that there's a kind of a certain sense in which these models are surface area is so broad. I don't think any individual team, let it be OpenAI or Stanford, anyone, has the ability or even the authority to really determine what decisions to make. And I think there's some tough trade-offs. For example, how you filter. If you filter toxic information, you could marginalize certain groups. And I think there's constant tension here that I think demand kind of a much more public and visible kind of discourse. And also, I talking to many kind of large foundation model developers, people have very different opinions and norms about release, what's safe and what's not. And I think we should be acting more coordination as a community to figure out get on the same page with respect to what are the kind of the issues, what trade-offs, and it's fine to disagree because everyone has slightly different values, but also kind of use cases, but there's a certain kind of consensus building that I think we're lacking a need here.
Bob, do you have a quick
I mean, for anyone here, but just a response to Ilya's remarks, underscore that I agree with Percy that if we're talking about a foundation model that has these general adaptations, whatever the size of the team is at OpenAI, and however hothoused and long the process was in trying to imagine use cases that you wanted to try to intercede or limit, well, if millions or potentially billions of people had access, presumptively, they would come up with use cases that you couldn't imagine. So that makes me wonder, since no team, agreeing again with Percy, possibly could imagine all possible use cases, how about talking openly and publicly, looking for feedback on whatever the framework was that you used internally for identifying beneficial and malicious, or however you describe them, use cases. What was the framework OpenAI used in this year-long process, however long it was, in order to sort out what counted as worthy and unworthy use cases?
So I want to make a comment on on the first part of the question. Another important part of the way in which those models are released is that they're released gradually. So rather than say, hey, we've got a new model, billion users, please start using it, we're going to say, well, let's start with 100 users first and see what they do, and learn from that. And then you release it to the next 100, the next 500, and you fine-tune the policy and the various controls that you have on the basis of those experiences. So in other words, instead of doing a very big discontinuous release and maybe finding yourself facing a crisis, you have very small releases, and so you're able to productively learn from whatever happens and bake it in. And this graduality is very important. There is another thing that I want to mention that will be increasingly important in the future, is that the AI capability itself will be helping us with making these decisions. At present, AI is not good enough and it cannot be counted in order to help decide on use cases and explain why a use case is good or not. But in the future, I expect it will change. And that will be a very important tool in the toolbox of deploying such systems and dealing with their large surface area. I would say, and to your question of the specific framework that we used, so this stuff was very new when we were doing it, and so we've taken a pretty restrictive and a conservative approach. We have decided that we want to err on the side of caution. That would be my general description of the framework that we've used. And we figured we'd rather start restrictive and gradually expand it, as opposed to start overly permissive and then contract it. So that might be the one-sentence summary of the framework.
I think I'd better cut things off there. This is a great discussion. I'm sure we could spend another hour just talking about the answer to Fei-Fei's question alone. And I realize there are other people that are hoping to ask questions. I'm sorry, but we're already eating into lunch hour, which seems a bad thing. So hopefully you can answer your questions either by cornering the speakers during lunchtime or with other fellow lunch eaters, or else you could send them along to HAI. But anyway, thanks to our panelists one more time for the engaging discussion.
Our next panel is on a topic that's dear and near to my own heart. In recent years, we have only seen explosive progress. We have not only seen explosive progress in NLP or visual recognition, such as image classification, our general field of AI has made great progress in fundamental technologies in 3D computer vision, computer graphics, and computational optics to model the physical world. You got a glimpse of that from the keynote speech by Kavita Bala earlier today, but we're diving in deeper. Advances in these areas have resulted in progress in VR, AR technologies, a resurgence of work linking AI and robotics, and new frontiers of embodied AI and grounding. We'll be hearing about some of those advances as well as its social implications in our next panel. So please join me in welcoming Dieter Fox, Andrew Kanazawa, Gordon Wetstein, Jiajun Wu, and Anna Lemke. Thank you. And of course, Chris Manning. So our first speaker today is Dieter Fox, who is joining us remote. Hi, Dieter. Can you see us? Great. Dieter is Senior Director of Robotics Research, NVIDIA, also Professor of Department of Computer Science and Engineering in University of Washington. Dieter, the podium is yours.
All right. Thanks a lot for having me, and I'm very excited to be presenting here. Let's see does it all work with the display screen? Okay, can you see the slides?
Yes, you look great.
Okay, perfect, thank you. Yeah, hi everybody. What I want to present on today is why I'm excited about simulated environments and why that is the case even coming from me as a core robotics researcher. At the NVIDIA Research Lab for Robotics, we're focusing on kind of the core technology to develop the next generation of robots that can interact with people in populated dynamic environments and solve complex manipulation tasks. Application domains could be in industrial settings, but also, for example, in the healthcare setting or in normal home environments. As Fei-Fei mentioned, over the last years, we've seen great progress on these interactive 3D environments, simulated environments. Various teams have developed really nice settings here. You can see some examples on the slide. Most of these have been developed by the computer vision community, and the robotics community has been somewhat hesitant to kind of fully embracing the setting. And the reason is because we have the saying in robotics that simulation is doomed to succeed, meaning that simulation always makes various abstractions, assumptions about the world, and somehow you get your robot always to do the things you want it to do in simulation, but that doesn't mean that it's going to work in the real world. Another way to put this is, in the more modern terms, is the sim to real gap between simulation and reality is too large. And you can argue that various of these environments actually do make quite some assumptions and abstractions about, for example, especially the physical interaction between the robot and the objects it wants to interact with. And therefore, the success of this environment has been really, especially in the navigation domain and in the high-level reasoning domain. But looking at low-level physical contact-rich interaction is still kind of an open problem in this area. And I just want to go through some examples for why I think this missing link between these kinds of simulations and the real robot, physical interaction in the real world, why we can really bridge this gap with these more recent development on the simulation side, especially the physics and photorealistic simulation side. Let me just give you one example for how we can use this to solve some real, let's say, robot manipulation tasks. Imagine you want to teach a robot to pick up certain objects. You can do this in simulation by just having a shape model, like you can see here on the left. You have various copies of this red object, and you just randomly generate possible ways for grasping that. So you have different relative locations of a gripper relative to this object, and then you run this through a physics simulation, and you check out through the physics simulation which of these grasps succeed at appropriately fixing the object in the gripper. You can do this, of course, in parallel. You can do this for thousands of objects, thousands of grasps that you try for each object. And then you can generate a large data set, as we have done here based on ShapeNet, where let's say you have close to 9,000 objects, and you can annotate picking up unknown objects solidly based on depth camera data. And it works actually without any retraining or fine-tuning, just coming out of the simulation. We can apply the similar techniques now also, for example, for the robot to pick up objects when people want to hand it to it. Again, the grasping strategy is solidly trained in simulation. Other kinds of objects that we can now start to simulate are, for example, deformable objects. In these panels, what you see on the left side is the real world execution, and on the right side, you see a simulated model. All these models now can be done in real time. So we can simulate, for example, how tofu gets squeezed and things like that, or these tubes. We can also simulate more complex phenomena like pouring granular media through a funnel. In this case, it's couscous and barley. And you can see that behavior on the right side of the simulation matches the real world actually very well. And we have also machine learning techniques that can actually adjust the simulation parameters to become more similar to the real world. Here's another example that I am actually very excited about. This is kind of hot off the press. Just today, we got it accepted at RSS this year, where the idea is simulating really fine-grained industrial kind of tasks like screwing a nut on a bolt. This has been up to now virtually impossible to do because it took way too long in the simulator, and also having the fine-grained models to simulate this accurately haven't been available. So we can now actually, with the new collaborations we did with the physics simulation team, we can now simulate 1,000 of these interactions in real time. And we can also use this now finally to actually train robots in simulation to do these kind of tasks. So this is something that up until now was not possible. And we can now finally really move robots in these industrial settings and train them to do these kind of tasks. The final example here I want to give is now scaling up, where it's again not just about robot interacting with a single object, but using frameworks such NVIDIA's Omniverse framework, which is designed for really scaling up these simulation environments and the training engines. We can now start simulating complete, for example, manufacturing processes or warehousing operations and things like that. And I think you would agree that in these videos, it's actually very difficult to determine which of those is real and which of them is simulated. So I think with these kind of capabilities now, we can get closer and closer to being able to train our robots in simulation and then transfer the trained policies to the real world. So with that, I want to wrap up where I believe that we're now really ready to train robots in simulation on very large scale settings, and also that this will have a very big impact on the future development of robotics. So we have physics-based simulation that also is photorealistic for many of these manipulation tasks, as you saw. I think the key advantages over immediately deploying our robots in the real world is we can train our robots in simulation. This means that the training can be done safely. It can be done much faster than real time, as you would have to do in the real world. And another key advantage is that since we're doing it in simulation, we can leverage the perfect state information that the simulator has to generate demonstrations that we can then learn through deep learning, for example, to replicate. I think that's a key advantage of training in simulation than immediately training using, for example, reinforcement learning in the real world. From a scientific perspective, I think simulation has a huge advantage in providing controlled environments that we can use for our experimentation and benchmarking. We can now really fairly compare different techniques, different network architecture. I think this will also lead a way towards maybe more capable foundation models. We can have a discussion on that later on. And I think the key limitations really moving forward right now is how can we generate sufficient assets, environments, and experiences in these kind of environments. And also, which is of course a core topic in this panel here, is how can we integrate realistically looking and especially behaving humans into these environments so that the humans can train robots in simulation. And with that, I'll thank you for your attention.
Thank you. Thank you, Dieter. So now I'd like to welcome our next speaker, Anju Kanazawa. She's an assistant professor in the Department of Electrical Engineering and Computer Science at the University of California, Berkeley. Go ahead, Anju.
Thank you, Fei-Fei. All right. Okay, so I'm super excited to talk about the directions that my lab is thinking about these days. So the founding principle of my lab is that we live in a world that is 3D and dynamic. So it has a lot of people that are interacting with each other and the environment. Because of this, we've been looking at a lot of problems of how can we understand what people are doing in 3D from a single image and recover their geometry and body pose, with a specific emphasis on making this work on real images in the wild with lots of clutter and occlusion, or video, so that you can replace for the marker, this would be a markerless motion capture system that would be useful for many applications like robotics and also in arts. Now, of course, we're starting to think about how can we add appearance to these digital people so that we can import them into our virtual worlds, and also how to control them so that they can move around and about in the virtual world. But today, I actually want to talk about slightly different directions. Tomorrow, I'll be talking about humans in the tomorrow session. Today, I want to talk about this concept of capturing reality that we're super excited about. So this is a painting from 45,000 years ago. This is the earliest paintings of people. And we drew this picture of a hog that we were hunting. Over 45,000 years, we got much better at painting, and we figured out how to do perspective effects and even model the lighting effects to capture the reality of that day. Of course, this led to photograph, and then to the development of film. And these are actually the mediums of reality capture devices that are in our phones and every day. But these devices, mediums, drop a significant aspect of the reality that it is 3D and dynamic. So what kind of 3D capture devices exist? Well, computer vision people have been working on structure for motion for a very long time, which you can find in your Google Maps, like today. But this is not really that accessible. Maybe Google can do this. So what is the next direction? So what we're thinking about is the direction of, first of all, photorealistic 4D memory, because the world is dynamic in 3D, so we want to be able to capture motion in 3D too. So here's a really cool cinematic short made by a VFX artist. So he went to Australia, he really liked it, so he took a lot of pictures of all of these trees and the leaves, and all of this is recreated in Unreal Engine. So none of this is real. But it's beautiful, and it really captures the essence of being in Australia. But of course, you needed to be a professional VFX artist, and so we want to make this casual. And so the goal is doing casual photorealistic 4D memory. This kind of concept has been around in pop culture for a lot. So if you're a Star Trek fan, you might think of Holodeck, or more younger generation, Harry Potter, where you can take your memory and you can revisit it with other people, or Oasis from Ready Player One. And so how is this different from structure for motion? So we've been studying this for a very long time in computer vision. The term structure for motion was coined by S. Ullman in 1979. And this is really developed into a very mature software. So what's the difference? So the difference, I think, is that this new direction is going to have a lot more emphasis on photorealism as opposed to the previous approaches really cared the geometry. Now we just want it to look good, but if it looks good for many different directions, it will also have good structure. Related to that, we want this to be immersive and not just partial, so that you can really look around and feel like you're there. And of course, the world is dynamic, and there's lots of things moving around, so we want to be able to capture this or be robust in motion at time of capture. And directions like this will have immediate impact in content creation, in virtual worlds, or gaming, or empowering artists. I'm also really keen on digital conservation of nature before it goes away. And the ability to capture nature also has a lot of cool application in vertical analysis of forestry, which is really important for wildfire. It's very relevant to us in California. Another really, really impactful direction, I think, is this of immersive news or storytelling. So New York Times have been doing really cool series of journalism where they fly these drones at sites to tell us stories. So if this kind of technology was available in today's geopolitical situation, I think it would be really, really impactful. Of course, like Dieter talked about, the ability to perceive the world in 3D will have immediate impact in having robots interact with our everyday world. Okay, so why am I talking about this? I think it's because there's this direction called neural radiance field that came out from Berkeley 2 years ago. And this approach is able to capture a photorealistic world from images and let you fly around in this world. And this has really led to a large array of research following in this direction. So without getting really too deep into the details, a NeRF is a neural scene representation that you optimize from lots and lots of image representations. For every single pixel, you shoot lots of rays, and you ask this network, what is the color and the density of this particle? You can integrate that using some volumetric rendering equation, and you want to make sure that can reconstruct the observation you have. So that's how it works. It's all great, but the problem is it's not very practical. NeRF requires lots of captures. Training takes a day. And most significantly, rendering NeRF takes 30 seconds a frame, which makes it not very applicable to anything that you want to do in everyday scenarios. So that's what we've been looking at. And so we've developed approaches that make NeRF real time and made it 3,000 times faster. So now you can almost deploy it on your device. And we also developed an approach to make it super fast optimization. So instead of taking a day, it will only take 10 minutes. Without getting too much into the details, we developed this new explicit 3D representations to achieve this. I can get into details in other talks. Here, let's just see some demos. So here are some real-time rendering of NeRF. And the nice thing is you can easily convert your NeRF to this format, which is great for visual debugging. Here are some results showing that, even though it's 54 FPS and much faster now, the quality is similar to the original NeRF. And here's the results on very fast optimization. Let's see if this video plays. This should play. OK. The AV person, can you click on this? This video gets clicked. So this is like a real-time side-by-side comparison of NeRF. You have to click on the, yeah, there you go. OK, well, if the video played, you would see that this thing optimizes much faster. It's unfortunate that this doesn't really. Please check it out on the website because it optimizes much quickly. Oh. OK, all right. Well, anyway, because it's very fast at optimizing, instead of taking a day, it only takes 26 minutes to optimize these scenes, which these videos are also not exactly playing, but you can find them on the internet. You can also capture a 360 scene. So this is the real Lego. Can you click in the video of the video? Because it will go as you do that. Yeah, like ahead of where it is. This is unfortunate. Well, you can check it out on the video, and you can look at these. You can remove the foreground and background, and you can feel like you're flying in there. OK, so this can be pushed also for larger scenes. So this is a new work that's coming up from the lab, presented at CVPR 2022, where my student went to Waymo and used the camera to reconstruct the entirety of San Francisco so that you can fly through it. And these approaches also able to capture dynamic appearance, like changes in lighting that happens in these cities. Another direction is also this of infinite worlds. So taking a single image, you want to be able to generate infinite content that you can explore. Anyway, so the goal is a real-time practical capture and synthesis of immersive dynamic scenes that hopefully you can put it on your device and explore your memories. We're working on this. I'd like to thank my lab and my collaborators, and looking forward to the discussions. Thanks.
Thank you. Thank you, Andrew. I wanna ask Chris Manning, does the Australia virtual tour look real to you?
Oh, it looked awesome.
Nostalgic. So next on stage, we have Gordon Wettstein. He's an associate professor of electrical engineering and by courtesy of computer science at Stanford University. He's also co-founder and chief scientist of Zin Labs and co-founder of Raxim. Go ahead, Gordon. Thank you.
Thanks so much for having me. It's great to be here. I'm going to use my own laptop just so I can play the videos. Okay, as somebody working at the intersection of electrical engineering and computer science, the metaverse is two things for me. It's developing technologies that bring digital experiences to physical humans like us, and also bring the physical world into these digital experiences. And we need to think about a human-centric approach to doing that. But to do that, we need to understand the user, because that's the most important thing. And you know, our visual system is the primary interface between these digital experiences and us as a user. So understanding how it really works and how we need to engineer systems is critical. We need to understand how the photoreceptors are distributed on the retina and what their sensitivity is in order to develop displays that can stimulate it at a photorealistic way and giving us perceptually plausible experiences. We also need to understand the way the lens refracts the world in order to help us see better, correct prescription, or help us get natural focus cues in VR, AR experiences. But we also need to think about sensing, especially low-power sensing systems that track things like ocular motion and eye movements in general to help us understand the user as they're exploring these digital experiences. So in my lab, we're working on these displays. We've worked a lot on different types of displays. And one idea that I like is this idea of the visual Turing test for displays. You know, when have we engineered a system that's good enough? Well, if we can present digital content next to physical content and the user cannot distinguish which one is real and which one is digital, then I think we have achieved our goal. But we're far away from that. As I was mentioning, low power eye sensing and just tracking pupil movements, eye movements, is really critical to giving us the best experiences and also engineering the systems. So I don't have enough time to really dive into technical details, but if you're interested in talking about new types of displays that fuel AR and VR experiences, perceptually driven rendering, or emerging eye tracking that operates at ultra low power, that's basically what I work on. But as I was saying, the second component to this metaverse is to digitize the physical world and populate this digital space. And how do we do that? We need to synthesize content. And what's better than a generative adversarial network to synthesize new content? GAN is typically trained using lots of real-world data. But if we want to generate 3D photorealistic content, well, we need to learn that from some data set, because our AI is only as good as our data that we can use to train. And there are a lot of data sets that have multiple photos of the same person, but they're sort of limited in the number of different identities, the number of different people, the number of different viewpoints. So it's not adequate to really train an AI to generate photorealistic people from these captured data sets. We can use synthetic data, but that's never going to be photorealistic. So there's this discrepancy between quality and quantity. What my lab has worked on over the last few years, and partly in collaboration with Jiajun and others, is to use large collections of 2D, totally unstructured 2D photographs from the internet to train multi-view consistent 3D models that can generate new people that don't really exist and also interpolate between them. So here's some results from an upcoming paper that we did in collaboration with NVIDIA, actually. So this is a person this is the results of a 3D GAN of an AI that can generate a 3D person. It's only trained on individual photographs, 2D photographs of 70,000 people or so that are scraped from the internet. And you can get a lot of diversity in these people. It's getting to the point where it's almost photorealistic. You can spot some artifacts if you look closely. You get these depth maps. Even though the algorithm has never seen depth, you don't need to scan that. And you get this large diversity of different types of people. And basically, you can now generate almost photorealistic people, but also cats or other types of objects, whatever you may be interested in, to populate this synthetic world. Okay, so we're getting closer to the point of bridging this gap between real and sim, just by virtue of being smart about how we leverage the large amount of data that we have at our disposal. And if you look at this field, 2D GANs have been quite common over the last few years, and we've been able to achieve photorealistic synthesis of faces, for example, other types of content for a number of years. But for 3D GANs, it's really uncharted territory. And just over the last few years, we've seen lots of people trying to do this, including ourselves just about a year ago. And the results just have been very far from being plausible. But just within the last year, for example, we've been able to improve frame rates to become real time. So it's actually useful for metaverse type applications. And in this world of GANs, we measure the quality of these generated images as the FID score. And that's come down quite significantly, almost to the point where we can compete with 2D GANs. So it's quite exciting that just within 1 year, we've made great strides. And that's one big area that's interesting for the metaverse. One thing to convince you that these are really no real photographs are these interpolation results, where you basically represent each person as a string of numbers, as a latent code, and you can interpolate between these latent codes and get these interpolation results of different people, both the appearance and also these shapes, and that just hopefully convinces you that this is really not real, but it's all totally synthetic, just learned from a distribution of real-world photographs so that the algorithm just generates these people. As I was saying, all of this works in real time, so it's becoming pretty good by now. Lots of work to be done, obviously, and this is only object-specific, so we need to start thinking about extrapolation, doing this for outdoor scenarios, just like Anju was saying earlier. But there's a lot of things that we can enable also with these techniques. Once we have a pre-trained 3D GAN, we can take a single photograph of a person that wasn't part of the training set. For example, here's one of our co-authors from NVIDIA, and we can now fit this latent space of the GAN to this person, which kind of looks like this if you visualize the convergence. And what we come out with is we can take a single photograph, a 2D photograph of a person, and we get a full 3D model of that person that we can now use as a digital avatar. And again, we're making great strides towards basically bringing AI into these traditional computer graphics and computer vision pipelines, which is particularly exciting for metaverse-like applications. So with this, I'd like to thank my group, my collaborators at NVIDIA, who were part of the EG3D paper, and also other group members. Thank you. I'm excited to discuss more.
Thank you. Thank you, Gordon. That was awesome. Okay, next, please join me in welcoming our next speaker, Jiajun Wu, who is an assistant professor of computer science at Stanford University.
Okay, yeah, thanks for having me. I'm Jiajun. So I'm going to talk about simulating a physical but human-centered world. So a lot of you here are familiar with all the recent advances in simulated or embodied AI. In particular, right, there has been a paradigm. I took a slide from this Facebook Habitat team, or now Meta's Habitat team, where there has been innovations in 3 fronts. The first is tasks, the problems I want to solve, like embodied QA or language navigation, and the development of physical simulators that support these tasks, and as well as the assets, the data they use, right? Especially here, people may think about the scenes that these simulators may support. Okay, you can see that a lot of exciting progresses in each of the 3 thrusts. But what is really missing here, or how can we really do better, Here this is an event organized by HAI, but I really believe and agree that what is really missing here is we will need to think about how can you make this more human-centric, in the sense that can we develop more human-centric tasks, and can we think about how we can develop more human-centric assets. So what does that really mean? Let me give you just 2 concrete examples in this short talk about how we have been advancing in this round. So let's first look at the tasks. There are a lot of exciting progresses, right? Okay, we want to do embodied QA or language navigation. But can we ask, why do we want to solve these tasks at all? Why do I want to come to this auditorium? I'm not coming here just for fun. I come here for a reason, to perform an activity, and the activity here is to participate in this panel discussion, which is really exciting. Right? So they are not end goals of of human life, and they're actually the means to the ends. So instead of sitting in front of a computer and we as researchers coming up with new tasks that we believe are important, is it possible for us to really consider a different bottom-up approach and look at what people are really doing? Right? So this is the motivation behind our effort called behavior, which is a benchmark for everyday activities, household activities in these virtual, interactive, and ecological environments. So here we try to simulate 100, actually now it's getting more and more, daily activities that people perform in their indoor scenes, and now we're also looking at other scenes, such as cleaning up a bedroom or packing a lunch bag. And these are the activities that we really care about, humans really do, and can we let robots do that, or can we let robots help people do that? Right, so the way we do that is we first really look at try to get a diverse set of ecological plausible activities. How we're looking to go to the Department of Labor website, look at American Time Use Survey, look at the activities that people really do. And then we go to the WikiHow website to look at how people do them. And then we ask humans to annotate what are the initial conditions and final conditions of each activities. So we took ideas, from task planning from robotics community, and we defined the initial conditions and final conditions of activities such as packing a lunch bag, packing lunch, in terms of these kind of symbolic predicates. For example, the initial condition of packing lunch, maybe water is in a container or a hamburger is in the fridge and stuff like that. And the final condition, what we want to achieve is, every hamburger or water, they're all in the bags and stuff like that. Okay. So this kind of symbolic predicate-based representation also allows you to sample varied and realistic environments in simulation, so that the robots or the embodied agents can be presented all these different setups and try to learn to accomplish the tasks. Now, for example, we can sample different initial positions of the objects, or different scenes. Here is an example if you may want to put books into a bookshelf, but the books can be in different initial configurations, and the scenes can be also different. Right. And also, you can populate the scenes in different ways, right? Okay, so these are the examples that we can present to you, for example, training an embodied agent to perform the tasks or to help people to perform the tasks. And not only do we want to come up with the task definitions, there's also the questions of how we evaluate them. And we'll also come up with a set of human-centered evaluation metrics that, of course, we want to evaluate how good we are, right? How many final predicates, the percentage of predicates in goal conditions has been satisfied, which is accuracies. Even if you cannot do it 100%, you may want to do 50%, or even the higher the better. But also you care about time efficiency. Are you doing it as soon as possible? And are you doing it in some sense human-like way? Are you achieving kinematic efficiency, which means, for example, you don't want to disarrange other objects that are irrelevant. You don't want to break objects. You don't want to put objects in irrelevant conditions, or you don't want to put on fire your house while just try to pack a lunch bag. Or you don't want to just move around doing random things, and finally you're lucky and you get things done, but you just wasted a lot of energy. Right? So you want to really consider all a set of human-centric evaluation metrics on top of these human-centric tasks. And partly as the ground truths, we also collected human demonstrations in VR, where humans are there are 500 human demonstrations where humans are presented a task in VR, where they're providing 2 possible guidances. One is either natural language description about what a task is, or highlighting the target object posed in the scene, and the target object in the scene that, okay, this is the book that I want to interact with, so I want to put it onto the bookshelf. And these demonstrations can really serve the ground truth, where you want to achieve and benchmark how models have been getting close to humans in all the metrics I just described above, but they can also serve as ground truth demonstrations in, for example, an imitation learning setup. Okay. So here's an example of how human-centric tasks are, instead of coming up with new tasks like embodied QA, which are also important, and there's a lot of exciting progress there, maybe we want to think about it, what are task activities that we really do, and can we discover and define those activities and use them to develop embodied AI agents? Okay, let me quickly switch gears and talk a little bit about our efforts on building human-centered assets. Here people may think about it as the scenes. Can we scan indoor rooms or all those auditoriums, but mostly household, apartments. But another important part of it is, can we actually simulate objects, right? But when we see an object, when we look at like a vase like this, now we understand it in many different ways. Of course, we care about appearance. We know how they look like, and you can, for example, imagine how the object will look like from a different viewpoint. Right. In computer vision and graphics, it is like novel view synthesis. Or you can imagine how the object look like from a different lighting because you understand its material. Right. This is like the task of relighting. But you also care about other things that just beyond the visual appearance. For example, you care about how the object sounds. Great, it works. Thank you so much. Yeah. And how it feels, right? You can touch it. Tactile feedbacks are very important, for example, robot manipulation, as well as how it behaves, the physical properties. What happens if you drop the vase onto the ground? It's probably going to break, or how objects are going to interact with each other. So when we're developing assets or used in these simulated embodied AI environments, you may want to consider not only the visual appearance, but also the multimodal aspects of it. So this is the motivation behind our efforts on Object Folder, which was published last year's Coral, but we have a newer version, which is larger and much better, and this is CVPR, which is a multi-sensory object datasets. And we build upon all the recent advances in neural rendering. So it's great that Kavita covered it a little bit in the morning, and then Andrew Gordon spoke about it more. So I don't have to cover the basics. But the main idea is very simple. That is, think about what really belongs to the object. Right. What really belongs attached to the object, which is the texture of the object, which is the material of the object, the shape of the object, the physics. And you can bake these object intrinsics into a neural network, like implicit representations, all the things that Gordon and Andrew has shown, that fantastic stuff. And you can query this neural network with extrinsics. For example, how would the object look like given a lighting coming from the right, I'm seeing it from the left? Or how the object will feel if I touch it at this particular position. So that you can do neural rendering, but not only for visual data, but also for auditory data and tactile data. So the benefit of this data set is now you have this unified, object-centric, multi-sensory implicit representations, and it provide easy access to the community as a standard benchmark for a number of tasks in vision, graphics, and robotics. Embodied AI. It is also platform agnostic, that hopefully we can integrate them with all those simulators. And here's a quick demo of the 1,000 objects that we're building. And here is a more detailed visualization of, say, 100 of them. It's harder to play the sound. It takes a lot of time, so I'll just quickly show the visual aspects of it. Just one final slide on applications it enables. For example, if you feel the objects, then okay, where the object is, and then can you actually use the tactile feedback to localize where the contact point is, which is often very useful when you want to try to get and grasp an object in the dark room. This is contact localization. Or if you touch the object, and can you integrate your tactile feedback, which is like give you sparse signals on object geometry, to put them together with the visual image so that you can do like multi-sensory shape reconstruction, which is also very important in a lot of robotic activities. Okay, so to summarize, we think these are just two examples about we think how human-centric approaches can be helpful in developing these embodied AI tasks, as well as the assets that are used for these simulators. And I think to summarize, we want to think about the research in simulation embodied AI should really take and think about this kind of human-centered approach, because we got inspiration from humans, and eventually we develop these approaches in the systems for humans to augment human abilities, to help humans. So we should consider these human factors at all levels. Thank you.
Thank you, Jiajun. Our next speaker, if you watch the movie Social Dilemma, you'll know she's a star in the movie. So our next speaker is Anna Lemke. She's a professor and medical director of addiction medicine at Stanford University School of Medicine. Welcome, Anna.
Thank you. I'm just going to stay seated. Is that okay? Okay, great. Well, I'm excited to be here. I mean, it goes without saying that this is an incredible burst of creativity and innovation that makes me feel really old, but very, very excited for all of the amazing work that you all are doing. Dieter called his talk, Why I'm Excited by Simulated Environments. And I guess if my talk had a title, it would be Why I'm Worried About Simulated Environments. And I based that really on my real-world clinical experience, seeing consumers of these digital products coming in. And of course, as a psychiatrist, I'm going to see the potentially most serious bad outcomes. I'm not going to see all the wonderful examples of how people are thriving, but I do think that the sort of negative outcomes of this amazing technology is something that we obviously also need to pay attention to. So let me tell you a little bit what I've been seeing over the past 20 years or so. I've been seeing increasing numbers of individuals coming in with what appears to be full-blown addiction to consumption of these digital products, from online pornography to video games to social media to you name it, whatever's on there. And what I've seen is that the kind of natural history of these addictive behaviors to these digital products follows a very similar trajectory to addiction to drugs and alcohol. People usually start out using for one of two reasons: to have fun or to solve a problem. If it works for them, they return to using that product, and eventually they find that they're using it more and more and need more potent forms or more of that product or that drug. I'm just going to use drugs very broadly in order to get the same effect. And over time, that drug then becomes very central to their lives. There are consequences for their use. They're giving up other behaviors. They're engaging in ways that are orthogonal to their values, hopes, dreams, and goals. And essentially, they then have a difficulty stopping their use even when they want to, and even when they recognize that the behavior is problematic. And what we know about the neuroscience of addiction is that anything that's addictive will release dopamine, our reward neurotransmitter, in the pleasure circuits of our brain. And the way that our brain then compensates and responds to that spike in dopamine is actually by downregulating our own dopamine production and our own dopamine transmission, not just to baseline levels, but actually below baseline levels. So we go into a dopamine deficit state, and that probably happens instantaneously. And of course, that dopamine deficit state is an aversive psychological state. The universal symptoms of withdrawal or dopamine free fall from any addictive substance are anxiety, irritability, insomnia, depression, and craving. And so we have a natural instinct to want to grab for that drug again, not really even to feel good, but to stop feeling bad. Over time, with repeated exposure using the same or similar drug, we essentially reset our hedonic set point. So now we're in a chronic dopamine deficit state. And even when we're not using, we're walking around in that chronic dopamine deficit state that is essentially akin to clinical depression or anxiety or insomnia or what have you. And so our focus has narrowed. We have less ability to take joy in other activities, in more modest rewards. And we're very, very focused on going back to consuming that drug again, now not to get pleasure, but just to restore homeostasis or a level balance and feel normal. And so what I'm seeing in my clinical work is increasing numbers of people coming in reporting addiction to video games, to pornography. And people debate whether or not you can really be addicted to a behavior, but all I can tell you is that the natural history is identical. And when we look at that construct through the lens of addiction and we intervene as if it is an addiction to a drug, people get better in the same way that they get better to drugs and alcohol. And how do we intervene? We ask for a period of abstinence long enough to reset brain reward pathways. So patients come in with pornography addiction. And by the way, let me say that the numbers of these patients have really spiked beginning in about 2001, which coincides with the advent of the smartphone and the 24/7 digital access. In addition to needing to spike dopamine to be addictive, the other things that make something addictive are quantity. So the more you use a drug, the more likely you are to get addicted to it, right? Potency, the stronger the drug, the more dopamine it releases, and the faster it releases that dopamine, the more likely you are to get addicted. but also novelty, right? If you can take a drug and then just slightly make it a little bit different than the drug you saw last time, that really triggers dopamine. So access, quantity, potency, and novelty. And of course, the simulated world does that just beautifully. So patients will come in, they'll be very depressed and anxious. They'll say to me, the only reason I'm spending all of my waking hours playing video games is because I'm depressed and anxious. If you could just solve that problem, I wouldn't be so compulsively engaged in being online. And I say to them, well, I hear you that your subjective experience is that you're self-medicating your depression and anxiety, but I would postulate to you that it is your consumption of this digital drug that's actually driving you into this dopamine deficit state, which is creating your depression and anxiety. So we do the intervention, we ask for a period of abstinence. On average, for people who are addicted, it takes 4 weeks of abstinence from their drug to reset reward pathways. Patients who are willing to engage in this, and let me tell you, it is terrifying for people to think about giving up their digital drug for even 24 hours in some instances, but when they're willing to do it for a long enough time, they will come back and endorse an incredible restoration of mental well-being, such that I have really become convinced that there is a very serious dark side, that people can get addicted to these behaviors, people are addicted to these behaviors. Now, the vast majority of people who use alcohol will not get addicted to alcohol. It's about 10 to 15% lifetime prevalence. So this is not something that the majority has to worry about, but we have to take care of our vulnerable minority, and it's also a spectrum disorder. I think we can all relate to being at least a little bit addicted to our devices. So addiction is something I worry about. Very quickly, 2 other things I worry about. Derealization. Derealization is the sensation that I'm not real and the world is not real. And this is a very common psychological syndrome that has been well known and described for a long time, that usually manifests when people are depressed and anxious. Even an acute stress reaction can make us feel like maybe I'm in a movie and things aren't real. I'm seeing more and more patients coming in who are spending enormous amounts of time in the simulated world, endorsing a kind of derealization and depersonalization, along with nihilism, this sense that if I'm not real and the world's not real, then maybe none of it really matters. And those individuals are often suicidal. Another thing I'm worried about is the disembodied nature of these simulated environments. So the ways in which we're all up in our heads and disconnected to our bodies. And I think we're really at this stage where we're now experiencing what I will call phantom body syndrome. You may be familiar with phantom limb syndrome. When people get an amputated limb, they still have that sensation that they have a limb even though it's not there. I feel like we're in danger of being so incredibly disconnected from our bodies, exacerbated by the simulated world, that people are going to get, and already are getting, signals from their bodies because their bodies have nowhere else to put those signals. And so we get much more manifestation of things like chronic pain syndromes in the absence of any organic explainable etiology for that pain, because people are not moving their bodies. And then, of course, one more thing, I'm sorry if there's a time limit here, is that's the infinite comparisons that make us all feel less than, that you get especially on social media, where no matter what you accomplish and how much you do, you go on social media and feel like you just can't measure up. And our minds really weren't meant for those types of comparisons. So I'm just going to close by saying that Anju, so interesting, but I was scared when you said, quote, we have to capture nature before it goes away, unquote. As if nature going away was an inevitable endpoint. Can you guys use your amazing innovation to make sure nature doesn't go away? Gordon, seeing those faces that you made up. No, Gordon, where are you? Okay. Did you not feel, the rest of you, because this is what I felt, both a thrill and a chill, right? Something very, very scary to me about seeing people being created that didn't exist before, giving this whole thing a kind of godlike quality, but is it a kind of a false worship? I'm frightened. And then Jaju, I loved how you started out by saying, why are we making this technology? To what end? To what purpose? But then I was disappointed when you went to talking about how we can use it to do things like pack lunches faster. And honestly, as a mother who spent a lot of time packing lunches, I appreciate that. But here's the problem. With this technology, we are able to get a lot more free time and not spend it on these jobs that previously took a lot of time. But what are we doing with our free time? We're playing video games. I mean, there are data showing there's been a mass exodus among young men out of the modern workforce. Where are they? They're playing video games. So we cannot look at this technology without asking the deeper existential questions of why do we want this technology and what are we going to do with it?
Thank you, Anna. So speakers from previous panels, aren't you glad you're not on Anna's panel? So as a reminder, we have microphones on the aisles. Please line up, queue up if you have questions. I'm going to start with one for the technologists on the panel to redeem yourself. Is that starting from Dieter and Andrew, Gordon, and Jiajun, very quickly, can you give us one example of a real-life application you'd like to see of your technology in, let's say, 5 to 10 years that truly excites you? One example, and let's see if Anna is convinced by your example. Dieter?
Yes, so from my perspective, and I think Anna raised some, of course, incredibly important points, so I totally agree with all of this. But I think coming from a robotics perspective, viewing these as kind of the training wheels for the future robots, I think is really also an exciting application. And these robots themselves, I think, can have very positive impact on society by, for example, helping elderly people in their home, helping in the healthcare sector, but of course also in industrial tasks and things like that. So I think training robots to be able to do some household chores that enable, for example, elderly people to spend more time in their home and not having to go, for example, to a nursing facility early on can be extremely beneficial.
Great. Andrew?
I think I am really excited about this aspect of capturing nature. And when I say it's going to go away, it's because I'm maybe from a generation that the long-term impact of global climate change is real and it's inevitable. And in a way, if you do capture, you can analyze them and maybe prevent these, forest fire and things like this. But this idea of taking a picture and conserving the moment of life and history, I think it does really resonate with me. And I do wonder if it's needed for digital consumption. I think I want it for digital preservation. And to be able to revisit it in future for historical context, and also sharing stories. I think those are ways that I feel like can positively impact our history, and then that's kind of what I'm excited about.
Digital preservation, I love it. Gordon?
Okay, I'm going to go back to some of this convergence of VR, AR, and robotics, actually, that Dieter touched upon. One thing that I'm really excited about is surgery, training surgeons, minimally invasive surgery. The Intuitive has this Da Vinci surgical system out there that's minimally invasive, and it's remotely operated by a specially trained surgeon. It helps people not to undergo a major invasive surgery. It allows you to have an expert performing a procedure or surgery who may be completely remote from you, and I think it gives people access to higher quality of medical treatment. And it's fueled by technology that combines robotics, VR, AR, haptics, and a couple of other things. And I think it's just something where, it doesn't matter where you live, you can get access to high quality surgical care, and that's something that I'm excited about.
I think there are maybe two things I can think of. The first is also assistive robotics, because a lot of the motivation behind all this work, including Andrew and I have been working on something. It's also about, can you see humans and then think about how you can help them, especially for people with disabilities and elderlies, because they cannot, do things as quickly or as easily as, maybe young adults. So I thought that would actually be very useful. And the reason that packing lunch bag is, first, it's important, and in this case, they can actually be useful, but also at the same time, this shows, we're pretty far from achieving. Now, even that is already very hard for existing systems, so we're not there yet. Okay, and the second thing I think might be interesting is, if you can easily virtualize like daily object or stuff like that, it may increase and I would say motivate people's creativity for collaborations. For example, a lot of think about if you want to design your home or apartment, you may have some creative ideas. You may see a beautiful sofa from a picture. You're like, oh, this is great, how it will look like in my room. And a lot of time you have to go to designers. Designers have to download 3D models and spend thousands of dollars, and communication is hard. So it may really help people to develop their own creativity and make their collaboration with those professionals much easier by having these virtualized techniques.
Thank you. Anna, do you want to quickly comment, or we?
Well, let's go.
Okay, let's move to a couple of audience questions. I think you were first. No, you're first. Thank you. Please introduce yourself and be brief with the question.
Sure. Can you hear me?
I think we can hear you.
Okay, great. So my name is Yusuf Rouhani. I'm a PhD student here at the AI Lab. Thank you for your great panel, very exciting discussion. I just wanted to follow on from some of the points that Anna raised. Very, very important points. Thank you. I really appreciate you being on this panel. But I was also interested in not just the psychological aspects at the individual level, but also the social aspects of this technology. So for instance, right now we're plagued by the issues of deep fakes and fake news and propaganda being propagated using these AI-based technologies. When we see a world where the deep fakes are intersecting with the metaverse, I just wonder who is responsible for helping us decipher what is true and what isn't. Is it the technical experts? Is it the psychologists? Is it the politicians? And what are we doing right now to move in that direction where we can tell people this is real and this isn't?
It's definitely not the psychologists and the psychiatrists. I can't tell you what's deep fake and what isn't. In fact, I'm so startled by how you can't tell. But it's a great point. This is not just an individual problem, it's a collective problem. And I think it even goes beyond the things that we talk about a lot, which are things like privacy and fake news, which are huge issues. But also I think you've got a huge issue of potential social norms, because what we already have in the metaverse is people going as their avatars and urinating on other people and assaulting other people and just basically doing whatever they want while divesting from the real world. So I think that raises some really scary potential moral consequences. Plus then you've got the fake news, then you've got the adrenaline, dopamine that comes from the herd mentality when you get the rush of having your extreme opinion validated by a million other extremists in the world. So it's a really fascinating and volatile and combustible mix of emotion and addiction and dopamine and morals or lack thereof, and then fake news.
So if you were in the earlier morning sessions, we've got Liz from Path.ai, Rob Reish. These are the people who are looking at who's responsible for technology from different angles. So by the way, I'm very proud of Stanford AI Lab students asking this kind of question.
Yes.
So kudos to you. Go ahead.
Hi, everyone. My name is Aditya Mohan. I'm the founder of Robotics Machines. We are building on-edge AGI to power machines that feel. I have a question for each one of you, and probably being objective, maybe better than being subjective. There's a movie that came out from Pixar called WALL-E, and at the end of the movie, they show that everyone is in their chair, everyone is really fat, they don't know the physical world. What is the probability, I'm not talking about possibilities, but what is the probability that that future can come in soon? So each one of you, just a probability out of 100%.
I really liked in the earlier session what Rob was saying, which is that you really need this to be regulated, and there's this kind of overall discussion of what was going to be happen. We're technologists that develop technology, and then it can be used in good ways and bad ways. Kavita said it, with great power comes great responsibility. So the probability of this happening is really how can we get together and govern all of these things, or think about the ways in which we can regulate all of this. But I think it is a real fear. It actually happens in many sci-fi. For example, in Ready Player One, a lot of people have given up, and then the virtual world is the only place they get to kind of enjoy. I think that kind of pessimism is something we need to be talking about it, but it's not just solely on the technology, is my thought that we need to work on it, and the technologist needs to be in on it, and I'm interested in this conversation, but yeah.
Yeah, let me go to Dieter, because Dieter, do you have a probability?
Let me unmute. I have given up on trying to predict such things with probabilities and timelines or something like that. So I'd rather abstain from that. And that is why we have these kinds of events, right? So that the technologists get the feedback from the general audience, but also from experts like Anna, right? And can inform kind of the research that we're pushing forward. And regarding also with the deepfakes, for example, I think it's important that while the community develops techniques that can generate these incredibly realistic images, that maybe similar related techniques can now be developed in order to detect these deepfakes, or maybe encode things in these images so that they can be detected and things like that. So I think it's more important to try to prevent these things from happening, reducing the probability. And again, I'll stay away from numbers here.
Gordon?
Okay. Interesting question. I would say people freak out when new technologies come around, and that's been the case for a long time. The British invented a great motto that says, keep calm and carry on. I think most of the time we learn how to deal with new technologies. One example is when the Lumiere brothers in France invented the movie projector, and they projected the first movie with people just watching it. It was this train arriving at this train station. You know, the audience would freak out and think that there's this train coming at them, and they would run over to the movie theater and just freak out, right? Nowadays we look at this and we're like, oh, it's just a movie, right? So I think we just need to, first of all, before we freak out about new stuff, keep calm, carry on, and understand these technologies. And it is part of our responsibility as the people developing the technology to also be aware of how you can detect it and so on and so forth. But, you know, let's not freak out just yet.
Judging, are you freaking out?
I think it's not, I really don't think that, as long as we keep talking to people from different areas like Anna, Rob, and we have come up with systematic approaches, to think about, to when we're developing new technology, to keep these problems in mind, and keep doing that even whenever new technologies come up. I don't think I'm freaked out.
Anna, did you hear the technologist say, as long as you're here, it'll be
right,
fine?
Right,
What do you
that's
say?
scary. That's really frightening. Yeah, I think it's my job to freak out on this panel anyway. So let me. My response to this query is, Karl Marx said religion is the opium of the masses, and I think that we're looking at a possible future in which the simulated world is the opium of the masses. And by that I mean I think we're looking at a big class divide and social determinants of health divide, in which the people who make these products and people who are wealthy and highly educated will probably use them less and less, or more and more judiciously, and people at the bottom of the socioeconomic ladder who have less privilege and less choice will be the greatest consumers of the metaverse.
Thank you, Anna, and thank you for the question. What did you say?
Will you want to try to with the probability?
Oh, my answer? That's not fair. I'm supposed to moderate.
Fair enough.
My answer would be the probability is greater than 0 if we don't take on collective responsibility. So we can elaborate offline. Chris, you have a question.
Yeah, I want to continue on this theme of physical versus simulated world, but in taking it in sort of a different direction to the one that Anna's been concentrating on. So Dieter, you started off by saying how interesting the simulated world is, even to someone who's a roboticist. But I guess you were then really concentrating on physics-based simulation. And I mean, physics-based simulation is great if you want to do something like industrial robotics or having robots moving around your plates in the kitchen when there aren't any human beings in it. But if you want to be more human-centered, I sort of kind of feel like simulated worlds just aren't very interesting because there aren't any very good simulators for human beings. And so from after your talk, I guess Angjo's then started and she showed these dancing human beings, and that seemed like the real world and just the kind of thing that you can't do in simulations. Now, of course, as the session went on, we saw those amazing artificial humans that are being generated by GAN-like techniques. And, to me too, the quality of those is truly amazing. But they're not actually really simulating human beings and their behavior, right? It gives you an amazing head that you can rotate around. And I think we're so far away from simulating human beings that I'm not convinced that simulated worlds are very interesting, certainly not for the kind of things that I want to do that involves humans and languages and things like that. I mean, are the prospects for broad use of simulated worlds actually that useful if what we want to be doing is improving things in the actual physical world?
Chris, your question is to a specific panelist?
Well, maybe Dieter could answer it first, since he's...
Not sure I can answer it, but first of all, I totally agree that simulating humans, we are far behind on the quality of that, right? And that is for practical reasons why we are currently focusing on the basic aspects of, we have 2 dogs currently at home, sorry about that. But that is why we're focusing on what you might call simple tasks of just picking up objects, moving them around and interacting with them, which for roboticists is actually not quite as trivial as it might look often for people who don't do robotics. But I think we need to solve these basic problems anyway, even if we want robots to focus on interacting with people in a natural way. And I think then we can move on towards like, okay, how can we get people into these simulated environments? And there are then these technologies like virtual reality, which might be a first step towards this. And also kind of maybe at the same time, many of the ways for which we generate motion for robots to achieve tasks, maybe we can use these similar techniques to simulate humans interactively achieving tasks and then jointly learning with these robots in simulated environments. And regarding the photorealism, you also said, I fully agree that at this point, we might be good at generating images, and Gordon's results on the 3D, of course, shape are really amazing. But at the same time, of course, that is not the sufficient or the really hard part, which is about generating things that behave like humans, right? And that is so much harder. And of course, from an AI perspective, also so much more interesting and relevant for human-robot interaction. And I think we are just beginning to move in this area. So it's very exciting, but also very difficult.
Great. Let me move on to another couple of audience questions. You in the back.
Yes, first of all, thanks to Stanford for hosting such a wonderful event. I missed a lot of morning talks. I am intrigued by self-supervised learning and reinforcement learning and the promise they hold for general intelligence. This conversation has been about simulation. You all have progressed to robotics and this kind of simulation. I'm still stuck in autonomous driving environment where simulation is a big challenge, where you have to put together large processors, you have to put together a lot of LiDARs and radars and other sensors. You have to add motion, you have to add environment, and then you have to add on top of it end-to-end machine learning, deep learning algorithms. Simulating that is challenging, to say the least. And I would not have asked this question if it wasn't for Stanford, where there's so much under one roof that you can actually give an answer. So my question to you all is, can your simulation research help make the simulation of autonomous driving in the light of self-supervised learning, reinforcement learning, volumetric rendering, and other ML algorithms any easier? Thank you.
Okay, thank you. Who wants to take on the autonomous driving question? Dieter, I think.
Oh.
Sorry. You work in a company that does that, so.
Yeah. The funny thing is autonomous driving is in some respects, actually, that's why I was focusing so much on physics-based simulation, right? In some respects, it's actually much easier than the kind of robotics tasks we are looking at, because in our tasks, you have to really, you physically interact with your environment, right? You grasp things, you have people right next to you and things like that, where autonomous driving is mostly just avoiding any kind of contact with things that are not your own car. But I think, yeah, we're making, I think all these, this progress is also percolating into the autonomous driving domain, that we can start really training detection system, training prediction models for how humans behave, and then maybe feeding that back into improved simulations of these environments so that we can train the behavior of the cars. I think all of this is actually happening and going on. And the same also in the more robotic setting, which is very related, of course, where where we see a lot of progress on deep reinforcement learning. Unfortunately, a lot of it still depends on having very good training examples and demonstrations, and that's also often a question of where do we get these from. But I think we are seeing some pretty good progress, also, of course, especially at NVIDIA, but other places, of course, do this as well, about simulating environments and analyzing scenarios in these simulated settings and things like that.
Thank you. Let's try to fit in a couple of quick questions. Go ahead.
Hi, I'm Mark Afius. I'm a Stanford alum and founder of Deliberate AI, where we apply multimodal machine learning to psychiatric and neurological health. So, Anna, I was kind of really appreciative of your kind of adding a contrarian view to the promise of this panel. But I can't help myself to also ask you the question of where do you see the role of this in actually supporting treatment for the kind of patients you see, specifically thinking of addiction and PTSD. And in that sense, like, what kind of things would you like this community to work on in order to support you in that?
Yeah, thanks. Gosh, what a wonderful opportunity for me to, put an ask out there. So I guess I believe that, in the healing relationship with other humans, that really that relationship is the key to everything good that happens. So if this technology could be used in a way to extend and leverage the meeting of real humans through space and time, that would be great. So not this idea that you would replace the healthcare provider, especially not the mental health care provider. And it's not because I don't want to be replaced. Trust me, I actually really do. I would love to be replaced at this point in my life and go home and do other things. It's that I really feel that we will never replace what one human can give to another in a kind of Martin Buber I and thou experience. That's not replaceable. But even since the pandemic, what my entire practice has gone online, except for the few remaining people who are still willing to come in. I go to my office every day, I'm there in person. People don't want to come in person anymore. I get it. How can we make that interaction as close to being in person as possible, including whatever the pheromones are that probably get transmitted between live humans in the same room? That would be great. And what I see happening already in the world of addiction, where everybody's got an app, right? I hear every week about a new app. But those don't really interest me unless they're a way to facilitate the human connection, real humans to humans. So for example, the exciting piece to me is peer recovery and mutual help communities that are exploding online beyond Alcoholics Anonymous and Narcotics Anonymous. And those communities are healthy, real, intimate, positive, can be, communities. So the kinds of technology that can leverage the deep and healing human connection.
Anna, when you said you want to be replaced, I was like, oh no, are you derealizing yourself?
Yeah, it happened to me many times already in my life, acute anxiety, derealization. But no, what I'm really looking for is just, to pass
Packing
it on
lunch.
to the next generation, packing my own lunch at this point.
Actually,
and going out in nature before it completely disappears.
Or go to Andrew's lab.
Yes, that's
to
right.
see
Or
it.
looking at her Australian simulation, that'll work too.
Excellent question. Can I follow up there 1 second? Is there a scientific study or result that establishes the connection between photorealism and addiction? Because you are speaking with the premise that the more realistic these simulations are, the more freaking out you are.
Right.
But there has to be a logical link in order to be worried about that.
Right. See, you're so logical. That's why you're in that job. So there is not, to my knowledge, scientific data, but what you have is clinical observation. And the natural history of the disease of addiction is you need more and more potent forms over time to get the same effect. And that's what we see with video games, right? And the levels have to go up. The initial level is no longer satisfying, or that graphic is no longer. The more real the world, the more vivid, the more colorful, the more lifelike, the more potent. Also, things like enumeration make things more potent and more addictive. The rankings, the number of likes. It was interesting. Chris talked about the fact that, well, he's really interested in a simulation where it could be very, very lifelike, right? Which I thought was interesting. But again, that's the thing that I'm, worried about, where what happens on social media is you take something that's essentially healthy, which is wanting to connect with other people, and you distill it down into its addictive essentials, right? The ways in which we can control it, the ways in which we can seek more potency. Also with pornography addiction, the natural history of that phenomenon, people start out with vanilla toast pornography, however you might define that. And over time, that doesn't work for them. Then they're looking at very deviant images. Then they're going into chat rooms. Then they're connecting themselves to, electrodes and having other people control it. So this is just the natural history observed through phenomenology in clinical work.
I feel like there is opportunity for actual research.
Yes, that we need real scientists, actual researchers to do this, not me.
No, but great hypothesis. And okay, we've got at least 2 or 3 audience questions. Please go ahead.
Hi, my name is Jorge Cueto, and I'm an alum of the computer science department, so it's great to be back for this event. I just finished reading the book, The Beginning of Infinity by David Deutsch, and in that book, one of the ideas that's discussed is that so much of progress throughout human history comes from the fact that we develop new technology, that technology brings about new problems, but then we as a society maintain an optimistic outlook that enables us to develop solutions to problems that we ourselves created through new technology. So there's this cycle of new technology being developed to address problems created by new technology. My question is, what do you see in this field at the intersection of AI and simulated worlds as something that you are very optimistic about for the future? What are you most optimistic about in terms of the potential of this field for addressing existing problems, or whether that's in the field itself or in the broader world as a whole?
We had a version of that question earlier, but maybe just quickly highlight what are you most optimistic about?
I guess the capturing of the memory so that you can go back to it. And, during COVID, this actually did hit me because it's like, oh, what was, New York's, Times Square look like before COVID? Maybe that's something we will never get back, or we will. Or also, of course, unfortunate incidents, or the situation in the cities in Ukraine, like, what do they look like? If you could, preserve those things, I think that is very impactful.
Gordon?
I'd say just bringing people together that wouldn't normally physically meet is one of the great promises of, I would say, any social media right now, but even more so for the metaverse in general. I mean, I used to play video games, just going back to some of these comments, and I don't think I ever got addicted to that point, but I think there was an inflection point where video games were originally just for a single person or 2 people to play with when I was young. But then there was this influx of massive multiplayer games online. And I think that was an inflection point where you actually had a lot of real people in that same simulated environment. And the AI was basically just simulating the background and some of these things. And, I think that created a lot more of an addictive factor. Actually, what I saw in other people, I kind of stopped playing then. But I think it's also a great promise of bringing people together and across the world. And yeah, I think that can be beneficial in certain scenarios.
I think it's actually maybe the awareness of the importance of interdisciplinary research. So not only just computer science or other engineering or science disciplines, but also the discussion, just like we see today with all the psychiatrists or social scientists. So when I say as long as we keep talking, doesn't mean just keep talking. It's really about as science people who develop technology, we're really aware, we totally agree with the importance of all these issues, and then we're willing to learn from people from different disciplines. Then we will be more responsibly when we're developing these technologies. So that's why I feel like, in general, I'm more optimistic, hopefully. Yeah.
Yeah, and I love that frame. I'm going to look for that book. But I would sort of go back to what I said about Jiaju originally, which is I think that this technology will force us to ask some of the existential questions about meaning and purpose, and about spirituality that I think we've been too busy in a kind of a way to pay attention to for some time, and that now we will have so much leisure that we're not using very well right now, I would say. We're either playing video games or we're going to war and bombing people. So I think, to force us to think about, wow, like what should humans be doing now that we don't have to live at a subsistence survival level and we can, press a button and get something that we need to eat? What should we actually be doing with ourselves? So I'm excited about that, what people will come up with, and I am optimistic that we will get there.
Dieter, do you want to add what you're excited about?
Yeah. Just as I said in my presentation, as a roboticist, I'm really excited about the potential, like how these environments can really help us train these robots in the future. And otherwise, I also, of course, share many of the concerns Anna has, and I hope we can mitigate these through good research in this area too.
Thank you. There's a question in the back. Thank you for your question. Yeah.
Thank you. Professor Lee, I'll ask you to translate this across the speakers, but what really is interesting to me is it's been a great opportunity, and thank you all for sharing your view from where you are with all these different technologies that we've heard about today, both the actual technology developing and the different fields that are coming in to help connect the humans and the machines. As far as the human-centric part, we're here together for the first time for a lot of us. And we still have Professor Fox in the video. Wouldn't have been like that a couple years ago. Where are there fields either on the science and technology side or on the more social, learning science side to connect this missing piece to have more of a realistic experience, to have the serendipity, to have more empathy so that can it be healthy to be in these simulated environments? If I could ask you to help us look at other fields beyond where you are, and where there's some other cross-discipline efforts maybe that can help us watch for where there's innovation there that'll help us get to that more empathetic experience.
So your question is, can the speakers articulate existing interdisciplinary research that's happening right now?
Mm-hmm. I think technologies we haven't talked about or different fields that we might be surprised that they're thinking about.
Right. Anyone?
I can speak a little bit to the 3Dification of animals, actually. We're organizing a new workshop called Computer Vision for Animals, where we have lots of interdisciplinary research with ecologists and neuroscientists who are studying animals to understand their behavior. And if you can use these computer vision techniques to perceive the poses of animals in an unsupervised or self-supervised way, that would have a lot of impact in this direction.
That's wonderful. That's wonderful.
Yeah, I think one of our colleagues, Jeremy Balinson here, would probably have a lot to say about empathy, which is a really great topic. But I think the simulated worlds offer an opportunity to bring anybody in anybody else's shoes, right? So if you can create a simulated environment that feels realistic, you can become anybody else and see the world from their perspective. So for example, Jeremy was working on this project where you can be a crab on the floor of the ocean and experience the acidification of the ocean and how everything around you dies firsthand from the perspective of the crab. And I think that's a very powerful thing to do, because you can, help anybody understand what it feels like to be in somebody else's shoes in a much different and more immersive way. So I think there are a lot of opportunities with these emerging technologies to create empathy in different ways than traditional media.
I thought behavior could be a very nice example of interdisciplinary research and how the values. It is something actually I forgot to mention in the talk, which I should, is it is effort with multiple PIs across a lot of departments, with Fei-Fei a very important role on building this thing together. And we have people from computer science. We also work with people in psychology, understanding how people really behave in those environments. And now we're really expanding it. We also work with economists, who I saw is sitting down there, understanding, for example, what are the activities that humans feel most valuable about. They will want some assistant or robots to help them with. And as well as how it will really impact and help people, especially like, for example, elderly people in household environments, and which are the activities where the assistive robots was most helpful and benefit. I think a lot of these really benefit and learn a lot from the collaboration with social scientists and psychologists.
Dieter, do you want to add anything?
Yeah, so for example, the robotic side is of course also a natural interdisciplinary with people from the medical community. For example, a colleague of mine, Sid Srinivasa at UW, he's working med school on developing techniques, for example, for feeding people with physical disabilities, and also very interesting work going on at Georgia Tech, for example, Charlie Kemp, again, helping people with physical disabilities to give them some more independence back to their life.
Chris, you have a question?
Maybe since getting near the end, I might ask Anna a question, give her a chance to expand on her optimism. I'm sure there are people in the audience with young kids who are dearly hoping that their kids don't end up in your office.
Right.
Well, it's too late for your advice to be useful for me, but if I briefly report on my own kids, when our kids were young, we actively kept them away from technology, and we sent them to a school where they played outside and did crafts and learned as little as possible of formal education. But despite our best efforts, the truth is our kids these days appear to live their lives mainly online. So how do you see building a better future that, we know that GPUs aren't going to start getting slower anytime soon. We've got people working on that in the audience. How are we going to build a better future?
Well, the reason I'm optimistic is because I think that young people today are slowly coming around to the realization themselves after some years and many, many hours online that it actually doesn't necessarily lead to human flourishing. So for example, my teenage daughter is not on any social media, and she says that her friends who are on social media say, I really wish I could get off social media. It doesn't make me happy. But of course, their whole lives and their identity in many ways, the social network is on there. So my optimism lies in more open discussions about the ways in which these digital products can be exactly like drugs, especially for certain vulnerable individuals. And so having these open discussions, and then I do really feel strongly that we have to cut back our consumption, that it's not just what we consume or somehow the quality of that experience, or that, we're being creative online. All that's good, but I think there has to be a tempering of the actual amount of time that we are spending online. And that is what I communicate to my kids and to parents that I work with. And I think that a food analogy is not a bad one. Like, you can't stop eating food. You would not want to stop eating food, but you would not want to have ice cream for breakfast, lunch, and dinner, right? And if you were prone to overeating, you might want to think about certain categories of foods that you couldn't eat, or you would want to think about intermittent fasting. So to me, we have to come to some sort of reckoning around sort of digital etiquette and what makes sense, and also reinvesting in real life, because the truth is, the more time we spend online, the more impoverished our real experiences actually become, so that you have a family dinner and you say no devices, and then people don't have anything to say to each other. Well, teenagers don't want to talk to their parents anyway, but there's even less to say, than there normally might be. And yet, if there's a kind of an understanding that devices will not come in during that period of time, people do then re-access an ability to be present in the moment and interact in the moment because they're not constantly individually anticipating when they're going to next check their phones. And that does change, the emotional experience. So it wasn't a very good answer. There's no easy answer, but it's the dialogue and the recognition that it's not just what you do online, but it's actually the amount of time that you're spending there.
Thank you, and I apologize to the audience who didn't get to ask their questions. Please email us. We will take your questions and distribute to speakers. But in the meantime, please thank our speakers again. Thank you. All right. As our previous panel speakers move down stage, let me welcome our next keynote speakers. I would like to welcome on stage Professor Kunle Olukotan. He's the Cadence Design Systems Professor in the School of Engineering and Professor of Electrical Engineering and Computer Science at Stanford University. Kunle is well known as a pioneer in multi-core processor design and the leader of the Stanford Hydra chip multiprocessor research project. Kunle founded Afra Web Systems to develop high-throughput, low-power multi-core processors for server systems. And it is the Afra multi-core processor called Niagara was acquired by Sun Microsystems. This Niagara-derived processors now power all Oracle Spark-based servers. Kunle recently directs the Stanford Pervasive Parallelism Lab, PPL, which seeks to proliferate the use of heterogeneous parallelism in all application areas using domain-specific languages. Earlier this morning, we already touched upon topics of AI and chip design, including privacy and other aspects of AI. You're here for a treat for the next keynote speech. Kunle, welcome. Thank you.
Thank you very much, and welcome to this fireside chat. It's my distinct pleasure to introduce Bill Dally, who is the chief scientist of NVIDIA. He's been in this role since 2009. Before that, he was a professor at Stanford for 12 years and was chair of the CS department at one point. And before that, we lured him away from MIT, where he did lots of important research. He's most well known for the work he's done on supercomputer networks. He's developed key architecture and circuit ideas that power most of the current large-scale parallel computers. For this work, he's received a number of awards. He's a member of the National Academy of Engineering. He's a fellow of the American Academy of Arts and Sciences. He's a fellow of both the IEEE and the ACM. And he has the highest award given to computer architects, the Eckert-Mokley Award. So please help me welcome Bill Dally to the stage.
Thanks, Kunle. So to start our fireside chat, I'm going to give you a brief presentation on what gets me excited these days, which is making hardware for deep learning. All of the great things that you've heard about that fire AI are really made possible by the hardware we make. And I think this is a slide that was really similar to one that Ilya had earlier, where he talked about sort of the 3 ingredients in his recipe for AI. I like to think of it as somebody who used to build race cars, as you need fuel, air, and spark to make something go. And the fuel and air were around for a while. That was the algorithms that all of this AI is powered on. Deep networks, convolutional neural networks, training them with backpropagation, stochastic gradient descent. The papers on those are all 1980s or earlier. They've been around for decades. The next, think of that as the air. It's been around for a long time. And then the fuel was introduced. And the fuel is large data sets. we had large labeled data sets, things like the Pascal data set, easily in the mid-2000s, say 2005. The missing ingredient, the spark that ignited that fuel-air mixture and really set off our current revolution in AI, was hardware fast enough to train a large model on a large amount of data in a reasonable amount of time. And reasonable for a lot of people was sort of order of 2 weeks. And so that happened for computer vision when Alex Krasinski trained AlexNet, sort of illustrated on the bottom here, using a couple Fermi-based GPUs. Since that point in time, progress in deep learning is gated by hardware. People would like to run even bigger models, train them on even larger data sets, but they're limited by what they can do in a reasonable amount of time, where reasonable now is, say, 3 or 4 months on 4,000 or 8,000 GPUs. And so we feel huge pressure to keep making the hardware that keeps this deep learning revolution getting faster every generation, because we feel like a lot of the progress in AI may stagnate if we don't. So let me start by giving a little bit of history. NVIDIA really started to get excited about AI around 2010, and actually the proximate cause was a meeting I had over a breakfast with Andrew Ng, my Stanford colleague, at Hobie's, where we talked about his finding cats on the internet using 16,000 GPUs as part of the Google Brain project. And as a result of this meeting, I got somebody in NVIDIA research, Brian Catanzaro, to work with Andrew to replicate that experiment on 48 GPUs. In some sense, democratized AI, so you didn't need 16,000 GPUs to find your cats. You could do it with a handful of GPUs and pretty soon just a few GPUs. And back then, we were working with things like the original GPU up here, Kepler, which really only had, it was not designed to do deep learning. It was designed for graphics and for high-performance computing. So the data type it had that was most suitable for deep learning was floating point 32. A couple years later, Google published their paper about their TPU, and they claimed all of their advantages were due to specialization. It turns out with multiplies, the cost of a multiply goes quadratically with the number of bits. So doing a 32-bit multiply is not 4 times more expensive than doing an 8-bit multiply. It's 16 times more expensive. And that difference accounts almost entirely for the difference between the TPU-1, which was int8, and the Kepler GPUs. And a lot of the evolution you'll see here over time has to do with getting data types more appropriate for deep learning. So once we actually knew we wanted to start using GPUs for deep learning, which was around 2010, 2011, it was too late for Kepler. It was already kind of cast in stone. We started doing 2 things. We started making the data type smaller, and we started amortizing the overhead of the instruction. So the next data point on here, if my mouse works, I guess I have to get it down there. Yeah, I'm not going to worry about the mouse. The next one is our Pascal GPU. And Pascal introduced FP16 because we found we could train most networks with FP16. And we introduced a dot product instruction. So we can, instead of having the overhead of an instruction issue just 1 multiply and add, now it's issuing 4 multiplies and 4 adds. We get to amortize it over more arithmetic operations. We made even more progress with Volta, where we introduced what the marketing people called tensor cores, what I think of as instructions. They're half-precision matrix multiply accumulate instruction that now amortizes that cost of instruction overhead over 128 arithmetic operations, making it essentially negligible. It turns out more than 80% of the energy at that point is actually going into doing the math, not into fetching the instruction, decoding the instruction, fetching the operands, or storing the operands. All of that overhead is now less than 20% of the operation. With Turing, it's the one that's down on the side, but where it says int8 IMMA, we introduced integer multiply, matrix multiply accumulate. This is now doing 1,024 operations with a single instruction, making the overhead even smaller. We now have the data type really matched for doing inference well. The next step going up to Ampere, just a couple years ago, is we introduced sparsity. So my former PhD student Song Han and I kind of rediscovered sparsity. It, like many things, had been around since the 80s as well, and published a paper about it at NeurIPS in 2015. But it wasn't really until we came up with the structured sparsity of Ampere that we came up with a way of harnessing it in a way that really gave dividends. There are lots of things you can do to do fewer operations with the sparsity, but you introduce a regularity that winds up eating all the energy you would have spent on those operations anyway. With the structured sparsity on Ampere, we get a legitimate gain from the sparsity. And then finally, we just announced Hopper, shown at the top here. and it introduces an FP8 data type and some optimizations for transformers. If you look at this progression, what you see it over a 10-year period from 2012 to 2022, we've improved the performance on inference by 1,000x. And this is during a period where historical Moore's law, what you get out of process technology, gave us maybe 2x. 2x of that 1,000 was due to process technology. The other 500 came from being clever. So one example of that cleverness is the structured sparsity. This sort of shows how it works. You start with training your network, and you get a set of weights, shown by the dense matrix there. We basically take the weights that are small and force them to be entirely zero, and then we retrain the network. We fine-tune it so the other weights can adapt to pick up the load from the ones that we've zeroed out. We then compress it by just basically throwing away the zero values and adding a little index vector that says which ones the non-zeros are. We use that index vector to fetch just the activations that correspond to those non-zero weights. And now we do what's essentially a dense matrix multiplication, but it's performing a sparse calculation, and we scatter those output activations back out to where they belong. And this winds up giving a 2x for that 2-to-1 sparsity, and almost every neural network can be pruned 2x. Actually, a lot of them can be pruned to like 10% of their original density. The GPU we just introduced a couple weeks ago at GTC is Hopper. This is the end of that 1,000x gain. It has a petaflop of TF32 performance, which the most difficult neural networks need. Most of the neural network can actually be trained either at twice that rate with FP16 or bfloat16. We support both formats, or even at FP8. There are actually a lot of networks, now that we understand how to scale things well, that can be trained with FP8, which is why we added it to Hopper. And for a lot of inference, we do it at int8 or even at int4. The memory system here is 3 terabytes per second of HBM3, 80 gigabytes. And two things are in here. One, the transformer engine. It's interesting how fast technology for neural networks changes. 4 years ago, everybody was using recurrent neural networks for these language models. And then the attention paper was introduced, and all of a sudden, everybody is using transformers. The world just pivoted in a matter of a few months, and everything changed. So we now support that very well. And it's actually a little bit orthogonal from deep learning, but I'd done a lot of work on bioinformatics, and so I defined a set of dynamic programming instructions that wound up actually making it into Hopper through a very rigorous plan of record process. One nice figure of merit against which you can compare things is how many teraops per watt on inference it achieves. And Hopper achieves at int8 or FP8, for that matter, 9 teraops per watt. And I'll mention that a little bit when I come to talk about, I'm going to skip over that one, accelerators. So this slide illustrates what I meant about amortizing operations. And it really sort of illustrates that there's a smooth continuum between having a programmable engine and a dedicated accelerator. With programmable engines with very small instructions, like back in the Kepler age, we basically had a half-precision floating multiply add instruction, the biggest instruction we had. Normalizing to 45 nanometer technology, that consumes about 1.5 picojoules every time you do a multiply add. The overhead of fetching an instruction is 20 times that much, about 30 picojoules. And so there was a 2,000% overhead, and that was the cost of programmable engines at that point. By the way, the cost of a CPU adds almost 2 zeros to that. It would be more like 20,000%, 200,000% overhead. Introducing the dot product instruction, we amortize that over 4 multiply adds. Now we're only 5x overhead. And once we introduce the tensor cores with half-precision matrix multiply accumulate and integer matrix multiply accumulate, we're down to where roughly 80% and roughly 85% of the energy is actually going into the payloads. There's almost no advantage of specializing beyond that. You lose all the advantages of programmability in handling new models, new training techniques, and the like, and you don't really get very much for specialization. The other thing we had to do to really match the needs, especially these big foundation models, was to scale up. And so starting with the Pascal generation, we introduced NVLink, and we've built a series of NVLink and NV-switched parts with each generation. And so this is a picture of a cluster, what we call a DGX superpod, with 4,000 GPUs, 4K GPUs. And they're interconnected in these boxes of 8 using NVLink, and then between the boxes using InfiniBand. We actually now support NVLink connections up to 256 GPUs. And this lets people seamlessly build large training clusters and scale their performance up almost linearly. At the same time, we've been sort of improving GPUs each generation, 1,000x over this 10-year period. We've been experimenting with a lot of techniques using accelerators. And the idea is that what works in the accelerators will eventually, some number of generations down the road, intersect into the GPU roadmap. Some of our first experiments with sparsity were this chip I built with Song Han in 2016, the efficient inference engine. Joel Emmer of NVIDIA and Vivian Z at MIT built Iris at MIT in 2016, which introduced a lot of really neat work on how to optimize what are called data flows, the movement of data around the chip, to minimize the energy of delivering weights and activations to function units. We made another shot at sparsity in 2017 with SCNN for sparse convolutional neural networks. We built a chip in 2018 we called Simba. It actually got a number of best paper awards, and it introduced a lot of neat concepts, including building a multi-chip module with 36 of these little accelerator chips, each of which had 16 little accelerators on it in an organization somewhat reminiscent of Iris, and very efficient signaling on that organic substrate between them. Building a lot of these accelerators, we decided it was too hard to do by hand, so we actually built a tool that explores the design space of accelerators we called Magnet. This was described at ICCAD in 2019. And what it does is it searches the space of, how wide should your vector units be? How many vector lanes should you have for a processing element? How big should each level of the cache be? And how many levels should there be? Which tiling, what data flow should you employ to break up that 7-nested loop of the convolutions in a typical neural network, or for some of the transformer networks, it's breaking up a different set of loops. And in doing this, we wound up discovering a bunch of things. One is that we actually needed to introduce additional levels of hierarchy. So we introduced these weight collectors and accumulator collectors that are shown on the far right. And in doing all of this, we actually have a paper that was just accepted to the VLSI Circuits Conference. It'll appear this July, where on BERT, we now achieve, with no loss of accuracy compared to FP32, we achieve 120 teraops per watt. And so that, for us, is our new baseline that we compare things against for what to do. And one of the things we did to do that is, I talked about that whole progression of encodings, from FP32 going to FP16, eventually to int8 and FP8. What we've discovered more recently is it's not sufficient to encode each activation, each weight individually. We need to optimize the encoding of groups of them. And we were already doing this. We started out with the original scaling work we did, computing scale factors per layer of a neural network for both the forward and the back propagation passes. What we then did is we realized we wanted to do it not just per layer, but often per channel in each layer. And as we started dicing it further, we got better results. We kept dicing it. And we had a paper at MLSys last year where we described VS Quant, where we basically rescale every vector of 32 weights and every vector of 32 activations. And this lets us take, for example, encoding things with 4-bit symbols. We can take the 16 data points of those 4-bit symbols and scale them to exactly match the distribution of that vector, and not have to deal with matching a distribution of a much larger data set, which is harder to do. So where are we going in the future? Some of these directions can be derived by looking at where we spend the power today. If you look at this pie chart, a lot of it, the math is that big blue part. It's roughly half, and it took a long time to get it to be half. When we first started out, it was like 20%. And then the rest of it is largely data movement and memory access. So we want to do math better, and we want to do memory and data movement better. And one approach to doing math better is to go back to how some of us started doing math when we first went to college, and calculators were super expensive, so nobody had them. And you use slide rules. And slide rules are a way of doing math using logarithms. The numbers on a slide rule are on a logarithmic scale. And so by putting your 1 against a number you want to multiply by and going to the other multiplicand, you can read down and get the product. But you're essentially adding the two logarithms to get a product. And so the log number system is really great in a lot of respects. One really nice thing about it is it has constant proportional error. So integers have constant absolute error. And the problem with that is when you're representing very small integers, the proportional error is large, right? So if I'm trying to represent 1.5 with an integer, my error is 0.5. It's 33% of my number. If I'm trying to represent 1.5 using logs, however many bits I've chosen for a log, I get a constant proportionality. For these 4-bit logs, it winds up being I think 9% max error across here. And if you use 8-bit logs, it's better. And what you see is for small numbers, the error is small because you take small jumps. And for big numbers, the error is large. And this large error with small numbers of integers is particularly painful for neural networks because if you look at the weight distribution of a typical layer, it looks like this, where most of the numbers are actually pretty small. And so most of your errors are pretty large. With logs, you wind up with small errors for those small numbers, which works a lot better. Now, as everybody knows, adding things with logs is really cheap. Multiplying them gets really expensive. We came up with a really clever way to do that cheap as well, but I don't have time to talk about that since that timer is counting down rapidly. We actually experiment with a lot of techniques to move bits around less expensively. If I were to assign students in a classroom the task of moving bits around as expensively as possible, I think they'd probably come up with what most of us do, which is you represent 1 with the power supply and 0 with ground, and you swing full swing between the power supply and ground to send these bits around. It turns out you can do much better than that. And this is an example which we published, I think, in 2016 in ISSCC, where we make every electron work twice. So we basically split the power supply by having, say, ground is 0 volts and VDD is 1 volt. We'll introduce a ½ volt V mid. And every electron goes and it helps move 1 bit on the upper 4 here, then it helps move another bit on the lower 4. And by toggling back and forth between the two, we make sure the current draw of the two is identical. And that way, we don't actually need a regulator for V mid. It will regulate itself and automatically seek the midpoint. Now, there have been a lot of papers in various conferences, in ISSCC and VLSI circuits and the like, about analog and optical means of doing neural networks. And so we spent a while looking into this. And I think some of the most interesting research projects are the ones that come up with negative results, because you learn the most from them. And this was a negative result. What we found is that you could make the actual multiply in analog be extremely inexpensive. If you can put your weights into something that looks like a resistor, and you put your activation into something that looks like a voltage, you'll generate a current, which is the product of that, or the conductance and voltage. The problem is that ultimately you have to convert because you can neither store nor really reliably move data in the analog domain. And the cost of conversion, even if you consider the multiplies to be free, and they're actually not completely free, is such that if you wanted to preserve the accuracy of 8-bit integer, would cost you 1.25 picojoules per Mach. So remember, Hopper is 9. Our latest accelerator work is 120. The best you can get if you want to really preserve the accuracy is about 1. If you're willing to give up some accuracy by taking your analog to digital converter and actually throwing away the highest values and throwing away the lowest values, sort of clipping at both ends, you could probably move 2 lines over on here and get down to about a half or maybe even a third of picojoule per bit. But you're never picojoule per Mach. So you're now getting to maybe 3 teraops per watt. But you're never going to get to the 9 or nowhere even close to the 120. So we actually cut off that entire line of research we were doing. So before I run out of time here, I do want to comment on software. Because at some point in time, if you take your glasses off and squint a little bit and everything becomes very fuzzy, what you realize is that all of these different systems for doing neural networks are basically matrix multipliers with stuff wrapped around them. And if you do the right things, you can do a pretty good matrix multiplier. And hopefully you wrap the right stuff around it. But ultimately, it has to actually solve a problem for somebody. So we actually have more people at NVIDIA working on the software to feed these than we have designing the hardware. And it starts out at the bottom level with a bunch of system software, our entire CUDA programming system, a whole bunch of libraries that sit on top of that. And then there are libraries for deep networks, cuDNN, and for doing inference optimally with them, TensorRT, for serving inference models, the Triton Inference Server, for training models. And then we actually build whole vertical stacks. We build vertical stacks for speech. We build vertical stacks for doing video coding. We have really neat AI-based video coding that sort of exceeds all of the traditional H.265 and things like that approach to video coding. We have vertical stacks for autonomous vehicles, for robotics, and many other application areas. Because ultimately what matters to a customer is what is the amount of effort they take to take your matrix multiplier and get their application working on it. So we try to make that as painless as possible. So let me wrap up here. So GPU inference performance has been doubling every year. And this is due to a number of innovations. So better number representation, starting with FP32 and moving down to FP8. Amortizing the overhead of instructions over more operations. Sparsity, one thing I didn't talk about a little bit is plumbing. When you get to the point where you're doing 4 petaops on a chip, it's really important that you can provide the operands to those 4 petaops of arithmetic units with enough bandwidth to keep them all fed, or they're going to go idle. We've done a whole bunch of accelerators, most of which I sort of classify in the same realm as the analog stuff. They were failures from which we learned a lot and helped us ultimately move in the right direction. But we experimented a lot with sparsity, with tiling, and with number representations in these accelerators. And I think the way we keep doubling, because we feel a real need to continue doubling every year, is by doing even better with number systems, log numbers, encoding vectors of numbers, not just a single number, optimally clipping numbers to their range, exploiting sparsity even more than what we've done already with the 2-to-1 structured sparsity, circuit optimizations in both memory and communications, and there's probably another factor of 2 in process to be had. And so with that, I guess I will let Kunli grill me, and after that's done, I get to fly home to Lake Tahoe.
Thank you very much, Bill, for that really informative presentation about all the developments that have been going on at NVIDIA to make deep learning the force in society that it currently is. And it's absolutely the case that NVIDIA saw the direction early and started developing systems that could really accelerate the whole training and inference process. So, let me start by asking, you talked about how the rise of deep learning was really this closely coupled development of hardware accelerators and algorithms for deep learning, which had been around for a long time. And there's this notion that recently appeared on the cover of the communications of the ACM called the hardware lottery, right? And there's a notion that the reason that the deep learning models look this way is because that was what the hardware was good at, and potentially going forward, then the question is, how much do you believe that? How much are you driven by the direction that you see the algorithms go in, and how much are the algorithms driven by what you can do efficiently?
Yeah. Well, there's clearly co-evolution going on. I mean, a lot of the original algorithms were developed independent of GPUs, but then once GPUs became the dominant platform, I think there was definitely pressure for people to do models, at least at the higher end, that would run well on GPUs. At some of the lower end models, things like MobileNet and Efficient Net, were clearly more aimed at embedded systems and actually don't run well on GPUs for the reason that was a different target. But I think at the same time, GPUs have evolved as they see what people do with models. As transformers came out, there were a bunch of modifications made to GPUs to make transformers work well. The data types really traced what people needed to get their deep learning models to work well. And so I think over time, the two have co-evolved to it's at least a local minima, if not a global minima, in the energy space.
Mm-hmm. So, going forward, then you'd expect that you will continue to look at transformers, a good example, right? Mm-hmm. So you look at sort of what you did for transformers. Is that very specialized, or you think that has wider applicability? Or is it exploitable by a programmer who kind of?
So you're referring to the transformer engine?
Yeah.
Yeah. So what the transformer engine is really support for dynamic multi-precision. It will look at a set of weights and activations and make a decision on the fly based on the distribution of the data, whether it can use FP8 or whether it has to fall back to FP16 or BF16. And that's actually pretty general. I think that for any neural network layer, if you have the ability to dynamically scale it and choose data types based on that scaling, you could use that engine.
Okay, and that would happen automatically. It would be available in the cuDNN library, or it would be something that you'd have to exploit all the way to.
Yeah, most people use our, for training, use our GPUs within one of the frameworks.
Yeah.
And so most likely they would use it within a framework and not have to deal with, If you actually dig deep down inside the cuDNN models, a lot of that code is not really fit for humans to look at.
Right.
Although it's interesting because we actually generate almost all of it from high-level language now. We used to write a bunch of the kernels in assembly language, and then when the Volta generation was coming out, we were behind on it. And so I got a bunch of people to think about it, and we thought about, should we all drop whatever we're doing and start coding SAS, which is our assembly language for all these kernels, or should we try to be really clever and write a compiler that'll do that for us? And we decided to be clever and write the compiler.
Yeah.
And so we wound up with a really good compiler to generate all those kernels.
Right. So, a lot of the software story is, as you allude to, the story of sort of sophisticated compilation. And CUDA is an example compiler. How much of the sort of the benefit in the short term is going to come from sort of better compiler technology?
Well, I think a really interesting thing to look at is how performance numbers on the MLPerf benchmarks have improved over time on the same hardware. And I actually don't have the numbers in front of me, but if you go back and you look at, for example, when Volta first came out, it put up a number of MLPerf numbers, which we were really happy with because they were the best MLPerf numbers out there. But a year later on the same hardware, some of the numbers had improved by 2x. Now, some of that is better compilers, and some of it is also just programmers looking at the task and improving their code. And it's just getting, it's getting the overhead out at a bunch of different levels. We've already worked really hard at getting the overhead out at the architecture level by having big instructions like, HMMA and IMMA, but there's, that's sort of at the bottom level of doing the matrix multiply. You then look at things like, gee, I've got to do a batch norm, and I've got to do some pooling, and I've got a nonlinear function of other things in there. And if you schedule that wrong, you wind up moving the data back and forth to memory a couple times. And it's really easy to burn factors of 2. And I think if you really try to get to the optimum pipeline where you're doing the least amount of data movement, whether you think of that as a compilation task or a programming task, there's still a bunch of low-hanging fruit to be had.
Right. So in your talk, you focused a lot of on sort of the 1000x inference performance that we've gotten over the last 10 years. But if you kind of look at sort of where high-end NVIDIA GPUs are used, they're used mostly in training, right? So at least the high-end GPUs. So how do you view inference and training? And what typically happens, at least as I understand it, you correct me if you think the story is different, is that training gets done on high-end GPUs, which are good for doing computation on large batch sizes, and then inference gets done on CPUs where batch one is a lot more efficient, and you want low response time and low latency.
Yeah, so I think I think we actually ship more GPUs to do inference now than we do. They're not the same ones, but and one of the reasons is it's like more than 100 times more energy efficient to do inference on a GPU than it is on a CPU. So I think they're really important use cases for both, and they're different use cases because both the data types required and the memory footprint is different for inference and training. For inference, you can get by with int 8, and sometimes with the VS Quant, we can even get by with int 4 and some of the log formats, for inference. And you only need to keep the current level of activations around. Whereas for training, we need to keep all the layers of activations around so they're there for backprop. Otherwise, you'd have to recompute them to get the partial derivatives. And we typically need higher precision. We need at least FP8. We can actually train a lot of models now with good scaling with FP8. And sometimes we'll need FP16 or BF16. And a few really difficult models we need TF32 for. But in the talk, I focused on that chart with inference because the first time I drew that chart, which was, I think, right around when Ampere was announced, and I needed to sort of give a talk like this about Ampere. I happen to have all that data sitting right in front of me, but I could very easily write the identical chart for training, and I think it would be almost exactly the same factor of 1000x for almost exactly the same set of reasons. But it's interesting, we actually designed one GPU architecture, and then we specialized it a little bit, usually mostly in terms of sizing. Almost nothing else changes for the two, but the two problems are very different.
So there's some people, researchers advocating this idea of sort of continuous training, or at least episodic training, where you are constantly doing training and inference potentially on the same acceleration device. What might that mean for the sorts of systems that NVIDIA develops, right?
Yeah,
Given that you've already specialized for one or the other.
Well, no, like I said, it's actually the same GPU. So it's the same. What we've changed is sizing. By sizing, I mean the number of SMs.
Okay, so you're not changing the
right. So the underlying architecture is the same. Yeah, I would actually have to see the application to see. We spend a lot of time, instrumenting these applications and measuring them very carefully to decide, how to optimize the next generation architecture for each application. And so far, we haven't seen a real need to diverge training and inference. Although, quite frankly, it's all a question of what you're giving up for, to keep it a single architecture, because we do have more on-chip memory than we need for inference.
Right. Do you see sort of these deeply embedded applications where you need very, very low power and energy? You see the same sorts of, this is where you see the most specialization, the most accelerated. You see the same architecture working there.
There's a couple points. So we make devices ranging from H100, which comes in a bunch of configurations, but the high energy configuration is 700 watts.
Mm-hmm.
There's also a 300 watt and 150 watt configuration. Down to our Xavier and Orin embedded parts that are aimed at sort of 10 watt and 1 watt points to go into embedded devices. And when you get down to the really low energy points, we also have a deep learning accelerator that sits on there, and it offers inference for numbers closer to what we get out of Magnet than what we get out of Hopper.
Okay. So, you spent a lot of time in academia doing research, and now you're over in industry. So what advice would you give to people, academics? There's lots of you go to the latest computer architecture conferences, and of course, like everywhere else, it's all about ML acceleration and trying to speed up these sorts of algorithms, and presumably the goal would be to influence companies like NVIDIA. Are you being influenced by this research? What would you like to see?
Not really. I think the big ideas in ML accelerators, sort of at that scale, were published 5 years ago, and the work I see coming out more recently is pretty incremental and unlikely to have much impact on us or anybody else. I think what I would like to see the academic computer architects work on is what are the next big problems to accelerate. I think we've beaten ML to the point where it's hardly recognizable as a quadruped. And I think it's time to move on and look at something like SAT solving or fully homomorphic encryption. What are other commercially important problems that could be put into future GPUs? The way I think about a GPU is it's a platform onto which you can plug accelerators. We started out plugging accelerators for raster graphics, and then we did really accelerating for deep learning. Then we put in ray trace graphics. Now we have dynamic programming for bioinformatics. What's next? I would like really smart people to be thinking about what is the next big problem to accelerate, rather than trying to pick up a few % on small optimizations on ML.
Is this a forward-looking analysis, or is it looking backwards and saying, no, that's what we did? Right?
Oh, it's interesting because that's what we were doing, but we had to look back in retrospect to realize that was what we were doing.
Yeah. So, you talked about sparsity, and I'm a big believer in sparsity being the way forward. But if you kind of look at the structure sparsity that you had in the A100, it was kind of simple, 2, 4, and it seems like you didn't increase it in Hopper. Why? What about trying to exploit more interesting, more sparsity or more irregular types of sparsity?
Yeah, so I think it's a very productive future direction. So I've been working on trying to make sparsity practical since Song and I wrote the paper that was in NeurIPS in 2015. And it's surprisingly hard. It's really easy to reduce the number of arithmetic operations, but you introduce so much irregularity in doing so that it winds up being almost neutral on energy unless you're really careful about how to do it. So the fact that the 2-to-1 sparsity is really simple is what makes it work. Because it's simple enough that you can implement it without the overhead of the irregularity killing everything.
Right. Yeah. No, it's a real challenge. I think the answer has to be in more structure.
Right. But there's an opportunity to go beyond that. A lot of neural networks you can prune down to 10% or less in some cases, and we should be pruning the activations as well as the weight, so that then becomes dynamic pruning and introduces a set of complexity around that. Changing from frame to frame.
Right. So we've done 1,000. You have provided 1,000x in 10 years. You think there's another 1,000x to go in terms of ML, or as you said, should we move to something else?
Yeah. So
because as you'd assume that it's easier to get the benefits when you start.
Oh yeah. Yes. So back in the days where computer architecture was kind of driven by Moore's law, what was great is every generation you got a new process node, and with Moore's law and Dennard scaling, you got essentially 3x, 2.8, root 2 cubed. And it was free, and you could just do it over and over again. The problem with being clever is, once you played the card of, let's do matrix multiply instructions, that card's played and you can't play it again. And you have to think of what is the next card you're going to play. And I think we probably have the next 3 doublings. So that's a good 8x. Right. All it would take is another 3, and we'd be to 64, and then another 3, and we'd get there. But I think it gets harder, and I think there's likely to be a little bit of flattening out. Who knows when it's going to happen? Maybe it'll be after that first 8. Maybe we'll get another 8 after that.
Yeah. So let me change topics a little. So there's been a lot of interest in these large language models, right? These large language models called foundation models are the root of lots of interesting new products in banking, financial services, medical field, all sorts of things. But these models are huge. They take thousands of GPUs to train. They take millions of dollars to train. And they are kind of locking out smaller organizations, maybe academics from the game, because they're so big, they're so costly. So what was NVIDIA doing about, does this, on the one side you might say, great, the bigger the model, the more hardware, the more we sell, and this is all good. But but to some extent, there is the view that you talk to some academics, for instance, and they say, we can't play in this game because we can't get access to the amount of compute that it takes to actually train these models. What's NVIDIA's take on
there are a couple answers to that question. So the first is, it's not clear you have to train the model to play in this game. What's really great about the foundation models is they're sort of zero shot, applicable to a lot of problems beyond the ones they were originally trained on. And so with the models that are made public, almost anybody can take one of these models and do interesting work using the model. That's not the same as training a new model, but I think there's a lot of work to be done, using the model, applying it to a lot of different things. In terms of costs, I mean, we trained the joint project with another company. We trained Megatron, Turing, and LG, and I think it was 2,000 GPUs for 8 weeks. And so if you sort of calculate up, a number of GPU weeks, it was probably a few $1 million of GPU time to train that. And so, for a small organization, if you have something where training a new model would generate a lot of value, I think that's the kind of money that can be raised. I mean, as long as what you're going to get out of it is worth more than that. I think the bigger burden for a lot of people is getting the very large data sets, even though many of them are public, whether they train them on Wikipedia or Reddit or whatever public data set, accumulating that data and feeding it is actually almost more of a chore than doing the GPU training on the large model. And then if you look at many academic endeavors, particularly in experimental physics, a lot of them are way more expensive than training a foundation model.
One could argue that experimental physics isn't something that every corporation or every
right. But I mean, but it's a legitimate academic discipline, and what has evolved is a research support for the community of a certain level, and then the scientists basically sharing a few very expensive experimental facilities to carry out the experiments. And you could see something like that evolving for AI as well, where you'd have a few big experimental facilities that academics could submit the equivalent of an observing proposal for a telescope to make use of some of the time. I also see a real future with a partnership between academics and industry. As part of my role at NVIDIA, I wear two hats. One is the chief scientist hat, but the other is I'm senior vice president of research, and I run NVIDIA Research. And I have 12 people in NVIDIA Research who are tenured faculty at a university and simultaneously a member of NVIDIA Research. And it's a win-win for the university and for NVIDIA. And one of the ways it's a win is they get access to some very large supercomputers to run their experiments on. We see it as a win because they plug us into their whole academic institution beyond their own little sphere of research. We wind up finding, what Dieter, who is here, is 50% University of Washington, 50% NVIDIA, and we wind up getting a channel into UW through Dieter that's just extremely valuable to find out what everybody there is up to.
Great. So at this point, I'd like to open up the questions to the audience, and so please come to the mic, state your name, and give us your question.
Hello?
Oh, sorry, the guy in the back first.
Yeah, thank you. Great talk. So I have a PhD in electrical engineering from Stanford, so was the highlight of the day. So my question for Bill is, among the extended opportunities for GPU, and feel free not to answer the question, do you see hashing, given all the frenzy about crypto, like hashing today requires specialized ASICs to do it well? Do you see NVIDIA, or if you are going to do it,
Yeah, so it's interesting. So, for Bitcoin, you really need a specialized ASIC to do Bitcoin mining. For a long time, NVIDIA GPUs were the device of choice for Ethereum mining, and it caused us huge headaches because demand for GPUs would fluctuate with the price of Ethereum. And so the solution that we came up with was we basically put hash limiters in all of our current GPUs, and then we sell one SKU without the hash limiters, but also without a video port. And that way we can ensure stable pricing of GPUs for the people who want to use them for AI and gaming and scientific computing. And then the other set, we decide how much of our production is going to go to that, and its prices will fluctuate wildly, with the price of Ethereum. We've talked many times about whether we should, we certainly have the ASIC expertise. We could have turned out a Bitcoin chip. I personally, as an environmentalist, see throwing a lot of carbon into the atmosphere for no intrinsic benefit for mankind is a bad thing to do. Fortunately, the business people came to a similar conclusion for different reasons.
Thank you.
Yes, please.
My name is Aditya Mohan. I'm the founder of Robotics Machines. We are building on-edge AGI, artificial general intelligence, specifically to power machines that feel. I also have been in the semiconductor industry for a while, worked at Intel in 2016, came up with the term silicon is eating the software, which is very well the case right now in 2022. My question is not focused on big semiconductor company like NVIDIA or Intel, but on the startup scene. So I see two sort of companies. One is that are making, I would say, general purpose, even accelerators like Cerebras, Grok, Mystic, Cerebras, and so forth. And then the other is more application-specific silicon, and that's Tesla is a great example. Amazon, although it's not a startup, but they have their own silicon. Facebook has mentioned about that, and there's lots and lots of other companies. Apple is another example. My question is that in the next 5 years, I'm not 100% sure how to think about these general purpose accelerator or chip companies, because I don't see, maybe I'm missing something, but I don't see they could just survive on their own. They may get acquired by NVIDIA or Intel. I see more value here, as well as more value in bigger, more branded companies like NVIDIA or Intel or AMD in that respect.
Yeah, no, it's interesting. I actually am very worried about the health of the semiconductor startup industry. I'm a member of President Biden's Council of Advisors on Science and Technology, and as a member of PCAST, Lisa Su, the CEO of AMD, and I are actually running a study right now looking at what can be done to sort of reinvigorate the American semiconductor industry. And part of that is looking at startups and the obstacles they face. And the obstacles are pretty big. Depending on who you talk to, you'll come up with numbers anywhere between $500 million and $1 billion to make a full, state-of-the-art, 5 nanometer, digital systems ASIC. And so the question is, what markets are big enough to justify that expenditure? And right now, there's only one. It's AI, and that's why there are all these companies trying to make, general purpose AI chips. You should talk to him. He's the founder of one of them. And I think ultimately, there are too many. Too many wolves chasing, like one rabbit for the meat to go around to keep them all fed. And what I see as a much more productive thing is to try to build a semiconductor ecosystem where people can build specialized engines without that $500 million outlay. And there's actually a really nice set of ideas that have been forming by a fair number of people working together to build what a lot of people are starting to call a chiplet ecosystem, where a base ASIC can be done maybe by one of the big semiconductor companies, and there's a standardized interface, and somebody who has a really good idea, whether it's for a SAT solver or a bioinformatics accelerator, can with more like a $1 to $10 million investment, build the chiplet that plugs into that, and that could reinvigorate startups. Because right now, if you're on the finance side and somebody comes to you with a business plan that says, "Oh, I need $1 billion to get to my first viable product," unless that viable product is anti-gravity, it's unlikely that you're going to want to fund that.
And just one more simple question. So risk V is in that direction that you're actually talking about. How do you see that being sort of the standard for chiplets or the chip design or the cores?
RISC-V is an instruction set, so that's not really, a chiplet standard is actually going to be an interface standard that provides high bandwidth into the system SoC. I think RISC-V is nice in that it provides a kind of license-free microprocessor instruction set. We actually use it at NVIDIA. It's not exposed to customers in any way, but we have a bunch of little microcontrollers around the GPU that are now RISC-Vs. And it's a decent microprocessor article, but I don't think it's going to change the ecosystem of how startups in the semiconductor world work. But he should answer the question about all of these general accelerator startups.
So let me, ask a adjacent question, which is, if you have a bunch of chiplets, as you well know, the issue with actually, being successful in the marketplace has much more to do with the software and the other, and your go-to-market strategy and so on, than, just putting chips together, right? And so, how, even if you do have this infrastructure for putting chips together, how is that going to solve all the layers of software that you need? Bill says I'm a founder of a startup. I am, and even though it is a AI chip startup, most of the people we have in the company are actually software developers, right? So that's the question, and then I suppose the adjacent question is, are companies like NVIDIA going to open source CUDA to make these things easier? Probably not, right?
Thanks, Bill, and I'm happy to help. I belong to the startup world. We are also working on semiconductors, so if there's anything I could help, please, I will reach out. Thank you.
Next question, please.
Is it my turn?
Yes, please.
Oh, okay, sorry. My question is about the topic of sparsity that you're employing in designing the new chips. Yeah. And excuse me if this is a trivial question. I'm not a hardware person, but what are the potential problems that could arise? My understanding is that the programmer does not have access to that, and that's done under the hood. And for example, for debugging purposes, what can go wrong there, like during training, for example, and how can you actually address that as the programmer?
Yeah, so the way most people train with sparsity is you actually train dense and get a dense model, and then you sparsify it by, and there's a couple different approaches. Most people will simply find the lower valued weights and zero them. We actually use an approach where we compute the sensitivity of the weight to the output, and then zero the ones that have the lowest sensitivity, which aren't necessarily the ones with the lowest magnitude. And then you do a fine-tuning step, which is usually just a few epochs of training with sparsity. And it's kind of in the framework so that it's pretty easy to do and pretty foolproof. And in most of the cases, it just works. There's very little that can go wrong at this 2-to-1 level. If you start to go, when we ran a lot of the sparsity experiments, we were pruning much more aggressively. And there is a cliff you'll fall off of if you prune your model too much. Even after the fine tuning, you'll have lost accuracy, but you'll see that. I mean, and then we have to just not prune so aggressively.
So how would you know that it was due to that particular hardware provision that something went wrong?
It's not hardware. I mean, it's due to when you exploit sparsity, you're changing your model. You're moving from a dense model to a sparse model, and the loss of accuracy is not due to the hardware. It's due to the change of model.
So did I misunderstand that this was done at the hardware level to begin with?
We supported it at the hardware level, but we actually implemented it in software long before we put the hardware support in for it.
Got it. Yeah, thanks.
Another question, please. Yeah.
Hi, I like your views on the trend of ML for chip design, specifically the new research from Google Research about RL for floor planning for GPUs. I think they're TPU 4th edition. Yeah,
so I actually think very highly of the work that the team at Google has done. I think it's a really impressive result. We also have a big team working on ML for chip design, and ours falls really into sort of two categories. One is similar to the Google work, it's applying RL to actually do design, and probably the best result we have that was reported at the Design Automation Conference back in December is using RL to optimize parallel prefix circuits, basically carry chains and adders. And we've been able to come up with adder architectures that are better than any human has done by having, basically viewing it as a video game. Where do you put the intermediate, carry look-aheads in a 64-bit carry chain? And it comes up with some bizarre designs, but it turns out they're on the Pareto-optimal frontier. And then you can, by giving it different reward functions, have it come to different points on that frontier, whether you need speed at any area and power, or whether you need just enough speed to meet a clock cycle and you want the minimum area, minimum power at that point. And then the other way we've applied AI for chip design is really to sort of accelerate some analysis tools that take a long time. So by using the runs of existing analysis tools, things looking at, for example, IR drop and the like, we've been able to train tools to be very predictive. And actually one very productive use of that is these predictive tools can predict parasitics. And so it used to be our circuit designers would have to do a circuit design, we'd give it to a layout engineer, they would do the layout, we'd extract the parasitics. A couple days later, the circuit designer gets back and finds out their circuit doesn't work because the parasitics are worse than they thought. Now that cycle can be closed almost instantly, and it makes our circuit designers way more productive.
Great, so quick follow-up. Similar to AVs, do you see more and more of the human design being automated for chip design? Or do you think there's a limit to what can be done?
I think what we'd really like to do is basically make the humans more powerful by coupling them with AI to do the chip design. A lot of what we're doing right now just sort of either automates it entirely or moves it up a level. Another example is we now have a tool which, when we get a new set of design rules from a new process, like when we move to TSMC4, we basically used to have a team of about 10 people who would take a year to move our standard cell library, which has like 2,500 cells in it, into the new process. It now takes an automated tool a few days to do it, using RL to do that standard cell layout.
Okay. Well, I think our time has come to an end here. So thank you a lot for attending, and thank you to Bill for providing all the insights. And we'll turn it over to...
Thank you.
Thank you. Well, thank you so much, Bill and Kunle. I certainly don't know any better people to tell you all about the bowels and guts of what goes on behind the processes that support the amazing developments that have been taking place in AI. So on behalf of everyone at HAI, you've mainly been seeing me and Fei-Fei on stage, but there's been an enormous team helping out behind the scenes possible. We want to thank all the speakers that contributed to this day, and we want to thank all of you, whether you're audience in the room here today or people who are watching it online, for contributing to making this event successful. And we hope that there's been a good sharing of views and a lively discussion, and that will inform your thinking beyond this event.
Yeah, thank you again. And as always, I want to conclude this one-day conference with the words to students in the audience and students online. HAI is here for you to see possibilities. I hope today that you've seen the possibility of imaginative technology and creativity. You've seen the possibility of human-centered applications and use cases with this technology. But you'll also see the possibilities of harm and unwanted, unintended consequences. And this is why we're here. This is why we have established HAI 3 years ago. We invite you to this journey to work on technologies and interdisciplinary research and education programs to really better humanity with a human-centered mission. And I love what Kavita said to the audience today. We're here to keep us honest. And I want to end with the quote that we see a lot of debates and discussions on the platform of HAI. And William Penn has said, "In all debates, let truth be thy aim, not victory or an unjust interest." Thank you so much.